In the vast expanse of our universe, from the smallest subatomic particles to the most colossal cosmic structures, mysteries abound that continue to both challenge and captivate our understanding of reality. What secrets are concealed within the endless void of black holes? How did the first stars burst into life, illuminating the pitch-black canvas of the early universe? Could there be other forms of life scattered throughout the stars, or are we truly alone? These are the profound questions that have intrigued scientists, philosophers, and dreamers for centuries. Join us on an exhilarating journey as we explore some of the most mind-bending, awe-inspiring mysteries that have baffled scientists for generations. One of the most intriguing of these cosmic puzzles lies beneath the icy surface of Jupiter's moon, Europa. This small but fascinating moon, slightly smaller than Earth's own moon, holds a tantalizing secret: a vast, hidden ocean of liquid water. Europa has been a subject of scientific interest since the late 20th century, when data from missions like Voyager and Galileo first hinted at its watery depths. Its icy shell, approximately 10 to 15 miles thick, might seem impenetrable at first glance. However, beneath this frozen crust, scientists believe that an ocean could exist, stretching more than 60 miles deep, far surpassing the volume of all the water on Earth. What makes Europa's ocean so intriguing is the possibility of it being a habitable environment. The moon's chaotic surface terrain, regions where the ice has been disrupted and refrozen, suggests convection currents that could be driven from below. Tidal forces generated by Jupiter's immense gravitational pull cause friction within Europa's core, producing heat that prevents the ocean from freezing solid. This combination of factors, liquid water, chemical nutrients, and a source of energy, creates the conditions for life, raising the possibility that microbial life could exist in this hidden world. Missions like NASA's upcoming Europa Clipper are set to explore this enigmatic moon in greater detail, as scientists continue to search for clues that might reveal whether this moon harbors life beneath its icy surface. Another fascinating celestial body that stirs curiosity is Enceladus, one of Saturn's most captivating moons. Despite its relatively small size, its diameter is just 300 miles, Enceladus has become one of the most exciting places to search for extraterrestrial life. Beneath its frozen crust, Enceladus conceals a vast subsurface ocean, a discovery first suggested by the Cassini spacecraft. Cassini's observations revealed plumes of water vapor and icy particles erupting from fractures near the moon's south pole, known as tiger stripes. These geysers not only serve as evidence of a hidden ocean beneath the surface, but also offer clues about the chemical composition of that ocean. What makes Enceladus even more fascinating is the presence of organic compounds, salts, and silica grains in the plumes, indicating that chemical interactions are occurring between the ocean water and the moon's rocky core. These interactions could create the necessary energy for life, much like the hydrothermal vents found on Earth's ocean floor. Additionally, the detection of hydrogen in the plumes points to ongoing hydrothermal activity, which is a critical ingredient for life as we know it. While scientists have not yet confirmed the presence of life on Enceladus, the discovery of water, organic molecules, and geothermal energy makes it one of the most promising candidates for harboring microbial life in our solar system. Future missions, equipped with advanced instruments, may soon pierce through Enceladus's icy shell, potentially bringing us one step closer to understanding whether life exists beyond our planet. Then there is the extraordinary phenomenon of Saturn's hexagonal storm. Located at the planet's north pole, this bizarre storm has captivated scientists since its discovery by the Voyager spacecraft in the early 1980s. The hexagonal storm spans approximately 14,000 miles across, a size large enough to encompass nearly 4 Earths. Unlike the circular storms we are accustomed to on Earth, Saturn's hexagon remains a stable and persistent structure, puzzling researchers with its perfect angles and straight edges. The prevailing theory behind this geometric storm involves the concept of standing wave patterns within Saturn's atmosphere. Similar to wave patterns observed on Earth, these waves are thought to be generated by the differential rotation of Saturn's atmosphere. The planet's jet streams move at varying speeds, and the influence of a particularly strong eastward jet stream, referred to as a Rossby wave, causes a series of interacting winds and vortices. Over time, these interactions stabilize into the hexagonal shape, creating one of the most bizarre and mesmerizing weather phenomena in our solar system. Though scientists have yet to fully understand the mechanics behind Saturn's hexagonal storm, it serves as yet another reminder of the vast mysteries that our universe holds. From Europa's hidden ocean to the hexagonal storms on Saturn, the universe is brimming with puzzles that continue to defy our understanding. These celestial phenomena not only spark scientific inquiry, but also inspire us to look beyond the stars and imagine the possibilities that await us in the cosmos. As technology advances and our exploration of the universe deepens, we may one day uncover the answers to these age-old questions, revealing secrets that have eluded humanity for centuries. In this captivating exploration of Saturn, Venus, and Mars, we uncover the wonders of our solar system's most intriguing planets and their celestial bodies. Saturn's famous hexagon, observed by the Cassini spacecraft, extends deep into the atmosphere, reaching nearly 200 miles below the cloud tops. This astonishing phenomenon indicates that the hexagonal storm is not just a surface-level feature, but is deeply embedded in Saturn's complex atmospheric dynamics. What's even more mesmerizing is how this hexagon changes color with the seasons, transitioning from a bluish hue to a golden tone. This shift is further evidence of the interplay between atmospheric chemistry and solar radiation at Saturn's frigid poles, giving us a glimpse into the planet's rich and complex atmospheric processes. Venus, often referred to as Earth's sister planet because of its similar size and mass, defies expectations with a peculiar rotation that sets it apart from every other planet in the solar system. Unlike most planets, which rotate counterclockwise when viewed from above their north poles, Venus spins in the opposite direction, a retrograde rotation. This means that on Venus, the sun rises in the west and sets in the east. To make things even more fascinating, Venus has an extraordinarily slow rotation. It takes about 243 Earth days to complete one full spin, making its day longer than its year. The exact cause of this backward rotation is still debated by scientists, with several intriguing hypotheses coming to the forefront. One prominent theory suggests that Venus may have suffered a massive collision with another protoplanet or a series of smaller impacts in its early history. These catastrophic events could have altered its rotational axis and even reversed its direction. Another possibility points to the influence of solar tides. The immense gravitational pull of the sun may have gradually slowed Venus's initial rotation, eventually leading to its retrograde motion. Furthermore, the planet's thick and dense atmosphere, 90 times more massive than Earth's, plays a significant role. Atmospheric tides, caused by the extreme heat from Venus's runaway greenhouse effect, could interact with the planet's rotation, contributing to its unique motion. While simulations and models continue to evolve, it's likely that the true cause of Venus's backward spin is a combination of these factors, each contributing to the planet's distinctive characteristics. Mars, too, presents its own celestial puzzle with its tiny, irregular moons, Phobos and Deimos. Discovered in 1877 by American astronomer Asaph Hall, these moons bear more resemblance to asteroids than the familiar round shape of Earth's moon. Phobos has a diameter of about 14 miles, while Deimos measures about 8 miles across, both significantly smaller than the moon. Their odd shapes and surface features have led scientists to question their origins. One widely accepted theory proposes that Phobos and Deimos are captured asteroids from the asteroid belt, located between Mars and Jupiter. This theory is supported by the moon's composition, which closely resembles that of carbonaceous chondrites, a type of asteroid rich in carbon. However, capturing an asteroid and establishing a stable orbit around a planet is a notoriously difficult task, leading some scientists to explore other explanations. Another hypothesis suggests that the moons may have formed from debris resulting from a colossal impact on Mars. Such a massive collision could have launched material into orbit around the red planet, which then coalesced into Phobos and Deimos over time. This theory is bolstered by computer simulations, which show how collision debris can gather and accrete into moons. As our understanding of these fascinating celestial bodies deepens, we inch closer to solving the mysteries of these unique features in our solar system. The vastness and complexity of these planets and moons reveal just how much more we have yet to discover. Each discovery, whether it's the shifting hexagonal storm on Saturn, the retrograde rotation of Venus, or the origins of Mars's moons, adds a new layer to the rich story of our solar system. The moon Phobos, one of Mars's two small natural satellites, is steadily spiraling inward toward the red planet. This gradual descent is expected to culminate in a dramatic conclusion within the next 50 million years, where Phobos could either disintegrate or crash into Mars. This looming event aligns with a prevailing theory suggesting that Mars's moons, including Deimos, are not stable in the long term. Although definitive evidence remains elusive, the ongoing Martian Moons Exploration (MMX) mission, spearheaded by JAXA, aims to shed light on these enigmatic moons. By studying and possibly returning samples, MMX could provide groundbreaking insights, potentially solving the enduring question of their origins. The findings could unlock yet another fascinating chapter in our understanding of minor celestial companions. In a separate corner of our solar system, the dwarf planet Ceres, located in the asteroid belt between Mars and Jupiter, continues to captivate astronomers. Since its initial imaging by NASA's Dawn spacecraft in 2015, the bright spots within the outer crater on Ceres have baffled scientists. These unusually bright deposits, prominently located at the center of the crater, contrast sharply with the dark, heavily cratered surface of the dwarf planet. Detailed analysis has revealed that these spots are primarily composed of sodium carbonate, a type of salt. This discovery suggests the presence of significant geological activity beneath the surface of Ceres. These bright spots are believed to be the result of briny water reservoirs hidden beneath the planet's icy crust. When these reservoirs breach the surface through fractures in the crust, the salty water rapidly evaporates in the vacuum of space, leaving behind the reflective salt deposits we see today. This process indicates that, despite the frigid temperatures of Ceres, subsurface liquid water may exist, possibly kept in a liquid state by residual internal heat or antifreeze-like substances within the planet. The geophysical models and data collected by the Dawn spacecraft also suggest that Ader crater is relatively young, having formed less than 30 million years ago. The impact that created the crater likely exposed subsurface water ice, triggering hydrothermal activity and forcing the briny water upward. This discovery has profound implications for our understanding of small celestial bodies in the solar system, suggesting that even these seemingly inert objects may harbor the chemical ingredients necessary for life, or at least for prebiotic chemistry, either in the past or even today. Meanwhile, Uranus, one of the most peculiar planets in the solar system, continues to intrigue scientists with its extreme axial tilt. With an axial tilt of approximately 98 degrees, Uranus rolls around the Sun, with its poles alternately facing the Sun directly every 84 Earth years. This unusual orientation stands in stark contrast to the tilt of the other planets in our solar system. The cause of Uranus's extreme tilt has been a subject of scientific fascination for decades. The most widely accepted theory is that Uranus was struck by a colossal impact in the early chaotic days of the solar system, during a time when planetary formation was violent and tumultuous. It is believed that a protoplanet or a series of massive collisions might have knocked Uranus onto its side, permanently altering its axial tilt. Computer simulations support this hypothesis, indicating that such a dramatic tilt could be the result of a collision with an object at least twice the size of Earth. In addition to the planet's unusual orientation, Uranus's moons and magnetic field provide further evidence supporting the collision theory. The orientation of the planet's moons and the alignment of its magnetic field all match the tilted rotational axis of the planet itself. This alignment suggests that the same cataclysmic event that altered Uranus's tilt also affected its entire system of moons and rings. This theory continues to be explored, but regardless of the exact cause, Uranus remains one of the most fascinating and mysterious planets in our solar system. The study of its unique features continues to offer scientists valuable insights into the formation and evolution of planetary systems. Moreover, the internal structure of Uranus, combined with its unusual heat distribution, offers a compelling argument for a past marked by cataclysmic impacts. This evidence weaves a fascinating tale of a world that endured an enormous transformative collision, one so violent that it left Uranus with the unique tilt we observe today, making it a truly singular giant in our solar system. The planet's tilted axis, combined with peculiar internal dynamics, suggests an extraordinary history that continues to intrigue scientists, hinting at a past shaped by extreme forces. In contrast, Mercury, the closest planet to the Sun, faces some of the most dramatic temperature shifts found anywhere in the solar system. Unlike Earth, where an atmosphere and oceans work together to regulate temperatures, Mercury has no substantial atmosphere to mediate its surface conditions. This lack of an insulating layer plays a pivotal role in the intense and unpredictable thermal swings the planet experiences. During a Mercurian day, lasting approximately 59 Earth days, temperatures can soar to a blistering 800 degrees Fahrenheit, 427 degrees Celsius, a result of Mercury's proximity to the Sun. The planet receives over 7 times the solar energy per unit area compared to Earth, but without an atmosphere to help distribute or retain this heat, the planet is exposed to extreme fluctuations. At night, when Mercury's long rotation leads to its dark side, temperatures plummet drastically, reaching a chilling 330 degrees Fahrenheit, minus 201 degrees. Without any significant atmosphere to trap heat, the surface of the planet cools almost immediately, creating a stark contrast between the scorching daytime heat and the freezing nighttime cold. This extreme temperature variation is not just a curiosity, it has profound effects on Mercury's geology. The relentless expansion and contraction of the planet's surface due to these temperature shifts contribute to the formation of rugged cliffs and ridges. This dynamic, driven by Mercury's harsh thermal environment, shapes the planet's heavily cratered and rocky appearance, offering a glimpse into the violent processes that have shaped it over eons. Meanwhile, on Jupiter, one of the most fascinating features of the gas giant, the Great Red Spot, is undergoing a remarkable transformation. This massive storm, which has raged for over 400 years, has been shrinking in size over the past few decades. Once large enough to swallow 3 Earths side by side, it is now considerably smaller, puzzling scientists who have turned their attention to understanding the causes behind this mysterious change. Both Earth-based telescopes and spacecraft, such as NASA's Juno mission, have been instrumental in monitoring the storm, hoping to uncover the forces driving its contraction. One major factor contributing to the shrinking of the Great Red Spot is the shifting dynamics of Jupiter's atmosphere. The storm is a massive anticyclone, essentially a high-pressure system, where winds circulate counterclockwise in the planet's southern hemisphere. Over the years, the storm's vorticity, or its rotational energy, has decreased. As a result, the storm is weakening, unable to maintain its previous size and power. It seems that the Great Red Spot is losing a battle against Jupiter's surrounding jet streams and atmospheric turbulence, which are stripping away the storm's energy. This dramatic change in one of the solar system's most iconic features highlights the ever-changing nature of planetary systems and the mysteries that still await discovery. In both cases, the extreme environmental conditions, whether the searing heat and frigid nights of Mercury or the shrinking power of Jupiter's Great Red Spot, provide us with a fascinating lens into the forces shaping the planets of our solar system. Each of these phenomena not only serves as a reminder of the ever-evolving nature of our cosmic neighborhood, but also raises intriguing questions about the dynamic processes that govern planetary evolution and climate. In the vast and turbulent atmosphere of Jupiter, the Great Red Spot, a giant storm that has been raging for centuries, is constantly subjected to a variety of dynamic forces. Interactions with other atmospheric features play a crucial role in shaping its behavior. The Great Red Spot frequently encounters smaller, neighboring storms and vortices, which can disrupt its structure and siphon off its energy. This constant interplay within Jupiter's dynamic atmosphere contributes to the gradual erosion of the storm's boundaries, slowly shrinking the Great Red Spot over time. Observational data collected from space missions have shown that these interactions are not merely a superficial disturbance, but can physically fragment portions of the Great Red Spot, hastening its ongoing shrinkage. As these neighboring systems interact with the storm, they break apart parts of it, transferring energy and causing a gradual decrease in its size and intensity. Despite the Great Red Spot remaining one of the most extraordinary and iconic features of the planet, The persistent contraction of this massive storm suggests that even the most powerful weather systems in the universe are not impervious to the shifting and ever-changing forces of their environments. This phenomenon is a fascinating reminder of the dynamic and evolving nature of planetary atmospheres. The forces at play are complex, governed by the intricate interplay of weather systems that exist in the most extreme conditions. The Great Red Spot's gradual decline demonstrates that no matter how powerful or ancient, even the most colossal storms must adapt to their surroundings. The forces that drive this change also shed light on the broader understanding of atmospheric dynamics and the delicate balance that shapes the behavior of massive weather systems across the solar system. Far beyond Jupiter's stormy landscape lies Neptune, the distant and icy giant of our solar system. Hidden deep within this planet's mysterious interior is a phenomenon known as the hot ice layer, an exotic and captivating feature unlike anything we encounter on Earth. This term refers to water ice that exists under extreme pressure and temperature conditions, vastly different from the familiar frozen ice we see on our planet's surface. Neptune's internal structure is believed to consist of a rocky core, surrounded by a thick layer of water, ammonia, and methane ices, which are enveloped by an outer shell of hydrogen and helium atmosphere. Within this interior, the hot ice layer primarily consists of water, H2O, but exists in a form unlike any ice we encounter on Earth. The extreme conditions deep within Neptune's interior, pressures millions of times greater than Earth's atmospheric pressure, coupled with temperatures reaching thousands of degrees Celsius, force the water molecules into an exotic crystalline structure known as superionic ice. In this state, the oxygen atoms form a lattice structure, while hydrogen ions move freely within the lattice, resulting in a type of ice that is both solid and fluid-like at the same time. These unique conditions give rise to extraordinary physical properties. Superionic ice is characterized by high electrical conductivity and increased density when compared to conventional ice. While scientists on Earth have struggled to recreate such extreme environments, laboratory experiments using diamond anvil cells and high-energy lasers have provided valuable insights into the properties of this remarkable substance. These studies suggest that despite the high temperatures that would normally cause conventional ice to melt, the ice within Neptune remains solid due to the immense pressures present. Moreover, the presence of ammonia and methane in Neptune's atmosphere could further influence the formation and stability of this exotic ice, potentially leading to the creation of complex compounds not found naturally on Earth. Understanding the hot ice layer of Neptune provides scientists with an essential glimpse into the processes that occur deep within planetary interiors, as well as the broader understanding of the composition of ice giants. This research also holds significant implications for the study of exoplanets. Given the harsh environments and extreme pressures that exist in distant ice giants far beyond our solar system, it's possible that similar forms of superionic ice may exist on planets located light years away, offering a deeper understanding of the composition and nature of other icy worlds. Another fascinating exoplanet that highlights the extremes of planetary conditions is WASP-12b, a world that stands out not only for its hostile environment, but also for its strikingly dark appearance. This distant planet, located in a far-off star system, absorbs an extraordinary amount of light, giving it an ominously black appearance. The extreme conditions on WASP-12b, where temperatures can reach thousands of degrees and its atmosphere is subject to immense tidal forces, make it one of the most intriguing objects in the study of exoplanets. Just as Jupiter's Great Red Spot and Neptune's hot ice layer represent extreme atmospheric phenomena, WASP-12b pushes the boundaries of our understanding of planetary weather and composition. In conclusion, the study of extreme planetary environments offers valuable insights not only into the dynamics of our own solar system, but also into the broader nature of distant worlds. Whether it's the ever-shrinking Great Red Spot on Jupiter, the exotic hot ice layer of Neptune, or the incredibly dark and inhospitable surface of WASP-12b, each of these phenomena teaches us more about the complex and ever-evolving nature of planetary systems. Through research, we continue to uncover the mysteries of the universe, deepening our understanding of the forces that shape the very fabric of the planets and exoplanets that populate our galaxy. WASP-12b, a planet discovered in 2008, orbits its host star at a breakneck pace, completing a full revolution in just 1.1 days. This incredibly tight orbit exposes the planet to intense stellar radiation, superheating its atmosphere to temperatures exceeding 4,000 degrees Fahrenheit. These extreme conditions lead to some fascinating and extreme features of the planet, particularly its albedo, or reflectivity. Unlike most planets, which reflect a significant portion of the sunlight that hits them, WASP-12b is one of the darkest known exoplanets, absorbing almost all of the light that strikes it. In fact, it reflects back less than 6% of the incoming light, making it darker than fresh asphalt. This remarkable level of light absorption is primarily due to the unique composition of its atmosphere, which interacts with the intense radiation from its nearby star. In contrast to more reflective planets, the atmosphere of WASP-12b is composed of atoms and molecules like titanium oxide, sodium oxide, and ion hydrides, which are highly effective at absorbing visible light. Instead of reflecting light, these compounds trap stellar energy, converting it into heat. The result is a planet that absorbs nearly all incoming light, contributing to its incredibly dark appearance. The extreme temperatures on WASP-12b play a crucial role in preventing the formation of reflective clouds or hazes that are commonly seen on other gas giants. Most planets with atmospheres like those of Jupiter or Saturn have clouds that reflect sunlight, but WASP-12b's scorching heat keeps its atmosphere cloud-free, adding to its deep, dark appearance. Without reflective clouds, the planet's surface absorbs even more light, further intensifying its unusual darkness. Observations from the Hubble Space Telescope and other advanced instruments have been key in identifying these unique materials and understanding how they interact with the planet's environment. The study of WASP-12b provides invaluable insights into the wide array of atmospheric conditions found on exoplanets, revealing the fascinating mechanisms behind such dark, light-absorbing worlds. WASP-12b's extraordinary darkness offers a sharp contrast to the more familiar reflective gas giants in our own solar system, such as Jupiter and Saturn, showcasing the astonishing variety of planetary systems across the cosmos. While we gaze at the night sky and marvel at the many colors and features of planets, it is these extreme exoplanets, with their alien environments and mind-boggling atmospheric dynamics, that highlight the true diversity of the universe. In a similar vein, HD 199733b, a vivid blue exoplanet located 63 light-years away in the constellation Vulpecula, provides an equally striking contrast. While its azure hue may resemble Earth's, the source of its blue coloration is far from earthly. On our planet, the blue sky is a result of Rayleigh scattering, where sunlight is dispersed by Earth's atmosphere. But on HD 199733b, the blue tint arises from an entirely different phenomenon. This scorching hot Jupiter, which orbits extremely close to its host star, experiences surface temperatures of around 1,800 degrees Fahrenheit. Such intense heat leads to truly bizarre weather conditions. One of the most captivating features of HD 1897333b's atmosphere is the presence of silicate particles and condensed metals, such as magnesium silicate, in its upper atmosphere. These particles can form clouds and even molten glass rain. As the glass particles fall through the atmosphere, they scatter blue light more efficiently than other wavelengths due to their size and specific optical properties, creating the planet's distinctive blue color. The extremely high temperatures contribute to this unique atmospheric composition, as the planet's heat allows the condensation of metals into tiny droplets of molten glass. Adding to the planet's already hostile environment are the high-speed winds that blow at over 4,300 miles per hour. These winds are so strong that they turn the molten glass rain into a horizontal torrent, making the weather on HD 1897333b even more violent and dangerous. The combination of molten glass rain, extreme heat, and supersonic winds creates a truly bizarre and alien environment. The planet's blue hue is not just a visual quirk, but a direct result of its unique atmospheric conditions and violent weather systems. This extreme exoplanet underscores the diversity of planetary atmospheres, offering a fascinating glimpse into the complex interactions between atmospheric chemistry, local conditions, and planetary characteristics. In conclusion, the study of exoplanets like WASP-12b and HD 199733b reveals the vast and mind-blowing variety of planetary environments that exist beyond our solar system. These planets, with their unique atmospheric compositions, extreme temperatures, and hazardous weather, challenge our understanding of what is possible in the universe. They not only broaden our knowledge of other worlds, but also highlight the endless possibilities that exist within the cosmos, each one with its own set of wonders waiting to be explored. In the fascinating realm of exoplanetary science, as both instruments and observational techniques continue to evolve, our understanding of the most extreme and exotic climates beyond our solar system is expanding at an astonishing rate. Among these alien worlds, the concept of diamond rain on Neptune and Uranus stands out as one of the most captivating phenomena in planetary science. This unusual weather event, which is far from being mere science fiction, is rooted in the unique environmental conditions deep within these icy giants. Both Neptune and Uranus are shrouded in thick atmospheres primarily composed of hydrogen and helium, with considerable amounts of methane, ammonia, and water vapor. It is, however, the presence of methane that lays the foundation for one of the most extraordinary atmospheric processes known to science: the creation of diamonds. Methane, a simple yet crucial molecule made up of one carbon atom bonded to 4 hydrogen atoms, plays a pivotal role in this process. Under the extreme pressures and temperatures found thousands of kilometers beneath the surface of Neptune and Uranus, which can reach a blistering 7,000 degrees Fahrenheit, methane molecules begin to break apart. The environmental conditions here, intense pressure and extreme heat, force the carbon atoms to detach from the methane molecules. As pressure continues to build, these free carbon atoms are compressed and reorganized into crystal structures, eventually forming diamonds. These tiny diamonds then begin their descent through the planet's thick atmospheres, falling potentially thousands of kilometers toward the core. This phenomenon is not a mere theoretical concept, but is supported by experimental evidence gathered on Earth. Using high-pressure devices like shock compression techniques, scientists have successfully recreated the intense conditions believed to exist within the depths of Neptune and Uranus. In these laboratory settings, carbon atoms do indeed form diamond-like structures when subjected to such extreme pressure. The evidence strongly supports the idea that these distant worlds experience actual diamond rain. But this diamond rain isn't just an intriguing display of cosmic oddities. It may have significant implications for the internal dynamics of these planets. As the diamonds fall toward the cores of Neptune and Uranus, they generate frictional heat. This heat could contribute to the planet's overall thermal profile, potentially playing a role in their magnetic fields. Such insights not only enhance our understanding of Neptune and Uranus, but also provide valuable clues about the interior dynamics of exoplanets with similar compositions. In essence, studying these phenomena enriches our knowledge of planetary science and widens the scope of what we can expect from other worlds scattered across our galaxy. A striking example of how extreme planetary environments can defy our expectations comes in the form of Kelt 9b, a remarkable exoplanet that was discovered in 2016. Orbiting its star, Kelt 9, a luminous A-type star, every 1.5 days, Kelt 9b experiences some of the harshest conditions known to exist in the cosmos. Due to its extreme proximity to its host star, the day side of Kelt 9b reaches temperatures soaring to a blistering 7,800 degrees Fahrenheit. To put this into perspective, the day side of Kelt 9b is even hotter than some stars, including red dwarf stars, which typically have surface temperatures around 6,000 degrees Fahrenheit. Several factors contribute to this extreme thermal environment. Kelt 9b orbits its star at an incredibly close distance of just 4 million kilometers, far closer than Mercury is to our own sun. This tight orbit exposes the planet to an immense amount of radiant energy from its host star. Additionally, Kelt 9, the star itself, is much hotter and more massive than our sun, emitting a substantial amount of ultraviolet radiation. This intense energy bombardment from both the star and its high-temperature atmosphere makes Kelt 9b one of the hottest known exoplanets. Kelt 9b's extreme climate challenges everything we thought we knew about exoplanetary environments. It forces us to rethink the boundaries of habitability, highlighting how diverse and unusual planetary systems can be across the galaxy. As scientists continue to study such extreme worlds, they uncover new insights into the vast and varied array of climates that exist far beyond our solar system. The discovery of these otherworldly phenomena not only enhances our knowledge of distant planets, but also illuminates the incredible diversity of planetary processes at work in the universe. Each new revelation pushes the boundaries of our understanding, inspiring awe and wonder at the mysteries that lie beyond the reach of our everyday experience. Kepler 9b, a planet so extreme that it's locked in a state where one side is bathed in constant sunlight while the other remains cloaked in endless darkness. This tidal locking results in a staggering temperature difference between the two hemispheres. On the sunlit side, temperatures soar to unbearable levels due to the relentless bombardment of stellar radiation. The darkness of the night side, however, offers no relief. Without the cooling effect of the sun, heat accumulates, creating a volatile atmosphere where energetic processes rage. The intense heat forces the planet's hydrogen-rich atmosphere to break down, ionizing and dissociating the gases into a plasma-like state. This creates a turbulent and highly dynamic environment. What makes Kepler 9b particularly fascinating is the atmospheric winds, fueled by the stark temperature contrasts. These winds act as a kind of heat redistribution system, moving energy around the planet in an effort to stabilize the extreme disparities between day and night. Scientists are drawn to this planet not only because of its striking conditions, but also because it provides unparalleled insights into exoplanetary physics, especially when it comes to star-planet interactions and the atmospheric compositions that arise under such extreme heat. By studying planets like Kepler 9b, we expand our understanding of the forces at play in distant planetary systems and gain a deeper comprehension of the complex environments that exist in the farthest reaches of our galaxy. Now imagine a world where the sky isn't filled with a single star, but two suns engaged in an eternal cosmic dance. Welcome to Kepler 16b, a planet located 200 light-years from Earth. This remarkable exoplanet orbits not one but two stars, a phenomenon known as a circumbinary orbit. Kepler 16b, about the size of Saturn, showcases how intricate gravitational forces can create stability even in seemingly chaotic conditions. The two stars that Kepler 16b orbits are locked in a tight gravitational embrace, orbiting each other every 41 days. But how does the planet avoid being torn apart by the gravitational pull of two suns? The answer lies in a delicate balance of forces. The two stars create a unified gravitational field, rather than acting as two separate forces pulling on the planet. This allows Kepler 16b to follow a stable orbit around the barycenter, the point around which both stars orbit, effectively allowing the planet to move as if it were under the influence of a single star. Despite the planet's relatively close proximity to its suns, orbiting at a distance similar to Venus's orbit around our sun, Kepler 16b enjoys a steady and stable orbit due to this celestial choreography. It's a remarkable display of cosmic stability, further expanding our understanding of how complex systems in the universe can remain in harmony. Finally, meet the ancient planet PSR B620-26b, affectionately called Methuselah, after the biblical figure known for his long life. This planet holds the record as one of the oldest ever discovered, estimated to be 12.7 billion years old. Orbiting a binary system of dead stars, a pulsar, and a white dwarf, Methuselah stands as a living testament to the cosmos's longevity. But what makes this planet so ancient? For most planets, their lifespans are tied closely to the fate of their parent stars. However, Methuselah's story is different. It originated around a star much like our sun, but as the universe aged, so too did its star. The once main sequence star evolved into a red giant and eventually shed its outer layers, leaving behind the pulsar and white dwarf that now dominate the system. Methuselah's survival through such an extraordinary timeline challenges our understanding of planetary formation and endurance. Its existence in the early universe offers invaluable insights into the processes that shape the very fabric of our cosmos, providing a glimpse into the ancient past of exoplanetary systems and the incredible resilience of worlds in the face of cosmic evolution. In the dense heart of the universe, where gravitational forces sculpt the lives of stars and planets, one celestial system reveals the fascinating story of evolution, survival, and strange cosmic relationships. This system, which includes a white dwarf, a pulsar, and a planet known as Methuselah, offers a glimpse into a past long forgotten by most of the universe's inhabitants. Methuselah's journey began in the midst of a planetary system already in turmoil. As it orbited its aging star, this once vibrant system was gradually transformed by a powerful stellar encounter. The pulsar, an intensely magnetic and rapidly spinning neutron star, arrived in the system, disrupting the status quo. It is in this event that Methuselah experienced a unique cosmic bond with the pulsar, followed by the white dwarf that replaced the aging star. But the gravitational forces didn't stop there. The system's dense, packed environment allowed for intense gravitational interactions, pushing the planet into a new and unexpected trajectory. The globular cluster M4, home to this stellar congregation, played a crucial role in shaping Methuselah's cosmic destiny. In this crowded and ancient stellar nursery, the intense interactions between stars and other remnants allowed Methuselah to achieve an almost unimaginable age, one that carries it into the deepest reaches of time. As the planet continues its orbit around these remnants, its journey not only marks its age, but also offers profound insight into the early universe's conditions. The stars of M4, ancient in their own right, have set the stage for Methuselah's continued existence, and its relationship with the pulsar and white dwarf speaks to a cosmic dance that unfolds in the most unexpected of ways. Then there's WASP-107b, a planet that defies all conventions of planetary science. Situated about 212 light-years away in the constellation Virgo, WASP-107b may resemble Jupiter in size, but its density is a mere fraction of that gas giant's. Imagine a planet the size of Jupiter, but weighing less than 1/10 of what you'd expect, closer to the mass of Neptune. This bizarre planet is a super puff, a term that captures its lightness due to an unusually large, thin atmosphere that's been stretched over its core. What's most perplexing about WASP-107b is its ability to retain such an immense atmosphere, despite having a core much smaller than what would typically be required to support such a structure. Scientists believe that during its formation, WASP-107b must have captured a vast amount of gas from the surrounding protoplanetary disk, despite its modest initial size. The planet's core, smaller than expected, suggests that it managed to gather and hold this gas with remarkable efficiency, a process unlike anything seen in traditional gas giant formation. The planet's close proximity to its star, just 8 million kilometers, exacerbates this inflation. The intense heat from the star heats the planet's atmosphere to extreme levels, further bloating it into its peculiar super puff form. This strange planet challenges our conventional understanding of gas giants, showing that there are more ways for planets to evolve than we have imagined, expanding our knowledge of planetary formation in the universe. Then there is the fiery and extreme world of HD 189733b, a gas giant located 64 light-years away in the constellation Vulpecula. This planet is a living example of how extreme weather can be when a planet is subject to both the forces of nature and the peculiarities of its orbit. The weather on HD 189733b is nothing short of astonishing, with winds that scream across the surface at speeds of up to 5,400 miles per hour. These winds are nearly 7 times faster than the strongest hurricanes on Earth, a phenomenon caused by the planet's proximity to its star. HD 189733b, classified as a hot Jupiter, orbits its parent star at blistering speeds, completing an orbit in just over 2 Earth days. It is tidally locked, meaning it always shows the same face to its sun, much like how the moon always shows the same face to Earth. This tidally locked nature creates extreme temperature variations across the planet, with one side scorched by the heat of its star, reaching temperatures over 1,200 degrees Celsius, while the opposite side is left in relative cold. This stark difference in temperature between the day and night sides generates fierce winds as the atmosphere desperately tries to balance the thermal disparity. In the extreme heat of the day side, winds race from the blistering temperatures towards the cooler night side, creating an environment of constant motion and fierce atmospheric dynamics. The planet's proximity to its star and the fierce weather systems combine to make HD 189733b a world where survival is shaped by extremes of temperature, of wind speed, and of the relentless forces that govern its existence. This world, seemingly inhospitable to life as we know it, still offers a unique look into the wild range of possibilities for planetary systems in our universe. HD 189733b, a world in the depths of space, where the laws of nature seem to bend and twist under the force of extreme conditions. This distant exoplanet reveals one of the most turbulent atmospheres ever observed. The sky, if one could ever gaze upon it, is a swirling mass of silicate particles, fine, dust-like debris that is constantly whipped through the air by winds that reach terrifying speeds. These winds are no ordinary breezes, but ferocious gusts that can tear apart anything in their path. The cause of this furious atmosphere is the immense heat of the planet's parent star, a powerful force that vaporizes the silicate particles into clouds. These clouds don't simply hang in the air. They drive the atmosphere itself, stirring up winds that only grow stronger. The combination of intense stellar heat, rapid planetary rotation, and vaporized silicate clouds creates an atmosphere so violent it rivals the harshest storms found in our own solar system. Yet HD 189733b isn't the only planet that shows us the extremes of cosmic weather. Coro 7b, located 489 light-years away in the constellation Monoceros, is another marvel of planetary survival. This rocky world, known as a lava planet, defies our expectations for how planets should behave when they're so close to their parent star. Orbiting its star every 20 hours, roughly 23 times closer than Mercury is to our Sun, Coro 7b is constantly bombarded by scorching temperatures. These conditions, which are enough to melt rock on its surface, should, in theory, cause it to disintegrate. But against all odds, Coro 7b remains intact. What gives it such resilience? The answer lies in its solid composition. Unlike gas giants, which would likely be vaporized in such intense heat, Coro 7b is a rocky planet, formed from durable metals and silicates. Its dense, heavy core holds it firmly in place, and it may also have a magnetic field that offers some protection from the planet's extreme environment. Even though its atmosphere has likely been stripped away by the star's fierce winds, the planet endures, clinging to existence with sheer force of will. This remarkable survival so close to a star forces us to reconsider the limits of planetary habitability. Coro 7b stands as a testament to the surprising adaptability of planets, even in the harshest of conditions. But it's not just about survival. Glycine 436b presents another intriguing puzzle. A Neptune-sized exoplanet orbiting the red dwarf star Glycine 436, it resides about 30 light-years away in the constellation Leo. Despite its surface temperatures soaring beyond 800 degrees Kelvin, this world manages to maintain a substantial amount of water ice, creating a paradox that has long confounded scientists. How can water ice exist on a planet that is so hot? The answer lies in Glycine 436b's extreme gravitational forces. The immense pressure at the planet's core forces water into a state known as superionic ice, or ice 7. In this phase, water molecules are compressed so tightly that they form a solid structure, despite the high temperatures. This strange form of water exists only under extraordinary pressure, and it could not survive under Earth-like conditions. Scientists continue to study this phenomenon, intrigued by the strange interplay of heat and pressure that gives rise to this otherworldly ice. But that's not all. Glycine 436b's atmosphere also presents mysteries of its own. Observations suggest the presence of hydrogen in its atmosphere, which could contribute to the planet's extraordinary heat retention. Even as ice remains solid beneath the surface, the planet's unique atmosphere keeps it locked in a perpetual state of high temperatures and pressure. These worlds, HD 189733b, Coro 7b, and Glycine 436b, are not just distant specks in the cosmos. They challenge everything we know about planetary science, about survival, and about the extremes of nature. Each of these planets reveals a different facet of the universe's ability to create and sustain life in ways we cannot yet fully understand. The laws of physics, it seems, are not as rigid as we once thought. Instead, they bend and stretch under the weight of these strange and wondrous worlds. In the vast expanse of our universe, one of the most extraordinary phenomena to ever be discovered lies within the depths of space, the enigmatic gas giant Glia 436b. This planet's atmosphere, teeming with methane and other volatile compounds, presents an anomaly for researchers. Such elements typically disintegrate at the extreme temperatures that Glia 436b experiences, yet these compounds persist in the atmosphere. How? This remarkable feature points to a complex interplay of factors: gravitational compression, unique chemical composition, and intricate heat transfer processes. Together, they create a planetary environment that defies conventional understanding. Glia 436b, it seems, serves as a one-of-a-kind laboratory pushing the very limits of planetary physics. This blend of forces not only challenges our comprehension of gas giants, but also forces us to rethink what is possible for planets at the intersection of ice and gas giants. The behavior of this planet's atmosphere redefines what is achievable in terms of temperature, pressure, and atmospheric composition. As we continue to study Glia 436b, we edge closer to revealing new truths about planetary systems, raising profound questions about what other mysteries our universe still holds. Could this distant world hold the key to discovering other celestial bodies that stretch the boundaries of what we know? In the heart of our Milky Way galaxy, another awe-inspiring cosmic object looms large: Sagittarius A, a supermassive black hole of unimaginable power. Astronomers have been able to detect its presence through the profound gravitational effects it has on the stars and gas clouds in its vicinity. Despite being invisible to the human eye, no light can escape its crushing gravitational pull. The impact of Sagittarius A is unmistakable. It exerts such force on its surroundings that the evidence of its existence is undeniable. This colossal entity has a mass about 4 million times that of our Sun, yet all of this mass is confined to a region no larger than the orbit of Mercury. This presents an extraordinary paradox: a celestial body so powerful and dense that it warps the fabric of space and time itself. The environment surrounding Sagittarius A is as extreme as one can imagine. As gas and dust spiral toward it, they form an accretion disk, an immense rotating disk of matter heated to millions of degrees by the immense friction and gravitational forces. This superheated disk emits X-rays and other forms of high-energy radiation, which are detectable by space-based telescopes. This radiation paints a vivid picture of the cosmic dynamics taking place at the heart of the Milky Way. But the forces at play around Sagittarius A side don't end with the accretion disk. The gravitational influence of the black hole is so strong that it accelerates nearby stars to speeds of up to several thousand kilometers per second, creating high-speed orbits that defy normal expectations. This phenomenon has been crucial in helping astronomers pinpoint not only the location of this black hole, but also its immense mass. Recent observations have provided even more tantalizing clues. Flares and bursts of radiation detected in the area surrounding Sagittarius A suggest that dramatic interactions are occurring just beyond the event horizon, the point beyond which nothing, not even light, can escape. These observations have sparked new lines of inquiry, compelling scientists to develop more advanced technologies and theories to unravel the mysteries of galactic centers. With each new breakthrough, we move closer to understanding not only the black hole at the center of our galaxy, but also the broader nature of black holes across the universe. The formation of supermassive black holes remains one of the most tantalizing puzzles in astrophysics. These giants, with masses ranging from millions to billions of times that of our Sun, are believed to be the gravitational anchors at the heart of galaxies. While their exact origins remain a subject of intense debate, several theories aim to explain how such colossal structures came into being. One prominent hypothesis posits that supermassive black holes may have originated from the collapse of enormous primordial gas clouds in the early universe. These clouds, devoid of metals and elements that could cool and fragment the material, might have bypassed the usual star formation process, collapsing directly into black holes with masses equivalent to thousands of suns. Over time, these early black holes could have accumulated more matter, growing into the supermassive entities that we observe today. Another possible formation route involves the frequent mergers and accretions that occur in the dense, chaotic environments at the centers of young galaxies. In these crowded regions, massive stars collide and merge, creating intermediary mass black holes. These black holes, drawn to the galaxy's center through gravitational interactions, would eventually combine to form a supermassive black hole. This process, known as dynamical friction, would ensure that the black hole continues to grow as it consumes gas, stars, and even smaller black holes. The theory of hierarchical mergers adds another layer of complexity to the story. Gravitational wave observations have revealed that black holes often merge over cosmic time, leading to the formation of increasingly massive black holes. These mergers, combined with direct collapse and accretion, form the foundation for the creation of the supermassive black holes that anchor galaxies. As we continue to explore the mysteries of these cosmic giants, the process by which they form, grow, and interact with their surroundings becomes clearer. Sagittarius A is a perfect example of how supermassive black holes shape not only their host galaxies, but the very fabric of the universe itself. Every new observation, every burst of radiation adds to our understanding, pushing the boundaries of astrophysical theory and revealing the intricate cosmic dance that takes place within the heart of every galaxy. These findings remind us that the universe is full of mysteries, some we've yet to even begin to uncover. By exploring these formation theories, astronomers can reconstruct the evolutionary journey of these cosmic giants, providing us with valuable insights into the nature of black holes and the galaxies they reside in. This not only deepens our understanding of the black holes themselves, but also enhances our comprehension of the dynamic and fascinating nature of the universe. The Cartwheel Galaxy in particular offers an awe-inspiring visual spectacle, a cosmic work of art. Its unique wheel-like appearance sets it apart from conventional galaxy structures, showcasing the beauty of the cosmos. This extraordinary form is primarily the result of a catastrophic galactic collision that occurred hundreds of millions of years ago. The key to understanding the Cartwheel Galaxy's exceptional shape lies in the violent interactions it endured and the subsequent gravitational forces at play. Located approximately 500 million light-years away in the constellation Sculptor, the Cartwheel Galaxy was once a typical spiral galaxy, much like countless others scattered across the universe. However, its destiny dramatically shifted when it collided with a smaller galaxy that barreled through its core. This high-speed collision sent shockwaves of gravitational energy rippling outward, creating a profound disturbance in the galaxy's structure, much like the ripples formed when a stone is thrown into a pond. These shockwaves compressed the interstellar gas and dust, sparking a surge of new star formation that radiated outward in a ring-like pattern from the point of impact. The result of this cosmic collision is the Cartwheel Galaxy's striking ring of hot, young stars, which encircle its core, giving the galaxy its iconic appearance. This ring is often referred to as a starburst ring, due to the intense and ongoing star formation that it hosts. Surrounding this central ring are the galaxy's spiral arms, now stretched and distorted by the gravitational forces that arose from the collision. The remnants of the smaller galaxy that once collided with the Cartwheel are likely scattered at the galaxy's outskirts, or perhaps even merged into its structure. Through multi-wavelength observations spanning X-rays, ultraviolet, optical, and infrared light, scientists have gained profound insights into the dynamic processes taking place within the Cartwheel Galaxy's core and outer ring. These observations reveal the chaotic and transformative nature of galactic collisions, where galaxies not only survive such violent encounters, but are often completely reshaped by them, resulting in mesmerizing structures like the Cartwheel Galaxy. Galaxies such as NGC 1277, often described as red and dead, are equally captivating relics of the universe's earlier epochs. Located approximately 220 million light-years away in the Perseus cluster, NGC 1277 stands out for its old stellar population, with little evidence of recent star formation. This ancient stellar composition provides a unique window into the early stages of galaxy formation and evolution. The origins of such galaxies are believed to unfold in stages, influenced by both intrinsic properties and external factors present in the universe's early days. In the distant past, NGC 1277 likely experienced a period of rapid and intense star formation, fueled by the abundant gas reserves available at the time. This phase, known as a starburst, rapidly consumed vast quantities of gas, creating a dense, compact galaxy filled with massive young stars. These early bursts of star formation played a crucial role in generating many of the heavy elements now found in the galaxy. However, what makes NGC 1277 particularly fascinating is the swift cessation of star formation that followed. Several mechanisms could explain this sudden halt, with one possibility being the exhaustion of the galaxy's gas supply during the starburst phase, leaving little material for further stellar births. Another potential factor that could have contributed to this quenching of star formation is the environmental influences within the dense environment of the Perseus cluster. NGC 1277 may have undergone gravitational interactions with neighboring galaxies, or even been affected by the hot intracluster medium, which could have stripped away its remaining gas through a process called ram pressure stripping. This process would have significantly reduced the available material needed to fuel new stars, effectively halting the galaxy's star-forming activity. These findings not only help us understand the history of NGC 1277, but also offer broader insights into the complex processes that shape galaxies throughout the universe. In the vast and mysterious universe, supermassive black holes, particularly those found at the centers of galaxies like NGC 1277, wield a profound influence over their surrounding environments. These cosmic giants can prevent new star formation by heating the surrounding gas through energetic outflows and radiation. This process, known as feedback, halts the cooling and collapse of gas, which would typically lead to the creation of new stars. As a result, galaxies like NG 1277 transition into a phase dominated by their ancient stellar populations. The stars within these galaxies, which formed billions of years ago, now dominate the galaxy's mass, giving NGC 1277 its characteristic appearance of older red-hued stars. By studying galaxies in this state, astronomers can gain a deeper understanding of the evolutionary pathways that galaxies can take over cosmic time, revealing the intricate processes that halt star formation and cause galaxies to mature. As astronomers explore the cosmos, one of the most fascinating and perplexing features of the universe's large-scale structure is the presence of immense cosmic voids. These vast expanses of nearly empty space can span tens to hundreds of millions of light years and stand in stark contrast to the dense clusters of galaxies found along cosmic filaments. The creation of these colossal voids is intricately tied to the interplay of gravity and the conditions set by the Big Bang. Immediately after the Big Bang, the universe was a hot and dense soup of nearly uniform matter and radiation. Tiny fluctuations in density caused by quantum perturbations during the rapid inflationary phase seeded areas of slightly higher and lower density. As the universe expanded and cooled, gravity began to pull together areas of higher density, leading to the formation of galaxies and galaxy clusters. These clusters anchored the cosmic web's filaments and nodes, while the regions of lower density began to expand. Lacking the necessary mass to initiate gravitational collapse, these areas continued to spread out, forming the vast voids that we observe today, vast pockets of emptiness surrounded by dense cosmic structures. The role of dark energy in this process cannot be understated. Dark energy, the mysterious force driving the accelerated expansion of the universe, accelerates the evacuation of matter from these underdense regions, making the voids even emptier as time progresses. Simulations of cosmic structure formation based on dark matter and dark energy principles have helped astronomers reproduce the observed distribution of voids. These simulations highlight the essential role that dark matter, which makes up about 85% of the universe's mass, plays in structure formation. Dark matter interacts gravitationally with ordinary matter, guiding it to clump together along the cosmic web. In doing so, dark matter sculpts the vast voids that exist amid the larger cosmic structures. By studying these immense voids, astronomers can uncover critical insights into the composition of the universe, its expansion history, and the fundamental forces that shape its evolution. At the same time, the vast filaments of galaxies and dark matter, known as galactic filaments, form one of the most striking and visually captivating features of the cosmic web. These massive structures, which stretch across hundreds of millions of light years, weave a complex network of galaxy clusters, with nodes and intersections where galaxies accumulate. The stability and endurance of these filaments over cosmic time depend on several key factors, most notably gravity, dark matter, and the ongoing interaction with the surrounding cosmic environment. Dark matter, which makes up about 85% of the universe's mass, is invisible as it does not interact with electromagnetic radiation. Despite its elusive nature, dark matter plays a critical role in the formation and maintenance of these filaments. It exerts gravitational pull, clumping together to form scaffolds that draw in ordinary matter such as gas and stars, which coalesce to form galaxies and galaxy clusters along these filaments. The gravitational wells created by dark matter ensure that ordinary matter continues to accumulate, reinforcing the structure of these cosmic filaments. The influence of Einstein's theory of general relativity further helps to explain how massive objects warp the fabric of space-time, contributing to the gravitational dynamics that preserve the integrity of these cosmic filaments. As matter flows through the cosmic web, it is drawn into the filaments, continually feeding and reinforcing their structure. Yet, there is also a more subtle force at play: dark energy. While dark energy drives the accelerated expansion of the universe, its effect varies depending on the scale of cosmic structures. On the larger scales, such as between superclusters, dark energy accelerates the expansion, pushing structures apart. However, within individual filaments, the gravitational forces from dark matter and ordinary matter dominate, binding the structures together and counteracting the expansive influence of dark energy. This delicate balance of forces allows the filaments to maintain their structure, despite the universe's relentless expansion. In the grand scheme of the cosmos, these cosmic filaments, voids, and the forces of dark energy and dark matter are not mere curiosities. They are the foundational elements that define the universe's large-scale structure. By studying these cosmic features, astronomers gain invaluable insights into the ongoing evolution of the universe, shedding light on the forces that shape its past, present, and future. The cosmic web, with its vast interconnectedness, provides a stunning example of the beauty and complexity of the universe on the grandest scales. In the ongoing dance of cosmic evolution, the formation and interactions of galaxies play a crucial role in shaping the vast, interconnected structure of the universe. Within these intricate filaments, galaxies undergo mergers and accretion processes that redistribute matter, shaping the very fabric of the cosmic web. These dynamic interactions are essential to maintaining the coherence of the filamentary structure, even as individual galaxies evolve and change over time. The profound gravitational forces at play within these filaments continuously influence the arrangement of galaxies and clusters, ensuring the preservation of a unified cosmic pattern despite the relentless forces of galactic evolution. To validate these cosmic phenomena, cutting-edge cosmological simulations powered by sophisticated computational models have provided invaluable insights. These simulations incorporate elements like dark matter, baryonic matter, gravity, and dark energy, replicating the observed large-scale structure of the universe with impressive accuracy. The alignment between these theoretical models and actual astronomical observations underscores the reliability and robustness of these mechanisms in shaping the cosmic landscape. Through the symbiotic interplay of gravity, dark matter, and cosmic dynamics influenced by dark energy, the galactic filaments endure, providing us with an awe-inspiring window into the universe's grand design that stretches across both time and space. The periodic structure of the universe, often referred to as the cosmic web, unveils a breathtaking arrangement of galaxies, clusters, and superclusters, all interconnected by vast filaments. Between these intricate filaments lie the colossal voids, creating a remarkable and organized architecture that reflects the underlying physical processes that shaped the universe. This grand design is not a random accident, but the result of a well-ordered system influenced by the fundamental forces that govern our reality. The roots of this cosmic periodicity stretch all the way back to the earliest moments of the universe, specifically during the epoch of inflation, a brief but powerful period of exponential expansion that occurred just fractions of a second after the Big Bang. During this time, quantum fluctuations were stretched to macroscopic scales, seeding regions of varying densities in the primordial plasma. These density fluctuations provided the blueprint for the large-scale structure that we observe today, forming the scaffolding upon which galaxies and other cosmic structures would later be built. As the universe continued to expand and cool, these primordial fluctuations began to give birth to areas of varying matter concentrations. Gravity, in turn, amplified these differences, pulling denser regions together and causing them to clump into galaxies, galaxy clusters, and superclusters. Meanwhile, the less dense areas became the vast cosmic voids, immense spaces where matter was sparse. This process of gravitational collapse and clustering took billions of years, eventually resulting in the cosmic web that spans the observable universe today. A critical phenomenon driving this process is known as baryon acoustic oscillations, BAOs. In the early universe, sound waves propagated through the hot, dense plasma formed by matter and radiation. These oscillations left subtle imprints in the distribution of matter, particularly when electrons and protons combined to form neutral hydrogen. This transition allowed radiation to decouple from matter, creating the cosmic microwave background, the afterglow of the Big Bang. The characteristic scale of these acoustic waves is still evident today in the slight preferential separation between galaxies. This standard ruler provides invaluable measurements for cosmologists, helping them refine our understanding of the universe's expansion and its intricate structure. At the heart of this process lies dark matter, which makes up about 27% of the universe's total mass energy content. Though it does not interact with light, dark matter exerts a profound gravitational influence, forming a kind of invisible scaffolding that guides the clumping of normal matter, or baryonic matter. Regions rich in dark matter became the birthplaces of galaxies, reinforcing the periodic patterns set in motion by the primordial fluctuations and BAOs. This invisible force shapes the universe in ways we are only beginning to understand, playing a vital role in the formation of large-scale structures. Equally crucial is the influence of dark energy, which constitutes approximately 68% of the universe's total mass energy content. Dark energy acts as the driving force behind the accelerated expansion of the universe, subtly altering the periodic arrangement of cosmic structures over time. While dark energy pushes galaxies and clusters apart on the largest scales, its effect is most pronounced in the vast voids between the filaments and clusters. It is within these vast emptinesses that dark energy plays a more prominent role, affecting the distribution of matter and subtly altering the cosmic architecture. As we combine the insights gathered from advanced observations and simulations, the ongoing evolution of the cosmic web comes into sharper focus. These interwoven filaments, shaped by the interplay of gravity, dark matter, and dark energy, form the very backbone of the universe. The grand design of the cosmos is revealed through these interconnected structures, providing a captivating window into the universe's deepest mysteries, stretching across time, space, and the very fabric of existence itself. In the vastness of the universe, scientists continue to unlock the mysteries of cosmic evolution, delving into the structure of the cosmos and the forces that shape it. Through advanced telescopic surveys and sophisticated simulations, researchers have found a remarkable alignment between theoretical models and actual observational data, revealing the periodic structure of the cosmic web. These models, which integrate the effects of inflation, dark matter, and dark energy, offer a unified framework for understanding how the universe's large-scale structures came to be. This alignment presents a powerful testament to the intricate unity and complexity underlying the cosmos, highlighting the remarkable processes that have shaped everything we observe in the vast expanse of space. One of the most awe-inspiring examples of this complex cosmic evolution is the formation of galaxy clusters, particularly one known as El Gordo, whose name, translated from Spanish, means the fat one. This massive galaxy cluster, located about 7 billion light-years from Earth, is one of the largest and most massive structures in the universe. El Gordo boasts an astonishing mass that is approximately 3 quadrillion times that of our Sun, a mind-boggling number that underscores the extraordinary nature of these cosmic entities. The sheer scale of such galaxy clusters provides crucial insights into the intricate processes that govern the universe, processes predominantly driven by the forces of gravity, dark matter, and dark energy. The formation of these colossal galaxy clusters begins deep in the early universe, following the Big Bang with the gravitational collapse of dark matter. Comprising about 85% of the universe's total matter, dark matter is invisible to conventional means of detection, as it does not interact with electromagnetic radiation like regular matter. Instead, dark matter's existence is inferred solely from its gravitational effects. As the universe expanded, dark matter began to clump together under the influence of gravity, forming dense halos that acted as gravitational wells. These dark matter halos attracted regular matter, ordinary matter made up of atoms, leading to the formation of galaxies within these halos. Over billions of years, these smaller halos merged, gradually forming larger aggregates in a process known as hierarchical clustering. Through these repeated mergers and accretions, the massive galaxy clusters we observe today began to take shape. El Gordo, in particular, is believed to have formed through a dramatic collision between two smaller galaxy clusters. This energetic event, which continues to reveal the ongoing processes of cosmic evolution, creates shock waves that propagate across space and are observable in various wavelengths, including X-rays. Strong evidence supporting El Gordo's formation through such a collision comes from detailed observations of its hot intracluster gas. Telescopes like NASA's Chandra X-ray Observatory have detected the X-rays emitted by this gas, revealing a chaotic and turbulent distribution that is characteristic of high-energy collisions. The gas within El Gordo reaches temperatures of tens of millions of degrees and exhibits shock waves and compression features, unmistakable signs of a massive cluster merger in action. Additionally, the distribution of dark matter within El Gordo has been meticulously mapped using a phenomenon known as gravitational lensing. First predicted by Einstein's theory of general relativity, gravitational lensing occurs when massive objects, like galaxy clusters, warp the fabric of spacetime, bending and magnifying the light from more distant objects. These lensing observations of El Gordo have revealed a clumpy and extended distribution of dark matter, providing further evidence for the violent and dynamic nature of the merger that created this colossal cluster. While gravity plays a dominant role in shaping the structure of galaxy clusters, dark energy also exerts a subtle influence. Dark energy, the mysterious force driving the accelerated expansion of the universe, tends to push galaxy clusters apart on the largest scales. However, within individual clusters, gravitational forces overwhelmingly dominate. Still, the effects of dark energy can be seen in how they limit the rate at which clusters can grow, as dark energy accelerates the expansion of the universe itself. In the case of El Gordo, the immense mass and dynamic nature of the cluster offer an invaluable observational anchor for testing cosmological models and theories, providing astronomers with critical insights into the nature of dark matter and dark energy, as well as the complex processes that drive galaxy formation and evolution over cosmic timescales. Furthermore, the study of El Gordo and similar galaxy clusters allows astronomers to refine their understanding of the universe's large-scale structure. These clusters are not just remnants of cosmic history. They serve as laboratories for investigating the fundamental forces that have shaped the universe from its earliest moments to the present day. Through these observations, researchers continue to probe deeper into the origins of the universe's most massive structures, shedding light on the enigmatic forces of dark matter and dark energy that continue to govern the universe's expansion and evolution. An equally fascinating aspect of cosmic evolution is the presence of high-velocity clouds, HVCs, in galactic halos. These clouds of gas exhibit velocities that deviate significantly from the regular rotation of their host galaxies, and their exact origins remain a subject of intense investigation in the field of astrophysics. The origins of these HVCs are multifaceted, with several potential sources and processes contributing to their presence in the galactic halos. They represent yet another intriguing puzzle that scientists are working to unravel, offering valuable clues about the dynamic processes shaping our galaxy and beyond. In exploring the wonders of El Gordo, high-velocity clouds, and other cosmic phenomena, scientists are not only uncovering the intricacies of galaxy formation, but are also deepening our understanding of the very forces that drive the evolution of the universe. Each new discovery brings us one step closer to understanding the true nature of the cosmos and the fundamental forces at play. The origins of high-velocity clouds, HVCs, have long been a subject of intense scientific intrigue, with several prominent theories aiming to uncover their mysterious nature. One leading theory proposes that HVCs originate from the galactic fountain mechanism, a continuous process within a galaxy's disk where ongoing star formation and powerful supernova explosions generate intense stellar winds and shockwaves. These forces propel gas into the galactic halo, an expansive region surrounding the galaxy. Over time, the gas cools and loses energy, eventually falling back toward the galaxy's disk. Sometimes this gas accelerates to astonishing velocities as it cycles between the disk and the halo. This constant movement of gas plays a crucial role in regulating star formation and redistributing chemical elements across the galaxy. The interaction between the disk and the halo is vital as it helps maintain the dynamic balance of a galaxy, ensuring that resources for new stars remain plentiful and that essential elements, such as oxygen and carbon, are spread throughout. Another possible source of HVCs is the gas secretion from the intergalactic medium, IgM. Galaxies, far from being isolated systems, are in constant interaction with their surrounding environments. The cold gas from the IgM can be pulled into a galaxy's gravitational influence, streaming toward the galactic halo at high velocities. This influx of gas replenishes star-forming material and can contribute significantly to the growth and evolution of the galaxy itself. Such interactions between galaxies and the IgM play an essential role in galaxy evolution, especially in terms of feeding galaxies with new material and expanding their stellar populations. Tidal interactions and galactic mergers are also key factors that might contribute to the formation of HVCs. When galaxies pass close to one another, their gravitational fields distort and can strip away gas from their disks. This flung gas then enters the halo, often at exceedingly high velocities. These mergers are common in galaxy clusters, where galaxies are densely packed and interactions occur more frequently. In such environments, gas stripping and subsequent high-velocity ejections are natural occurrences, adding to the complexity of HVC formation. Moreover, some scientists suggest that HVCs might also be remnants of earlier galactic formation processes. In the early stages of a galaxy's life, gas clouds that failed to form stars may have remained in the galactic halo. These clouds could have maintained high velocities due to the conditions under which they were ejected or collapsed, preserving their rapid movement even as they settled into the galaxy's outer regions. Theories surrounding HVCs are supported by a range of observational evidence, primarily from radio observations of neutral hydrogen. Facilities like the Arecibo Observatory and the Green Bank Telescope have provided valuable data on the spatial distribution, velocity, and physical properties of HVCs. These observations help astronomers piece together the complex interactions between galaxies and their halos, revealing how gas behaves under various conditions. In addition to observational data, simulations and theoretical models are used to replicate the behavior of gas in galactic halos, offering further insights into the processes that govern HVC formation. The study of HVCs is vital, as it provides critical clues to the ongoing processes that shape galaxies. These high-velocity clouds serve as windows into the mechanisms of gas recycling, accretion, and interaction throughout the universe. By studying HVCs, astronomers gain a deeper understanding of galaxy formation, the evolution of star systems, and how elements are distributed across the cosmos over time. As observational technology continues to advance, astronomers hope to unravel the enigmatic origins of these clouds and further understand their roles within galactic ecosystems. Now, picture the universe not as a collection of isolated galaxies, but as an intricate web of interactions and cosmic exchanges. Imagine a smaller galaxy, perhaps a dwarf galaxy, drifting too close to a larger one, such as the Milky Way. The immense gravitational forces of the larger galaxy begin to stretch the dwarf galaxy's stars, pulling them apart like cosmic taffy. This process, known as tidal stripping, effectively tears the stars and gas away from the dwarf galaxy, creating a cosmic stream of stars that orbits the larger galaxy's halo. This is a cosmic dance of attraction and tear, repeated over billions of years. The result is the formation of what we call stellar streams, ghostly trails of stars that tell the tale of the smaller galaxy's past. These stellar streams are particularly captivating because they act as cosmic fossils, retaining the memory of their progenitor galaxy's motion and composition, even after the original galaxy has dissolved into the gravitational embrace of the larger one. Scientists now study these streams not only to uncover the history of galactic cannibalism, but also to gain insights into the distribution of dark matter around galaxies. The stars in these streams carry imprints that reveal the gravitational forces at play, and by analyzing their structure, researchers can map out the invisible, yet incredibly influential presence of dark matter. Using advanced telescopes like the Gaia spacecraft, astronomers are able to trace these faint stellar streams across the vast expanse of space. The data gathered allows them to decode the gravitational forces that shaped these streams and shed light on the hidden architecture of the universe. A single stellar stream could contain as many as 100,000 stars, and over the course of 1 billion years, these stars form a delicate trace that can reveal intricate details about the cosmic forces that shaped their journey. Stellar streams are not only evidence of galactic mergers and interactions, but also offer clues about the broader structure of the universe and the role dark matter plays in shaping galaxies. The study of these cosmic relics and the processes that produce them is an exciting frontier in modern astrophysics. Through continued research and observation, scientists are gradually unraveling the mysteries of the universe's past, one stellar stream and high-velocity cloud at a time. As our understanding deepens, we come ever closer to comprehending the complex forces that have shaped and continue to shape the galaxies we observe today. Dark matter is an elusive and profound enigma, a hidden force shaping the very fabric of our universe, yet remaining beyond the grasp of direct observation. Scientists have spent decades attempting to decipher its nature, but its precise composition still remains shrouded in mystery. While ordinary matter, the kind that makes up stars, planets, and even us, is composed of protons, neutrons, and electrons, dark matter is entirely different. It doesn't interact with light, heat, or any other form of electromagnetic radiation. This lack of interaction means that, to our eyes and instruments, dark matter is completely invisible. However, we know it exists because of its gravitational influence on visible matter, bending light, distorting the structure of galaxies, and revealing itself through the movements and behaviors of the cosmos. The search for dark matter has led scientists down several intriguing paths. One of the most widely discussed candidates for its composition is the weakly interacting massive particle, or WIMP. These hypothetical particles are believed to be about 100 times heavier than a proton, yet they only interact through the weak nuclear force and gravity. This makes WIMPs incredibly difficult to detect, as they barely leave a trace on our instruments. Despite their ghostly nature, WIMPs could be the key to explaining much of the mysterious gravitational effects we observe in the universe. Another fascinating possibility is the existence of axions, extremely light particles that, if they exist, could form a strange and mysterious state of matter known as a Bose-Einstein condensate. In this state, particles behave as if they were a single quantum entity, much like a unified swarm of birds moving together in perfect harmony. Although scientists have yet to detect axions directly, their theoretical existence opens up exciting possibilities for understanding dark matter. Then there are sterile neutrinos, particles that are even more mysterious than ordinary neutrinos. These neutrinos, unlike their more familiar cousins, do not interact via the weak force, which makes them even harder to detect. The potential existence of sterile neutrinos further complicates our understanding of dark matter, suggesting that it may be composed of particles we've yet to detect or even imagine. Despite these various hypotheses, the true identity of dark matter remains one of the greatest unsolved puzzles in modern physics and cosmology. It is as though an invisible hand is at work, subtly guiding the formation of the cosmos, shaping galaxies, and influencing the structures we observe in the universe. This invisible force is not a mere curiosity. It is fundamental to the very existence of galaxies and the universe itself. Without dark matter's gravitational influence, galaxies would fly apart, unable to hold themselves together due to the intense speeds at which they rotate. One of the most striking pieces of evidence for dark matter's existence comes from the phenomenon of gravitational lensing. This occurs when the massive gravitational field of dark matter bends light from distant stars and galaxies, distorting their images as seen from Earth. It's as if dark matter acts as a cosmic magnifying lens, warping the light that passes through it. By studying these distortions, scientists can trace the presence of dark matter and map out its distribution throughout the universe. But how do we study dark matter in a laboratory? The answer lies in experiments designed to detect the rare interactions between dark matter and ordinary matter. Deep underground detectors, isolated from the noise of cosmic rays and other sources of interference, are set up to capture the faintest signals when a dark matter particle might collide with a nucleus of ordinary matter. These collisions, though incredibly rare, would impart a small amount of energy, allowing scientists to infer the presence of dark matter. However, directly detecting dark matter is no easy task. It's akin to trying to see the wind. We don't observe the wind itself. We know it's there by the way it moves the leaves, bends the branches, and changes the landscape around us. Similarly, dark matter reveals itself not through direct observation, but through its influence on the universe around it. It's an invisible force, shaping galaxies, bending light, and guiding the structure of everything we see in the cosmos. The more we learn about it, the more it seems as if dark matter is not just a passive player, but an active architect of the universe, holding the cosmic stage together and influencing every star, planet, and galaxy within its reach. The mysteries of dark matter are far from being solved, but each new discovery brings us one step closer to understanding the invisible framework that underpins our universe. As scientists continue to probe the unknown, they may uncover clues that reveal the true nature of dark matter, perhaps even changing our fundamental understanding of the cosmos itself. Dark matter remains one of the universe's most elusive mysteries. Despite its profound influence on cosmic structures, it avoids detection in ways that continue to baffle scientists. Unlike ordinary matter, which interacts with light and electromagnetic forces, dark matter is invisible to our eyes, rejecting every attempt to be seen by the instruments we rely on, from telescopes to particle detectors. While the light that bounces off particles creates an intricate web of interaction, dark matter remains unaffected, hiding within the vast expanse of space. This invisibility cloak renders it undetectable, making it a true enigma in the search for the universe's deeper truths. The quest to reveal dark matter involves cutting-edge methods and ingenious experimentation. One of the most innovative approaches is designed to detect the rare, faint whispers of dark matter interacting with atomic nuclei. In this approach, deep underground laboratories, such as those housing the large underground xenon Lux detector and its successor Lux Zeppelin, use vast tanks of noble gases like xenon. These tanks are buried deep underground, shielding them from cosmic rays and background noise. The idea is that occasionally, a dark matter particle might interact with an atomic nucleus in the xenon tank, creating a tiny flash of light or a small burst of energy. These delicate signs are captured by highly sensitive detectors, hoping for even the slightest hint of dark matter's presence. Another promising method, though indirect, seeks to uncover evidence of dark matter's annihilation or decay. According to some theories, when two dark matter particles collide, they may annihilate, releasing detectable particles, such as gamma rays. Instruments like the Fermi Gamma Ray Space Telescope are tuned to spot these high-energy signals, which might emanate from regions with large concentrations of dark matter, such as the center of our galaxy. Despite these advanced techniques, the hunt for dark matter remains challenging, akin to searching for a needle in a haystack where the needle does not reflect light. Nevertheless, every discovery brings us one step closer to unlocking the secrets of the universe. The role of dark matter is not confined merely to detection. It is the hidden scaffolding, the invisible framework that shapes the universe itself. Imagine it as a cosmic web stretching across space, guiding the formation and evolution of galaxies. This web, known as the cosmic web, consists of dark matter filaments that weave through the universe, creating intersections or nodes where galaxy clusters tend to form. In the early universe, shortly after the Big Bang, both dark matter and ordinary matter were distributed relatively uniformly. However, slight fluctuations in this distribution grew over time due to the pull of gravity. While ordinary matter interacted with radiation and pressure, dark matter was unaffected by these forces and began to clump together under gravity, forming dense regions known as dark matter halos. These halos provide the gravitational wells that are crucial for gathering ordinary matter, mainly hydrogen and helium gases. As these gases fall into the gravitational pull of the dark matter halos, they cool and condense, eventually giving birth to the first stars and galaxies. Without dark matter, the gravity exerted by ordinary matter alone would have been insufficient to form the large structures we observe in the universe today. This makes dark matter the unseen architect of galaxies, providing the gravitational blueprint around which stars and galaxies could coalesce, paving the way for the complex structures of the universe. Simulations of the universe's evolution that incorporate dark matter have proven invaluable in explaining how galaxies form and cluster within the cosmic web. These simulations reproduce the intricate filamentary structure of the web and the distribution of galaxies with astonishing accuracy, showing how dark matter's hidden hand shapes the cosmos. The more we learn about dark matter, the more it becomes clear. While invisible, it is fundamental to the existence and formation of everything we see in the universe. The search for dark matter is more than just a scientific pursuit. It is the quest to answer one of the universe's deepest questions. How can something so invisible be so instrumental in shaping the cosmos? As we develop more refined techniques and delve deeper into the heart of space, each discovery brings us closer to understanding the unseen force that binds our universe together. One thing is certain, the mystery of dark matter is far from over, and with each experiment, we take another step toward unveiling the grand design of the universe itself. While the mysteries of dark matter and dark energy continue to perplex and astonish scientists, their presence in the universe is undeniable, shaping the very fabric of reality in profound ways. The story of these cosmic phenomena begins with dark matter, a mysterious force that cannot be directly observed but leaves an unmistakable imprint on the universe's structure. For instance, consider the rotation curves of galaxies, plots that chart the rotational speed of stars against their distance from the galactic center. If only the visible matter in galaxies were considered, the stars at the edges should be moving far slower. Yet, they rotate at speeds that cannot be explained by observable matter alone. This anomaly hints at the existence of a vast, invisible halo of dark matter enveloping each galaxy. This hidden mass exerts a gravitational pull, ensuring that the stars remain within the galactic boundaries, preventing them from flying off into the void. Dark matter, though intangible and elusive, reveals its influence on the cosmos, shaping the structure and behavior of galaxies in ways we can feel but cannot yet fully grasp. Dark energy, by contrast, plays a more abstract role in the ongoing evolution of the universe. Imagine the cosmos as a balloon, with galaxies and cosmic structures represented by tiny dots on its surface. As the balloon inflates, the dots move further apart, symbolizing the stretching of space itself. For much of our understanding, gravity was thought to be the force responsible for pulling matter together and governing the expansion of the universe. But everything changed in the late 1990s. Observations of distant supernovae revealed a shocking truth. Not only was the universe expanding, but it was accelerating in its expansion. This discovery turned conventional wisdom on its head. The expansion was not slowing down due to gravitational pull, but speeding up, suggesting the presence of a counteracting force, a repulsive energy pushing galaxies away from each other. This force, dubbed dark energy, seems to oppose gravity itself, causing space to stretch at an ever-increasing rate. Whereas dark matter clumps together due to gravity, dark energy appears to have the opposite effect. It does not pull objects together, but instead drives them apart, contributing to the rapid expansion of the universe. One of the most prominent theories to explain this behavior is the cosmological constant, an idea first proposed by Albert Einstein. In this theory, dark energy is envisioned as a uniform, constant energy density that fills space evenly, exerting a steady force over time that accelerates the universe's expansion. The cosmological constant provides a simple, elegant solution to the mystery of dark energy, offering an additive force that continually drives the universe to expand faster as time progresses. However, not all scientists agree on this interpretation. Another theory posits that dark energy is not a constant, but a dynamic, evolving field known as quintessence. Unlike the fixed nature of the cosmological constant, quintessence would change over time, its energy density fluctuating as the universe ages. This more flexible approach to dark energy allows for the possibility that its influence might vary, offering different predictions about the future of the universe and the ultimate fate of cosmic expansion. Regardless of which theory is correct, both suggest that dark energy plays a central role in the acceleration of the universe's expansion. When we examine the makeup of the universe, we find that dark energy accounts for nearly 70% of the universe's total energy density. This overwhelming influence only grows as the universe continues to expand. While matter becomes increasingly diluted over time, dark energy's density remains constant or nearly constant throughout the vastness of space. This unchanging nature of dark energy ensures that as space itself stretches and new regions of the cosmos are created, more dark energy is introduced into the equation, further accelerating the universe's expansion. In an attempt to unlock the secrets of dark energy, cosmologists and physicists use a variety of observational tools, such as studying the cosmic microwave background radiation, the faint afterglow of the Big Bang, and conducting large-scale surveys of galaxies. These observations provide crucial insights into the history of the universe's expansion and help scientists map out the influence of dark energy over cosmic time. By examining how galaxies have shifted and how space itself has stretched, researchers are piecing together a picture of a universe whose pace of growth is increasingly driven by an unknown force. The central question that remains is whether dark energy will remain constant or if it will evolve in some unpredictable manner. This inquiry is at the heart of modern cosmology, as understanding the nature of dark energy could offer a clearer picture of the universe's future. The current prevailing theory, the cosmological constant, suggests that dark energy is a steady force that will continue to accelerate the expansion of the universe indefinitely. However, if dark energy is indeed a dynamic field like quintessence, then the universe's expansion might behave in ways that defy our current understanding, potentially leading to a dramatic change in the universe's structure over time. The implications of these ideas are enormous. If dark energy is constant, we might be looking at a future in which the universe expands forever, with galaxies continuing to drift apart until they are beyond our reach. On the other hand, if dark energy is evolving, it could lead to a variety of outcomes, perhaps a slowing of the expansion, or even a reversal of the universe's fate, resulting in a cosmic collapse. Whatever the final answer may be, dark energy challenges our understanding of space and time, revealing a cosmos far stranger and more complex than we ever imagined. Understanding dark energy and its role in the evolution of the universe remains one of the most profound and exciting pursuits in modern science. Each new discovery, each new piece of data, brings us closer to unraveling the mysteries of the universe's accelerating expansion. Whether we are looking at distant galaxies, the faint remnants of the Big Bang, or the mathematical models that describe the cosmos, one thing is clear. We are still only scratching the surface of understanding the vast, enigmatic forces that govern the universe. However, the alternative hypothesis presents an equally fascinating perspective. It suggests that dark energy may not be a constant force, but could change over time, shifting its properties as the universe expands. This theory is often referred to as dynamic dark energy, or quintessence. Quintessence imagines dark energy as a field that evolves, unlike the cosmological constant, which remains fixed and unchanging. This concept introduces a variety of possible outcomes for the universe's ultimate fate, depending on how this energy behaves. In quintessence models, the energy density of dark energy could either increase or decrease over time, leading to dramatically different futures. If the energy density rises, it could cause a big rip, an event where galaxies, stars, and even atoms are torn apart due to an accelerated expansion of the universe. On the other hand, if the energy density decreases, the expansion of the universe could slow, eventually halting and possibly reversing into a big crunch where the universe collapses in on itself. The dynamics of quintessence therefore hold profound implications for our understanding of the cosmos, suggesting that the universe's end might not be written in stone, but instead influenced by this mysterious force. To test which model best reflects reality, cosmologists rely on a variety of observational tools. Distant supernovae, fluctuations in the cosmic microwave background, CMB, and the formation of large-scale structures in the universe all provide crucial data to track the expansion history and infer the properties of dark energy. Future missions, such as the James Webb Telescope and the Euclid mission, promise to provide even more precise data, potentially helping to distinguish between a constant cosmological constant and the dynamic nature of quintessence. The question of whether dark energy is constant or evolving is not merely an academic debate. It holds the key to understanding the ultimate of the universe, making it one of the most compelling and urgent mysteries in modern science. Modified gravity theories offer a different approach, questioning our traditional understanding of gravity to account for phenomena linked to dark matter and dark energy. These theories propose that the laws of gravity, as we know them, might need to be revised, especially on cosmic scales. Let's first explore the concept of dark matter. Conventional models, such as general relativity, predict gravitational effects that don't align with observations unless an unseen mass, dark matter, is introduced. Modified Newtonian dynamics, NMOM, proposed by physicist Mordechai Milgrom in the early 1980s, suggests that gravity behaves differently in the outer regions of galaxies. Mon posits that at extremely low accelerations, the laws of gravity deviate from Newton's expectations. This adjustment would explain the faster than expected rotation speeds of stars in galaxy outskirts without invoking the presence of dark matter. While Mond offers an elegant solution to certain galactic behaviors, it falls short when it comes to explaining large-scale cosmic structures such as galaxy clusters, where dark matter seems essential. To address these shortcomings, general relativity has been extended into new frameworks, such as tensor vector scalar gravity, TeVS, and FR gravity. These theories modify Einstein's equations by incorporating additional fields or geometric terms, which may explain the observed phenomena of both dark matter and dark energy without the need for invisible particles. Though promising, these modified gravity theories face significant challenges, including the need for precise fine-tuning to match observations and their occasional inability to predict cosmic behaviors accurately across different scales. When considering dark energy within the context of modified gravity, some theories propose adjustments to the geometry of space-time itself, eliminating the need for an external energy source driving the acceleration of the universe's expansion. One notable framework is the Brans-Dicke theory, which suggests that the strength of gravity can vary across time and space due to the influence of an additional scalar field. Another compelling modification to general relativity is the theory of massive gravity, which proposes that the graviton, the hypothetical particle that mediates the force of gravity, has a small but non-zero mass. This concept challenges the traditional view of gravity as a massless force and opens new possibilities for understanding cosmic acceleration without invoking dark energy as we know it. In the quest to understand the cosmos, the debate between constant and dynamic dark energy, as well as the various modifications to gravity, may eventually reshape our view of the universe. The ongoing exploration of these ideas is not just a theoretical pursuit, but one that could uncover the true nature of the forces that govern the universe's past, present, and future. As our observational tools grow ever more sophisticated, we may find that the universe's most profound mysteries are not beyond our grasp, after all. Dark energy, a mysterious force believed to be driving the accelerating expansion of the universe, has led scientists to theorize that certain forms of mass could produce gravitational forces mimicking this effect. While fascinating, these theories face significant hurdles. primarily reconciling with the well-established principles of general relativity. On one hand, the predictions need to match observational data from our solar system, where general relativity has been tested extensively. On the other hand, they must also scale up to accurately describe phenomena on a cosmological scale. Experiments such as gravitational wave detections by LIGO and Virgo, alongside precise mappings of the cosmic microwave background fluctuations, have become pivotal in refining these models. These observations continue to challenge and refine our understanding of how gravity operates, pushing scientists to revisit and revise their theoretical frameworks. Modified gravity theories, especially those aiming to explain dark energy and dark matter, present a bold direction for unifying our understanding of the universe's most elusive forces. In essence, these models strive to create a new version of gravitational theory, one that could not only explain the universe's expansion, but also unify two of its biggest mysteries, dark matter and dark energy. However, testing these ideas remains a massive challenge. As advancements in astronomical observation and experimental physics continue, they will undoubtedly play a crucial role in determining the viability of these models. The key question is whether these theories can withstand rigorous testing and redefine our understanding of the universe's most enigmatic forces. Galaxy clusters, the universe's largest gravitationally bound structures, have emerged as essential laboratories for testing these theories and uncovering the secrets of dark matter. These clusters, massive aggregations of galaxies, hot gas, and dark matter, provide key observational evidence that dark matter is indeed a fundamental component of the cosmic structure. Their gravitational effects are far more pronounced than what can be explained by visible matter alone. Take, for example, the work of astronomer Fritz Zwicky in the 1930s. Zwicky's study of the Coma cluster revealed that the velocities of individual galaxies within the cluster were far too high to be sustained by the gravitational pull of visible matter alone. To explain this anomaly, Zwicky proposed the existence of a missing mass, a concept now known as dark matter. His groundbreaking work marked the beginning of what would become a major scientific pursuit, the search for dark matter. The evidence for dark matter has only grown since then, with one of the most compelling pieces coming from observations of gravitational lensing. According to Einstein's theory of general relativity, massive objects can warp the fabric of space-time, bending the path of light. Galaxy clusters, with their immense gravitational pull, act as natural lenses, distorting and magnifying the light from galaxies lying behind them. By carefully analyzing these distortions, astronomers can map the mass distribution within these clusters. What they consistently find is that the lensing effect is much stronger than what would be expected based on the visible matter alone. This discrepancy strongly suggests that a vast amount of dark matter is present, unseen yet crucial in shaping the gravitational forces at play. These gravitational anomalies, unexplained by visible matter, form a compelling argument that dark matter is not just a theoretical construct, but a real essential part of the universe's structure. In sum, galaxy clusters serve as vital testing grounds for theories about dark matter, offering multiple lines of evidence that continue to deepen our understanding of the unseen forces that govern the universe. With ongoing advances in both observational techniques and theoretical models, the mysteries of dark matter and dark energy are slowly, yet steadily being unraveled. The universe, in all its grandeur and complexity, remains a place of discovery, one that is far from fully understood, but is becoming ever more captivating as new insights emerge. Dark matter and its profound influence on the cosmos have long been subjects of intense scientific inquiry. One of the most striking clues to its existence comes from the hot gas that permeates galaxy clusters. This gas, heated to millions of degrees Kelvin, emits X-rays, which can be detected by space telescopes like Chandra. Despite the fact that the pressure from this gas should cause it to escape the cluster, observations show that it remains tightly bound within. This retention suggests that an unseen force, which we attribute to dark matter, is providing the extra gravitational pull needed to keep the gas contained. In one of the most remarkable confirmations of dark matter's existence, the Bullet Cluster 1E065756 offers compelling evidence. This cosmic collision between two galaxy clusters has been studied extensively. The Chandra X-ray Observatory captured images showing the hot gas from the two clusters colliding and slowing down. Meanwhile, gravitational lensing maps revealed that the majority of the total mass inferred to be dark matter passed through the collision unaffected. The dark matter essentially separated from the hot gas, reinforcing the idea that dark matter does not interact electromagnetically like ordinary matter. Instead, it behaves in a fundamentally different way, which is a crucial piece of the puzzle. In many galaxy clusters, the gravitational behavior, the influence on light through lensing, and the dynamics of hot gas all converge to form a unified narrative that points directly to dark matter. This invisible component is integral to the shaping of the universe itself. In fact, dark matter plays an essential role in the formation of the cosmic web, an enormous and intricate network of filaments and voids that connects galaxies and galaxy clusters, essentially acting as the structural foundation of the cosmos. To understand how dark matter contributes to this vast framework, consider the early universe. It was once a nearly uniform sea of particles, both dark and ordinary. Tiny fluctuations in density, barely noticeable at first, were amplified by gravity over billions of years. Dark matter began to clump together in regions of higher density, creating what we call dark matter halos. These clumps, which account for about 85% of the total matter in the universe, provided the gravitational seed necessary to pull in ordinary matter like gas and dust, ultimately leading to the formation of stars and galaxies. As these dark matter halos merged and interacted over time, they stretched across space, forming the filaments that would become the cosmic web. Supercomputer simulations have shown this evolution in remarkable detail, illustrating how dark matter's gravitational influence helps to shape the universe's large-scale structure. In these simulations, we see how dark matter draws strands of ordinary matter into dense nodes, where galaxies form and thrive. These nodes are interconnected by dark matter filaments, creating a complex, interconnected network that guides the motion and formation of galaxies. Without dark matter, the universe as we know it would not exist. Ordinary matter would not have had enough gravitational influence to form the sprawling, interconnected structures observed today. Dark matter essentially serves as the universe's skeletal framework, with ordinary matter, the visible matter, like stars and galaxies, acting as the flesh. The cosmic web, in all its grandeur, could not exist without this invisible scaffolding. Empirical evidence from observations of the large-scale structure of the universe supports this role of dark matter. For example, the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang, provides a snapshot of the universe's early density fluctuations. These fluctuations, initially tiny, eventually grew into the cosmic web structures we see today. Models that incorporate dark matter align closely with the observed distributions of galaxies and their large-scale clustering. In conclusion, dark matter is not just a passive player in the universe. It is the architect behind the cosmic web, shaping the very structure of the universe. Dark matter dictates the formation and distribution of galaxies, ensuring the integrity of the cosmic framework. Its influence stretches far beyond what we can directly observe, embedding itself into the fabric of cosmic evolution. At the same time, the nature of dark energy remains one of the most pressing mysteries in cosmology. Dark energy, which constitutes about 70% of the universe's energy density, is thought to drive the accelerated expansion of the cosmos. Its characteristics, whether it remains constant or changes over time, are crucial to understanding the ultimate fate of the universe. If dark energy is a cosmological constant, as suggested by the lambda cold dark matter (LCDM) model, it would continue to drive the universe's expansion indefinitely. In this scenario, galaxies would drift farther apart, stars would burn out, and on an incredibly long time scale, the universe would become a cold, dark, and empty expanse. This scenario is often referred to as the Big Freeze, or heat death, where the universe approaches thermodynamic equilibrium, and energy transformations become increasingly rare. However, if dark energy is not constant but rather a dynamic field, its properties could change over time. This dynamic form of dark energy, known as quintessence, could either increase or decrease in strength. If the density of dark energy increases, it could lead to a phenomenon known as the Big Rip. In this future scenario, the accelerating expansion of the universe would become so extreme that it would overcome all other forces, tearing apart galaxies, stars, planets, and even atomic structures. This catastrophic event could unfold within a timescale of billions of years, depending on how rapidly dark energy's repulsive force escalates. Thus, the future of the universe remains uncertain, and much depends on the elusive properties of dark energy. Will it remain a constant force leading to a slow, cold death of the universe, or will it become increasingly dominant, tearing the cosmos apart in a violent and dramatic end? Only time and further discoveries will tell. In the mysterious realms of cosmology, one of the most mind-bending possibilities revolves around dark energy and its potentially transformative effects on the fate of our universe. If dark energy's density were to decrease, or even more intriguingly, flip from a repulsive force into an attractive one, we could witness the ultimate cosmic collapse. This scenario, known as the Big Crunch, envisions the slowing and halting of the universe's expansion, followed by a dramatic reversal, causing everything to contract back into a singularity-like state. Imagine the universe on the brink of a cosmic implosion, where galaxies, stars, and planets all fall toward a point of infinite density. This cyclical model of the universe proposes a fascinating concept. The universe could bounce back, triggering another Big Bang, and essentially resetting the cosmic clock. Theoretically, this could lead to an endless series of cosmic rebirths and destructive collapses. However, dark energy's true nature remains elusive, and much of its intricacies are still shrouded in mystery. To better understand it, cosmologists rely on an array of observational tools that help decode the properties of this enigmatic force. From the distant supernova surveys to detailed analyses of the cosmic microwave background radiation and vast mappings of large-scale cosmic structures, scientists are slowly piecing together the puzzle of dark energy. Future space missions, like those led by the Hubble Space Telescope and the James Webb Space Telescope, are poised to offer even more precise measurements of dark energy and its influence across cosmic distances and timescales. The discoveries made by these missions will help answer profound questions about the nature of the universe itself. In the grandest sense, dark energy could determine the ultimate fate of the cosmos, whether it will continue expanding forever, tear apart in a violent cosmic rip, or collapse in a cataclysmic Big Crunch. As one of the most perplexing phenomena in modern physics, dark energy's behavior is intricately tied to the destiny of everything that exists. Now, shifting focus to one of the most extreme environments in the universe, the heart of a black hole, specifically its event horizon, let us embark on a journey through one of the most fascinating and perplexing regions of space-time. The event horizon of a black hole marks the boundary beyond which nothing can escape, not even light itself. Once this point is crossed, there is no return. The gravitational pull becomes so intense that it inevitably leads to the black hole's singularity, a point where mass is thought to be infinitely concentrated. Here, the laws of physics, as we understand them, no longer apply in their conventional form. As an object approaches the event horizon, it experiences gravitational forces so intense that they stretch it out in a phenomenon known as spaghettification. Imagine, for example, falling feet first into a black hole. The force pulling on your feet is incredibly stronger than the force pulling on your head, causing your body to elongate into a thin, stretched shape like spaghetti. This drastic warping of the body serves as a striking reminder of the extreme conditions near a black hole. Once past the event horizon, the very fabric of space and time undergoes a radical transformation. According to general relativity, within the event horizon, space-time becomes so distorted that all paths lead inevitably toward the singularity. The concept of space and time, as we know it, is completely twisted. From the perspective of an outside observer, time appears to slow down dramatically for anything falling toward the black hole. As the object nears the event horizon, time appears to freeze entirely. However, from the object's own perspective, it continues its journey inward, completely unaware of the cosmic time dilation. At the center of the black hole lies the singularity, a point where densities become infinite, and the very fabric of space and time breaks down. The laws of physics as we know them cease to function predictably in this environment. Even the most advanced theories in physics, including general relativity and quantum mechanics, falter at the singularity. Current models suggest that all the information about the matter falling into the black hole is compressed into this infinitely small space. But precisely what happens here remains one of the most profound mysteries in modern science. At this extreme, the universe's fundamental rules unravel, and the very nature of existence itself is thrown into question. In sum, dark energy, the Big Crunch, and the enigmatic black hole singularity challenge our understanding of the universe. These phenomena raise more questions than answers, yet they also offer tantalizing glimpses into the vast, uncharted territories of space and time. The quest for knowledge continues, and with every new discovery, we draw closer to uncovering the universe's deepest secrets. In the enigmatic depths of the universe, black holes serve as some of the most fascinating and perplexing objects we have ever encountered. At the heart of these cosmic giants lies a paradox that challenges our understanding of physics, the information paradox. This paradox grapples with the question of how information about matter that falls into a black hole can be reconciled with the principles of quantum mechanics. According to traditional thinking, anything that crosses the event horizon of a black hole should be lost to the universe forever. Yet this raises a monumental issue. If information is truly lost, it would violate one of the core tenets of quantum mechanics, which holds that information can never be destroyed. The conditions within a black hole are so extreme, with overwhelming gravity and profound quantum effects, that they suggest the need for a unified theory of quantum gravity. This theory, still elusive, would bridge the gap between general relativity, which governs large-scale structures like black holes, and quantum mechanics, which explains the behavior of particles at the smallest scales. Scientists are exploring various hypotheses, such as string theory and loop quantum gravity, to unlock the mysteries that lie beyond the event horizon. However, much remains speculative, and the path to a comprehensive theory is still uncertain. Crossing a black hole's event horizon is not just a physical journey, but a metaphysical one, into the unknown. Once something enters this boundary, it is doomed to fall inward toward the singularity, where space and time collapse into one another. Matter is stretched, shredded, and ultimately annihilated, while the very laws of physics as we know them may no longer apply. The questions posed by these cosmic gateways continue to stretch the limits of our understanding, leaving scientists to wonder if one day we will develop a theory that can reveal their deepest secrets. At the core of most, if not all, large galaxies lies a supermassive black hole, a force of nature so immense that it exerts a profound influence on the galaxy's entire evolution. These supermassive objects can contain masses millions or even billions of times greater than that of our Sun. Despite their darkness, black holes play both a creative and destructive role in the galactic ecosystems they inhabit. Their gravitational pull shapes the galaxy's structure, dynamics, and star formation processes, making them essential architects of the cosmic landscape. One of the most significant phases in a supermassive black hole's life cycle is the active galactic nucleus, AGN phase. During this time, the black hole actively accretes vast amounts of dust from its surroundings, funneling this material into a swirling accretion disk. As this matter spirals inward, it is heated to unimaginable temperatures, emitting a flood of energy across the electromagnetic spectrum from visible light to X-rays. In some cases, the energy released is so intense that it produces powerful jets of particles, which can stretch for millions of light years into the cosmos. These jets, along with the intense radiation from the accretion disk, are among the most brilliant phenomena observed in the universe. The energy emitted by an active galactic nucleus can have sweeping consequences for the host galaxy. The high-energy radiation and powerful jets of particles can heat and expel surrounding gas, effectively quenching star formation. This feedback mechanism plays a critical role in regulating the galaxy's growth by controlling the supply of gas that would otherwise condense into new stars. Observations across a variety of wavelengths, from radio waves to X-rays, illustrate these interactions in vivid detail. For example, in the case of the galaxy Cygnus A, its radio jets extend hundreds of thousands of light years, injecting energy into the surrounding interstellar medium and even the intergalactic medium. This energy can trigger or inhibit star formation in distant regions by compressing gas clouds or tearing them apart. Supermassive black holes are also integral to the morphology and dynamics of their galaxies. Studies have shown a strong correlation between the mass of the central black hole and the properties of the galaxy's bulge, particularly the velocity dispersion of the stars within it. This relationship, known as the M-sigma relation, suggests that the growth of supermassive black holes and their host galaxies are intimately linked, evolving together in a cosmic dance. As black holes grow, they may directly influence the development of the galaxies that house them. When galaxies collide, the influence of supermassive black holes becomes even more dramatic. During these cosmic mergers, the black holes at the centers of the colliding galaxies can form binary systems, orbiting each other before ultimately merging. These cataclysmic events send ripples through space-time itself, creating gravitational waves. Ripples in the fabric of the universe predicted by Einstein and later detected by observatories such as LIGO and Virgo. The merger of these supermassive objects is not just a violent release of energy, but also triggers significant outflows of gas, which can redistribute mass within the galaxy and influence the rate of star formation. This process can reshape the galactic landscape, contributing to the evolution of the galaxy over billions of years. Far from being passive entities, supermassive black holes are dynamic forces, shaping their galactic neighborhoods in profound and unexpected ways. Through mechanisms like AGN feedback, jet emissions, and their immense gravitational influence, black holes regulate star formation, influence galactic morphology, and can contribute to the overall evolutionary trajectory of their host galaxies. These cosmic giants act as architects of the universe, whose impacts echo across time and space, reshaping the galaxies that they inhabit and the cosmos as a whole. Quasi-periodic oscillations, QPOs, in black hole emissions are among the most fascinating and enigmatic phenomena observed in the universe. These oscillations, which appear as regular yet variable periods in the light curves of X-ray binaries, provide invaluable insight into the complex and dynamic environment surrounding black holes. In such systems, a stellar mass black hole pulls matter from a companion star, generating intense gravitational forces and radiation. As this material spirals inward toward the black hole, QPOs emerge, offering clues about the nature of the accretion process and the inner workings of these extreme objects. The term quasi-periodic refers to the seemingly regular yet subtly changing intervals of the oscillations. These fluctuations are not exactly constant, but still display a repetitive pattern. This makes QPOs a unique and critical feature in understanding the physics of black holes. Various mechanisms have been proposed to explain these oscillations, each addressing different aspects of the accretion process, the dynamics of the inner accretion disk, and the relativistic effects near the event horizon. One of the leading hypotheses suggests that QPOs are generated in the innermost regions of the accretion disk, the place where matter is closest to the black hole and experiences the most extreme forces. In this highly energetic region, the gas swirling around the black hole is subjected to intense gravitational and magnetic forces that can cause the material to behave in fascinating ways. A key player in this process could be the lens-Thirring precession, a relativistic effect predicted by Einstein's general theory of relativity. This effect occurs as matter orbits the black hole, causing the orbit itself to precess due to the drag exerted by the rotating black hole's spacetime. Essentially, as the material moves, the black hole's spin causes the plane of the orbit to slowly shift, an effect known as frame dragging. This precession could modulate the X-ray signals emitted by the accreting matter, resulting in the QPOs that we observe. Another possibility is the idea of resonant oscillations within the accretion disk itself. Just as a guitar string can resonate at certain frequencies, parts of the disk might hit specific resonant frequencies, leading to coherent oscillatory modes. These resonant frequencies could occur in regions near the inner edge of the disk, where the gravitational forces of the black hole are strongest. In this area, the gas in the disk experiences the most significant interactions with the black hole's immense gravity, and any disturbances here could create periodic oscillations. Furthermore, magnetic fields threading through the accretion disk may also contribute to these oscillations. These fields can give rise to magnetohydrodynamic MHD waves, which can induce periodic modulations in the emitted X-rays. Yet another hypothesis revolves around instabilities in the accretion flow itself. The accreting material is not uniform. It fluctuates in density and temperature as it spirals inward. These variations can lead to regions of unstable energy release, causing periodic increases and decreases in the X-ray output. This phenomenon can produce QPOs through density waves or thermal instabilities that travel through the accretion disk. As these waves pass through regions where energy release is most intense, they can temporarily enhance or dim the X-ray emission, creating the characteristic oscillations we observe. Astronomers have gathered a wealth of observational data from X-ray telescopes like NASA's Rossi X-ray Timing Explorer XTE and ESA's XMM Newton. These observatories have provided critical insights into QPOs by allowing scientists to study the X-ray emissions from black holes with unprecedented precision. The data shows that QPOs come in two primary varieties: low-frequency QPOs, which occur at frequencies ranging from fractions of a hertz to a few hertz, and high-frequency QPOs, which can reach several hundred hertz. The coexistence of these two distinct oscillatory modes complicates the picture, suggesting that multiple mechanisms may be simultaneously at work in the black hole environment. The interaction between these different modes of oscillation offers a deeper understanding of the intricate processes that govern black hole accretion. Ultimately, the study of QPOs is crucial for advancing our knowledge of black holes. As astronomers continue to gather more data and refine our theoretical understanding, these oscillations will likely provide a key to unlocking the mysteries of the universe's most mysterious and powerful objects. With every observation, we edge closer to understanding the complex and dynamic behaviors occurring in the shadow of a black hole, offering an unparalleled glimpse into the heart of one of the most extreme environments known to science. While the exact cause of QPOS remains a mystery, it is a topic of intense ongoing research. The complex interaction between orbital mechanics, relativistic effects, magnetic fields, and instabilities within the accretion process presents a rich and multifaceted landscape. Every new observation sheds light on this cosmic puzzle, offering deeper insights into the environments surrounding black holes and the extreme physics that govern these enigmatic regions of spacetime. Among the most fascinating phenomena in this realm are binary black hole systems, which offer an extraordinary window into the dynamics of gravitational interaction and the intricate cosmic dance between two colossal entities. The evolution of binary black hole systems is a process that unfolds over multiple distinct phases, each governed by the intricate laws of general relativity and astrophysics. The journey of these systems begins with their formation, which can occur through a variety of mechanisms. One of the most intriguing pathways involves the dynamical interactions within densely packed stellar environments, such as globular clusters or the cores of galaxies. In these crowded and chaotic regions, stars and compact remnants like black holes can collide and form close binary pairs. Alternatively, binary black holes can also arise from the evolution of massive binary star systems. In this scenario, each star in the binary pair undergoes a supernova explosion, leaving behind two black holes that remain gravitationally bound. Once formed, these binary black holes embark on a fascinating journey of gravitational interaction. Initially, they are separated by vast distances, but over time they begin to spiral inward. This slow but inexorable process is driven primarily by the emission of gravitational waves, ripples in the fabric of space-time that carry away energy and angular momentum from the system. In the early stages, this process is incredibly slow, lasting millions or even billions of years, depending on the initial separation and the masses of the black holes involved. As the black holes continue to lose energy through gravitational wave emission, they enter a more dynamic phase known as the in-spiral phase. During this phase, the gravitational waves intensify, causing the black holes to spiral toward each other more quickly. This phase can last for billions of years, but as they approach the final moments of their cosmic dance, the speed of their inward spiral accelerates dramatically. This rapid progression brings the black holes closer to the point of no return, the merger. The next phase, the merger phase, is one of the most dramatic and intense events in the universe. As the black holes reach their critical separation, the gravitational wave emission spikes, reaching unprecedented levels. These waves are so powerful that they can be detected by instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo, even if the black hole merger occurs hundreds of millions of light years away. The final moments of the merger are characterized by a dramatic cataclysmic release of energy, culminating in the formation of a single, more massive black hole. The gravitational waves produced during this final stage serve as a cosmic signature, confirming the existence of binary black hole systems and validating the predictions of general relativity, particularly in the strong field regime. Following the merger, the newly formed black hole enters a phase known as ringdown. In this stage, the black hole is in an excited, non-spherical state, and it begins to settle down, emitting gravitational waves as it relaxes into a stable, nearly spherical shape. This process can be likened to a cosmic bell, ringing out the residual energy of the system. As the black hole reaches equilibrium, the gravitational waves emitted during this phase carry distinct signatures that provide crucial information about the masses, spins, and dynamics of the merging black holes. The event known as G50914, detected by LIGO in 2015, marked the first direct observation of a binary black hole merger. This landmark discovery not only confirmed the existence of these cosmic systems, but also ushered in a new era of gravitational wave astronomy, opening up an entirely new way of observing and understanding the universe. In addition to the primary dynamics of binary black hole mergers, these systems can be influenced by various astrophysical factors. For example, interactions with surrounding matter or third bodies, such as another star or black hole, can alter the system's evolution. These interactions can increase or decrease the eccentricity of the binary's orbit, potentially affecting the merger timeline. From their formation to their final explosive merger, binary black hole systems provide a remarkable glimpse into the universe's extremes. They reveal the complex interplay of gravitational forces and the behavior of matter in the most intense environments imaginable, offering profound insights into fundamental physics and the life cycles of black holes. Shifting focus to active galactic nuclei, the powerful jets emanating from these regions are driven by supermassive black holes, typically millions to billions of times the mass of our Sun. These colossal black holes reside at the centers of galaxies, surrounded by a swirling accretion disk composed of gas, dust, and stellar debris. Within this disk, particles move at speeds that approach a significant fraction of the speed of light. Extreme frictional forces heat the material to millions of degrees, creating an environment of immense energy and tension. Magnetic fields generated by the rotating accretion disk become twisted and coiled, storing vast amounts of energy. These magnetic fields play a pivotal role in the formation of jets. They funnel particles along the black hole's spin axis, accelerating them to near light speed. This process creates columnated jets of matter that shoot out from the poles of the black hole, perpendicular to the accretion disk. These jets are not only a testament to the power of black holes, but also represent one of the most energetic and fascinating phenomena in the universe. In the vast expanse of space, some of the most extraordinary objects are the relativistic jets, which can stretch across thousands, even millions of light years. These jets shine brilliantly across a spectrum of wavelengths, from radio to optical and X-ray. The sheer energy of these cosmic phenomena has the power to reshape entire galactic ecosystems. They influence star formation and play a crucial role in the distribution of gas and dust, reaching far beyond a galaxy's center. The jets, often referred to as cosmic geysers, are not just fascinating, but are also crucial to our understanding of the universe's intricate workings. Intermediate mass black holes, generally defined as having masses between 100 and 100,000 times that of our Sun, present a major puzzle in modern astrophysics. Their formation bridges the gap between stellar mass black holes, which are remnants of massive stars, and the supermassive black holes that dominate the centers of galaxies. One compelling theory suggests that these intermediate mass black holes might form through the repeated mergers of smaller black holes and neutron stars. Picture a densely packed star cluster where interactions are a frequent occurrence. In this gravitational dance, stars collide and merge, gradually building up mass over time. Alternatively, these black holes might form from the collapse of primordial gas clouds, which were significantly free of heavier elements and avoided the usual fragmentation process that leads to star formation. Instead, these clouds might have collapsed directly into black holes. Another possibility is the formation of these intermediate mass black holes within young, massive star clusters, where runaway collisions of massive stars might form a very large star that eventually collapses into a black hole. Although evidence for their existence is scarce, recent gravitational wave detections and observations of ultraluminous X-ray sources suggest that we may be getting closer to detecting these elusive cosmic giants. As a black hole nears the end of its life, it transforms into a cosmic spectacle governed by the laws of extreme physics. This dramatic process is driven by Hawking radiation, a groundbreaking theory proposed by physicist Stephen Hawking in the 1970s. According to Hawking's prediction, black holes are not entirely black. Instead, they emit faint radiation due to quantum effects occurring near their event horizons. Over incredibly long timescales, much longer than the current age of the universe, this radiation causes the black hole to lose mass. As the mass diminishes, the black hole's temperature rises, leading to the emission of more radiation. In the final stages, this process accelerates rapidly. As the black hole shrinks to an almost infinitesimal size, it could release a colossal burst of energy, potentially equivalent to the explosion of millions of hydrogen bombs. This termination flash marks the black hole's ultimate demise, dispersing its remaining mass and energy into space and leaving an empty void where once one of the universe's most enigmatic objects existed. This end, both spectacular and mysterious, continues to intrigue scientists, pushing the boundaries of our understanding of quantum mechanics, general relativity, and the very fabric of space and time. Primordial and stellar black holes are two distinct types of black holes, each fascinating in its own right. Primordial black holes are theorized to have formed just moments after the Big Bang, in the high-energy environments of the early universe. These black holes could have originated from density fluctuations in the universe's primordial soup, regions where the concentration of mass was sufficient to collapse directly into black holes, bypassing the need for star formation and death. Their masses could range from just a fraction of a gram to many times the mass of the Sun. Stellar black holes, however, are born from the life cycles of massive stars. When a star with a mass greater than about 8 times that of our Sun exhausts its nuclear fuel, its core collapses under its own gravity, triggering a supernova explosion. The outer layers are blown away, while the core compresses into a black hole, typically with a mass ranging from a few to several dozen times that of the Sun. These stellar remnants are usually found in galaxies, often as part of binary systems where they interact with companion stars, emitting X-rays that are detectable by astronomers. While stellar black holes have been well documented through observational techniques like X-ray astronomy and gravitational wave detections, primordial black holes remain a mystery. There is still no direct evidence of their existence, but their potential significance is immense. If they do exist, primordial black holes could account for some of the universe's most enigmatic phenomena, such as dark matter, and might even be the seeds from which supermassive black holes eventually grow. The search for these primordial giants is ongoing, and their discovery could revolutionize our understanding of the universe's formation and evolution. At the centers of galaxies, frame dragging unfolds as one of the most captivating consequences of Albert Einstein's theory of general relativity. This effect, first conceptualized by Einstein, becomes particularly intense in the vicinity of rotating black holes, described in detail by the Kerr solution to Einstein's equations. When a black hole spins, it does not merely exert its immense gravitational force to pull in material, it also drags the very fabric of space-time itself, causing a twisting motion that profoundly alters the behavior of objects near it. In essence, this phenomenon, known as the lens-Thirring effect, reveals that any object near a rotating black hole is not only affected by gravity pulling it inward, but is also subject to the twisting of space-time, causing a kind of spiraling motion. The degree of this twisting is influenced by the black hole's mass and the speed at which it rotates. Near the event horizon, this effect becomes so powerful that it can significantly change the paths of particles and light, compelling them to orbit in the direction of the black hole's spin. Imagine the environment around a rotating black hole. Even a space station in orbit would be caught in the motion of space-time itself, rotating along with it. Frame dragging has important implications for understanding the dynamics of black holes and their surrounding regions. While this effect has been observed on Earth through experiments such as the Gravity Probe B, where Earth's comparatively weak gravitational field and slow rotation yield much subtler results, the extreme conditions near a rotating black hole intensify frame dragging to the point where it greatly affects the orbits of matter in accretion disks and even the trajectories of relativistic jets. This effect not only helps us understand how black holes grow and interact with their surroundings, but it also provides a crucial testing ground for theories of gravity. By studying the way space-time behaves near these exotic objects, astronomers gain valuable insights into the intricate dance of matter and energy in the universe, deepening our understanding of some of the most extreme and fascinating phenomena that exist. Meanwhile, gravitational lensing presents a mesmerizing phenomenon of its own, where massive objects like black holes bend space-time to such an extent that they distort the paths of light rays passing near them. This dramatic bending of light is a direct consequence of Einstein's theory of general relativity, which tells us that mass curves space-time, causing light traveling along the straightest possible path in curved space to bend around massive objects. To visualize this, imagine space-time as a stretchable sheet, with a black hole being a heavy ball placed on that sheet. The ball creates a deep well in space-time, and when light passes nearby, its path is bent, much like a car navigating a curvy road. For black holes whose gravitational fields are extraordinarily strong, this bending can be extreme. Light from distant stars or galaxies passing close to a black hole can be deflected so sharply that it produces multiple images of the same astronomical object. In some cases, this bending is so intense that it forms an Einstein ring, where the background object appears as a ring of light encircling the black hole. The strength of this lensing effect depends on factors like the mass of the black hole and the alignment between the black hole, the light source, and the observer. While gravitational lensing produces striking visual phenomena, it also serves as a powerful tool in cosmology and astrophysics. By studying these distorted light patterns, scientists can infer important properties of black holes, such as their mass and, potentially, their spin. Furthermore, lensing events provide a unique opportunity to peer deeper into the universe, magnifying distant galaxies and offering clues about the distribution of dark matter. This awe-inspiring manipulation of light not only highlights the profound interaction between black holes and their cosmic surroundings, but also reveals the invisible framework of the universe itself. Then there are fast radio bursts, FRBs, mysterious and enigmatic phenomena that continue to puzzle astronomers. These incredibly brief but extraordinarily powerful bursts of radio waves last only a few milliseconds, yet during their brief existence, they can release as much energy as the sun does in nearly a century. Despite their fleeting nature, FRBs have become a major focus of research, with numerous theories proposed to explain their origin. The exact cause remains uncertain, but these bursts present an intriguing area of study, offering new insights into the violent and exotic processes occurring in the universe. In the vast expanse of the universe, an enigmatic phenomenon has been puzzling astronomers and scientists for years: fast radio bursts, FRBs. One of the leading hypotheses behind these mysterious bursts of radio waves points to a type of neutron star known as a magnetar. Magnetars, though rare, represent a unique subset of neutron stars, distinguished by their extraordinarily powerful magnetic fields. These magnetic fields can be thousands of times stronger than those of typical neutron stars, so strong, in fact, that they are billions of times more intense than Earth's own magnetic field. These immense magnetic fields are thought to result from the violent and extreme conditions that exist during the formation of the neutron star. When a star with more than 8 times the mass of our Sun exhausts its nuclear fuel, it undergoes a catastrophic supernova explosion, leaving behind a dense core composed almost entirely of neutrons. In the case of magnetars, the remaining core rotates rapidly, sometimes spinning in milliseconds. This rapid rotation, combined with powerful convection currents and fluid dynamics, creates an environment where the magnetic fields of the star are twisted and stretched through a process known as the dynamo mechanism. This mechanism is akin to the one that generates Earth's magnetic field, but on a vastly larger and more energetic scale. However, the story doesn't end there. The rapid rotation and internal fluid motions of the neutron star amplify the strength of these magnetic fields exponentially. These twisting and stretching magnetic lines of force can lead to catastrophic events within the star itself, known as starquakes. These are sudden shifts in the star's crust that can release intense bursts of radiation across the electromagnetic spectrum. The energy produced by such events could potentially be responsible for generating the powerful radio waves that are detected as fast radio bursts. Another intriguing theory proposes that FRBs could originate from catastrophic events within binary star systems. For example, the merging of two neutron stars, or even a neutron star colliding with a black hole, could create shock waves and intense magnetic interactions. These interactions might be powerful enough to generate the bursts of radio waves that we observe as FRBs. While these theories are compelling, there is yet another possibility that sparks even more fascination: the idea that FRBs could result from exotic objects, such as primordial black holes, or, more controversially, advanced extraterrestrial technology. The variability of FRBs adds another layer of complexity to this mystery. While some FRBs are observed repeating in bursts, they do so at irregular intervals, defying any clear pattern or rhythm. On the other hand, other FRBs appear to be one-time events, occurring just once and never again. This diversity of behavior implies that there could be multiple origins or mechanisms responsible for generating these elusive radio bursts, making the task of unraveling their secrets even more challenging. As scientists continue their quest to understand the origins of FRBs, they turn to advanced technologies and sophisticated observatories. The CHIME radio telescope in Canada and the Parkes Observatory in Australia are two such tools that have been instrumental in capturing more FRBs and studying their intricate characteristics. With each new observation, scientists inch closer to solving this cosmic puzzle, but the true nature of these mysterious signals remains just out of reach. Magnetars, with their immense magnetic fields and violent processes, remain a captivating and vital part of the story. These incredibly rare objects, formed in the aftermath of stellar explosions, may hold the key to understanding the origin of fast radio bursts and perhaps unlocking even deeper cosmic mysteries. In the vast expanse of the universe, one phenomenon stands out for its incredible power and mystery: the magnetar. These cosmic giants, possessing ultra-strong magnetic fields, have the ability to influence the very fabric of space-time. Their magnetic fields can alter the physics on the surface and atmosphere of neutron stars, triggering extraordinary events like massive bursts and flares. Such phenomena captivate astronomers who view magnetars as natural laboratories, offering a rare glimpse into the extreme states of matter and the fundamental forces of nature. The power and enigma of magnetars continue to stir fascination, deepening our understanding of the universe's most extreme conditions. One of the most mind-boggling and energetic occurrences in the cosmos are gamma-ray bursts, GRBs. These bursts of gamma radiation are so intense that they can outshine entire galaxies for brief moments. There are two primary types, short-duration and long-duration bursts. Each has distinct origins, giving scientists clues about the cataclysmic processes behind them. Long-duration gamma-ray bursts, lasting anywhere from a few seconds to several minutes, are often tied to the death of massive stars. When a star significantly more massive than our Sun runs out of nuclear fuel, it can no longer support itself against the force of gravity. The core implodes, potentially forming a neutron star or even a black hole, while the outer layers of the star are violently ejected in a supernova explosion. In some extreme cases, the collapse of the star creates highly focused jets of gamma rays that blast through the star's outer layers and shoot into space at nearly the speed of light. If one of these jets is pointed directly at Earth, it appears as a gamma ray burst. These events are commonly referred to as collapses, and they typically occur in active star-forming regions of galaxies. Their immense energy output, though brief, makes them the most luminous phenomena in the universe. As a result, GRBs play a significant role in the evolution of galaxies, offering insights into the birth and death cycles of stars. Short-duration gamma-ray bursts, however, have a different origin. These bursts, lasting less than 2 seconds, are believed to result from the violent collisions of compact objects, such as neutron stars or a neutron star and a black hole. As these incredibly dense objects spiral inward toward each other, driven by the emission of gravitational waves, they eventually collide, releasing vast amounts of energy in the form of gamma rays and gravitational waves. This catastrophic collision can lead to the formation of a rapidly spinning black hole or a highly magnetized neutron star, known as a magnetar, surrounded by an irradiated field of high-energy debris. Both types of GRBs send intense bursts of gamma radiation across the universe, temporarily becoming the brightest sources of electromagnetic radiation observable. Thanks to groundbreaking missions like NASA's SWIFT and Fermi satellites, astronomers can now study these bursts in extraordinary detail. By capturing the afterglow of GRBs in different wavelengths, scientists can pinpoint their host galaxies, providing invaluable data on the events that shape the universe. The ability to study these bursts not only enhances our understanding of stellar deaths, but also illuminates the violent processes that govern the evolution of galaxies. In the realm of binary star systems, the interaction between two stars orbiting a common center of mass reveals another layer of cosmic complexity. These systems, which can range from relatively simple to incredibly complex, go through fascinating evolutionary processes over millions, even billions of years. The evolution of such systems is highly dependent on the masses of the stars and their initial distances from one another, with each factor influencing the outcome in profound ways. Typically, both stars in a binary system form from the same cloud of gas and dust, entering their main sequence phase where they fuse hydrogen into helium. However, the more massive star evolves more quickly, eventually running out of hydrogen and expanding into a red giant. If the stars are close enough to one another, this process can lead to significant changes in their life cycles, setting the stage for potential stellar mergers or other dramatic events that can reshape the system's dynamics. The study of binary star systems offers valuable insights into the life cycles of stars, helping us piece together the intricate web of events that drive the evolution of the cosmos. The universe, in all its complexity, continues to unveil its mysteries, offering astronomers and astrophysicists a never-ending quest to understand the most enigmatic forces that govern our existence. From the unimaginable power of magnetars to the dramatic eruptions of gamma-ray bursts and the intricate interactions in binary star systems, we are only scratching the surface of what lies beyond the stars. These celestial phenomena offer a glimpse into the fundamental forces at work, reminding us of the awe-inspiring and often unfathomable nature of the cosmos. In the vast expanse of the universe, the dynamic interactions between stars can lead to phenomena that challenge our understanding of stellar evolution. One such interaction involves mass transfer, where a red giant loses material to its companion star. This seemingly simple exchange of material can have profound consequences on both stars, each embarking on a unique evolutionary journey. When a red giant sheds its outer layers, its companion star may gain enough mass to significantly alter its own path. This could lead to a dramatic increase in the companion's luminosity and size, propelling it toward a much more massive and luminous state. Alternatively, the red giant itself could undergo a transformation, losing enough mass to expose its core, eventually becoming a white dwarf. In some cases, the transfer process can escalate, triggering a dramatic event, such as a nova or even a type Ia supernova. This occurs if the receiving star happens to be a white dwarf, further complicating the intricate ballet of stellar evolution. One of the most captivating results of such mass transfer is the formation of X-ray binaries. In this scenario, the companion star might evolve into a neutron star or even a black hole, where the stellar remnants begin accreting matter from the red giant. As they do, they emit intense X-rays and other forms of high-energy radiation, creating a dazzling spectacle. Over time, gravitational interactions within the system can lead to tidal locking, where the stars' rotational periods synchronize, always showing the same face to each other. On much longer timescales, gravitational radiation can cause the binary orbit to decay, bringing the stars closer together, possibly culminating in a powerful merger. If the system consists of compact objects like white dwarfs, neutron stars, or black holes, the eventual merger could trigger extraordinary events, such as gravitational waves or gamma-ray bursts, illuminating the night sky in ways that are both awe-inspiring and unsettling. These diverse paths, stretching from the formation of X-ray binaries to the cataclysmic merging of stellar remnants, reveal the intricate nature of stellar evolution. By observing and modeling these systems, astronomers gain a deeper understanding of the cosmic processes that drive the life cycles of stars. As we peer into these systems, we witness a stunning interplay of forces that are not only central to the evolution of stars, but also crucial to our understanding of the universe itself. Meanwhile, far from the violent transformations of binary systems, Tabby's star, officially known as KICE 8462852, presents another captivating mystery. This star's light fluctuates in unusual and seemingly unpredictable ways, with brightness dips as deep as 20%, far beyond what can be explained by the typical transit of an orbiting planet. First discovered through data from the Kepler Space Telescope, these irregular dips have sparked a range of theories, each more intriguing than the last. One leading hypothesis suggests that a swarm of cometary fragments, possibly remnants of a shattered comet, could be orbiting the star. As these fragments move in and out of our line of sight, they could block the star's light in complex, unpredictable patterns leading to the observed dips. Another possibility is that the dips in brightness are caused by an uneven distribution of dust or debris in the star's circumstellar disk. This disk might have formed as a result of an interaction between the star and another object, or could be the product of a disintegrating celestial body. Despite the lack of strong infrared evidence to support this theory, it remains a contender. Intriguingly, another theory posits that the fluctuations could be the result of intrinsic stellar activity, like massive star spots or magnetic storms. However, the erratic nature of the brightness variations suggests this is unlikely the full explanation. Perhaps the most exotic theory, which initially captured the public's imagination, is the idea that an advanced civilization could have built a massive structure around the star, such as a Dyson swarm. While this theory generated considerable media attention, subsequent investigations, such as searches for radio signals or infrared emissions, have found no evidence of such technological activity. Regardless of the explanation, Tabby's star continues to be a focal point of research, pushing the boundaries of our knowledge about stellar behavior and the strange phenomena that can arise in the cosmos. In the dense environments of globular star clusters, another puzzling phenomenon occurs: blue stragglers. These stars stand out for being unusually young and hot compared to the other stars in the cluster, which should all have roughly the same age since they were formed together. Their presence in these older, red, giant-dominated clusters has baffled astronomers for decades. How do these stars manage to appear so youthful, and what processes allow them to remain so hot and blue? One leading explanation suggests that blue stragglers are the product of stellar collisions. Within the crowded confines of a globular cluster, stars often come into close contact, sometimes colliding and merging. The resulting star is more massive and behaves as if it were younger, burning hotter and bluer than its neighbors. Another plausible explanation is that blue stragglers form through mass transfer in binary systems. In such systems, one star evolves more quickly, becoming a red giant and shedding its outer layers. If the stars are close enough, the material from the red giant can be transferred to the companion star, significantly increasing its mass and extending its lifespan. This process can transform the recipient star into a blue straggler, rejuvenating it in the process. Both of these mechanisms likely contribute to the population of blue stragglers observed in various star clusters. As astronomers refine their observational tools, employing high-resolution imaging and advanced spectroscopy, they continue to uncover the detailed processes behind the formation of these intriguing stars. With each new study, our understanding of stellar evolution grows, shedding light on the complex and often unpredictable paths that stars can take over the course of their lives. Through these various phenomena, From the mass transfer of binary systems to the mysterious behavior of Tabby's star and the enigma of blue stragglers, astronomy continues to unveil the intricate and dynamic processes that shape the universe. The more we observe, the clearer it becomes that the cosmos is far more complex than we could have ever imagined, with each discovery leading to new questions, new mysteries, and ultimately, a deeper understanding of the forces that govern the life cycle of stars. In the vastness of space, astronomers continue to probe the intricate dynamics of stellar evolution, particularly the formation of unique stellar phenomena like blue stragglers. These mysterious stars offer rare insight into the often hidden lives of star clusters. They reveal the crucial role of gravitational interactions and the evolution of stars in shaping the characteristics of ancient stellar populations. Blue stragglers, with their unconventional behaviors, serve as a living laboratory for studying the intricate processes that govern the lives of stars and the gravitational ballet that drives star cluster evolution. One star that stands out in this cosmic dance is Pilsky star, also known as HD 165. This enigmatic star, located in the Centaurus constellation, has baffled astronomers ever since its discovery in the 1960s. Its irregular pulsations, which defy the patterns typically observed in other stars, have become a focal point of scientific study. Pilsky star belongs to a class of stars called rapidly oscillating AP stars. These stars are not only chemically peculiar, but also possess strongly magnetic fields, further complicating their already mysterious behavior. Unlike regular pulsating stars, where the expansion and contraction of the star occur symmetrically, Pilsky star's pulsations are non-radial. This means that different parts of the star's surface and interior vibrate asymmetrically, creating a more complex and fascinating pattern of oscillations. The pulsations in Pilsky star are believed to arise from slow, non-radial oscillations influenced by its intense magnetic field. These oscillations disrupt the typical symmetry found in other stars, causing waves to propagate in complex patterns throughout the star's interior. In a typical star, radial pulsations would cause the entire star to expand and contract uniformly, like a balloon being inflated and deflated. However, in non-radial pulsations, the vibrations occur in a more chaotic and unpredictable manner, affecting various parts of the star unevenly. Adding to Pilsky star's uniqueness is its peculiar chemical composition. The star's spectrum reveals an unusual abundance of rare earth elements such as strontium, europium, and neodymium, along with the presence of even rarer elements like uranium and plutonium. This strange cocktail of elements alters the star's opacity and internal structure, potentially affecting how the pulsation waves travel through the star. The combination of these rare elements and the star's enhanced magnetic activity contributes to the star's highly complex pulsations. These elements are ionized in unusual ways due to the strong magnetic fields, influencing how sound waves and other types of acoustic waves propagate through the star. The interaction between the magnetic field and these elements distorts the pulsation modes, leading to complex multi-mode oscillations that are difficult to understand, but rich in information about the star's internal structure. Through precise spectroscopic measurements and magnetic field mapping, astronomers continue to unlock deeper insights into these unusual oscillations, shedding light on the life cycles of chemically peculiar stars and the powerful interplay between magnetism and stellar evolution. Far from the peculiarities of Pilsky star, another celestial giant, the red supergiant star Betelgeuse, presents its own set of mysteries. Located in the well-known constellation Orion, Betelgeuse has captivated scientists with its dramatic fluctuations in brightness. Known as a semi-regular variable star, Betelgeuse experiences significant dimming episodes that have become the subject of intense study. Unlike Pilsky star, Betelgeuse's brightness variations can be largely attributed to its pulsations. As a red supergiant, Betelgeuse's atmosphere is inherently unstable, causing the star to expand and contract in size. These pulsations lead to changes in the star's surface temperature, which in turn affects its brightness. When the star expands, its surface area increases, but it cools slightly, resulting in a dimmer appearance. Conversely, when the star contracts, its surface area decreases and the temperature rises, making the star appear brighter. This dramatic variability provides a stunning glimpse into the complexities of stellar behavior, offering astronomers a valuable opportunity to study the intricate processes that govern the evolution of supergiant stars. Through the study of stars like Pilsky star and Betelgeuse, astronomers are not only deepening their understanding of individual star behavior, but also gaining insights into the broader processes that shape the evolution of galaxies and stellar populations. These stars are more than just points of light in the night sky. They are natural laboratories that allow scientists to observe the effects of magnetism, pulsation, and chemical composition on stellar dynamics. As our telescopes become more powerful and our understanding of stellar physics deepens, these stars will continue to illuminate the mysteries of the universe. Betelgeuse, a star known for its unpredictable and dramatic brightness variations, offers an extraordinary opportunity to explore the life cycle of massive stars. At its core, the star's convective processes play a crucial role in its ever-changing luminosity. In its outer layers, massive convection cells, resembling a boiling pot, push hot gas from the star's interior up to the surface. This process causes localized brightening, while cooler gas sinking back down can lead to temporary dark spots. This dynamic interplay between hot and cool regions influences the overall brightness we observe from Earth. Between late 2019 and early 2020, Betelgeuse exhibited an unprecedented dimming event, one that caught the attention of astronomers worldwide. This great dimming, as it's been called, saw the star's brightness drop to about 60% of its usual intensity. Extensive observations later revealed that a massive ejection of material had occurred, creating a dense dust cloud that obscured the star's light. This circumstellar dust cloud, though temporary, acted like a cosmic shade, reducing the star's visible luminosity from our vantage point. The event was more than just a curious anomaly. It was tied to Betelgeuse's advanced evolutionary stage as a red supergiant. As the star nears the end of its life, it becomes increasingly unstable, experiencing significant mass loss. Such instability can result in dramatic changes in brightness, as was clearly seen during the Great Dimming. For astronomers, these fluctuations not only help us understand the mechanisms driving such variability, but also provide a rare front-row seat to the final stages of a massive star's life before it explodes in a supernova. The mystery surrounding Epsilon Orionis, another fascinating star system, has intrigued astronomers for over a century. Epsilon Orionis is known for periodic dimming every 27 years, which lasts for approximately 2 years each time. Initially baffling, this periodic dimming is now understood to be caused by a dark object passing in front of the star. However, this is no ordinary celestial body. It's a massive, complex structure. The primary star of the system is an F-type supergiant whose light is partially blocked during these dimming events by a colossal disk of dust. This disk likely surrounds a secondary companion, which is believed to be part of an evolving binary system. The dust disk itself is massive, measuring around 8 astronomical units in diameter, roughly equivalent to the distance from the Sun to Jupiter. Its substantial thickness and density are sufficient to block a significant portion of the primary star's light, creating the dimming effects observed from Earth. What makes this system particularly intriguing is that the disk is not a solid object, but rather a structure of gas and dust, with variations in opacity due to inhomogeneities such as denser regions or gaps within it. The disk appears to be edge-on from our perspective, meaning we can observe its entire extent as it moves across the face of the supergiant star, eclipsing its light. This periodic eclipse, which lasts for about 2 years, occurs because of the disk's immense size and the time it takes to completely pass in front of the primary star. Further evidence from spectroscopic studies has confirmed the disk's composition, mainly dust and gas, which contributes to the observed opacity during the eclipse. Interestingly, subtle variations in light have been noted even outside of the primary eclipse, likely due to the interactions between the light from the supergiant and the structure of the disk. As astronomers continue to monitor and study Epsilon Orionis, they aim to refine their understanding of this unique binary system, focusing particularly on the enigmatic companion and its massive dust disk. By observing the system's dynamics, they hope to uncover further details about the structure, composition, and evolutionary history of both the disk and the companion star, shedding light on the fascinating processes that govern such complex systems. In the vast, uncharted territories of space, certain phenomena continue to mystify scientists, pushing the boundaries of our understanding. Among these enigmas is the curious case of Epsilon Origi, a star system that challenges the conventional wisdom of stellar evolution. In particular, binary systems like Alol, often referred to as the demon star, have left astronomers scratching their heads. This system, composed of two stars with vastly different characteristics, defies established theories in a striking way. Typically, in a binary system, the more massive star is expected to evolve more rapidly, eventually swelling into a red giant. Meanwhile, its less massive companion would remain on the main sequence, following a slower, steadier evolutionary path. But in the case of Alol, this progression appears reversed. Instead of the heavier star becoming the older, more evolved giant, it is the less massive star that remains young and still on the main sequence, while its companion star ages prematurely. This contradiction is not a fluke, but rather an intricate result of mass transfer between the two stars. At some point in its evolution, the initially more massive star expanded into a red giant, beginning to shed its outer layers. These layers were then siphoned off by its companion star. The recipient star, now possessing more mass, grew brighter and hotter, presenting itself as a younger star despite its advanced age. The donor star, having lost significant mass, was left with a smaller, more exhausted core, much older than it should appear. This fascinating dynamic within the binary system reveals the profound and often unexpected nature of stellar evolution, where the presence of a close companion star can dramatically alter a star's life cycle. Moving from the heart of stars to the deepest reaches of the universe, one of the most compelling puzzles in modern astrophysics is the origin of ultra-high energy cosmic rays. Particles with energies so extreme that they exceed 1 quintillion electron volts. These cosmic particles slam into Earth's atmosphere with immense power, triggering massive air showers that cascade into secondary particles detectable by ground-based instruments. What makes these cosmic rays so perplexing is their energy. Such powerful particles could not have originated within our Milky Way, suggesting that they come from beyond the galaxy. Several theories seek to explain the origin of these cosmic bullets. One prominent idea points to the violent processes occurring in active galactic nuclei. In these regions, supermassive black holes lie at the centers of galaxies, spewing enormous jets of energy and particles. These jets, composed of particles moving at nearly the speed of light, could provide the perfect environment for accelerating particles to ultra-high energies. Another leading hypothesis involves gamma-ray bursts, GRBs, colossal explosions that mark the death of massive stars or the merging of neutron stars. Such catastrophic events release unimaginable amounts of energy, which could propel particles to the extreme energies we observe in cosmic rays. Magnetic fields in these violent environments could further accelerate these particles, whipping them into frenzied motion across vast intergalactic distances. Eventually, they reach our planet, where they collide with Earth's atmosphere, offering scientists rare and valuable insights into the universe's most extreme processes. Yet, the influence of these high-energy particles extends beyond the realm of astrophysics. Cosmic rays may also play a more significant role in shaping Earth's climate than previously thought. When these energetic particles strike our atmosphere, they ionize air molecules, which can act as nuclei for cloud formation. As clouds reflect sunlight, an increase in cosmic rays could enhance cloud cover, potentially cooling the planet's surface. On the other hand, a decrease in cosmic ray activity might lead to fewer clouds, allowing more sunlight to reach Earth and triggering a warming effect. This subtle interplay between cosmic rays and climate remains an area of intense research, with ongoing studies exploring how these high-energy particles may influence long-term climate patterns. But perhaps most startling is the effect of cosmic rays on life itself. These energetic particles don't just crash into our atmosphere, they also interact with our DNA. Their high energies can cause ionization within biological tissues, potentially leading to genetic mutations. As we continue to study the far-reaching impacts of these particles, we may begin to uncover more about their role in both the evolution of life and the conditions necessary for life to thrive on our planet. In this ongoing journey of discovery, Epsilon Origin, the nature of ultra-high energy cosmic rays and their hidden influence on Earth's atmosphere and life are just a few examples of how the universe continues to present us with mysteries that defy our understanding. These revelations not only challenge our knowledge of the cosmos, but also remind us of the intricate, interconnected nature of the universe, where the smallest particles and the most distant stars shape the world around us in ways we are only beginning to comprehend. Cosmic rays, high-energy particles traveling at nearly the speed of light, strike the living tissues on Earth in ways that are both profound and mysterious. These energetic particles, originating from some of the most violent and dynamic environments in space, cause ionization as they crash into atoms and molecules within our bodies. This ionization can lead to genetic mutations, sometimes with serious consequences. While most organisms have evolved robust mechanisms to repair the damage to their DNA, the relentless bombardment by cosmic rays over millions of years has undoubtedly influenced evolutionary processes. What's truly fascinating is the potential role these cosmic rays play in genetic variation. As these high-energy particles strike living cells, they occasionally result in beneficial mutations, changes that may contribute to the evolutionary diversity of life. However, they also carry significant risks. For humans, the threat is notably heightened for astronauts, who are exposed to elevated levels of cosmic radiation outside of Earth's protective magnetic field. In such environments, cosmic rays can increase the likelihood of developing cancer and other health issues, underscoring the importance of shielding astronauts from these invisible dangers. Cosmic rays are not just abstract particles. Their effects are tangible and felt both on Earth and beyond. As some of the most mysterious particles in the universe, cosmic rays achieve speeds that bring them closer to the limit of what's possible in the realm of high-energy physics. Their velocity is primarily powered by some of the most extreme astrophysical phenomena, including supernovae, active galactic nuclei, AGN, and gamma-ray bursts, GRBs, all of which serve as natural particle accelerators. These energetic particles are generated from violent events in the cosmos, and their journey to near-light speed offers a glimpse into nature's incredible capacity to produce energy far beyond our most advanced human-made accelerators. Supernova, the explosive deaths of massive stars, are one of the primary mechanisms responsible for cosmic ray acceleration. When a star goes supernova, it releases an unimaginable amount of energy, sending shockwaves across space. These shockwaves act like cosmic particle accelerators, hurling charged particles to astonishing speeds, close to the speed of light. Similarly, the centers of galaxies, known as active galactic nuclei, also contribute to cosmic ray acceleration. These AGNs are powered by supermassive black holes that consume massive quantities of matter, releasing jets of particles that can extend for millions of light years. The magnetic fields within these jets whip the particles, accelerating them to ultra-high energies. Gamma-ray bursts, short-lived but incredibly powerful explosions from star collapses or neutron star mergers, offer another mechanism for cosmic ray production. These bursts, although brief, release colossal amounts of energy, propelling particles to near-light speed. Together, these violent astrophysical events create a celestial laboratory where nature achieves particle accelerations on a scale that dwarfs anything we can create on Earth. But the story doesn't end there. As these cosmic rays travel through space, they interact with the interstellar medium ISM, a collection of gas, dust, and cosmic plasma that fills the vast expanses of space. These interactions are both complex and fascinating. One of the most significant effects is ionization. When cosmic rays collide with atoms and molecules in the ISM, they strip away electrons, creating ions. This process plays an essential role in maintaining the electrical charge balance in interstellar space, and it also affects the chemistry of the ISM. These ionized particles participate in chemical reactions that can form new compounds and even trigger further changes in the medium. Another important interaction occurs when cosmic rays collide with nuclei in the ISM, leading to the creation of secondary particles. Among these are pions and muons, types of subatomic particles that are produced in the cascade of energy. These interactions also generate gamma rays, which can be detected by telescopes and provide astronomers with valuable insights into the underlying processes that are shaping the cosmos. By studying these high-energy interactions, scientists can learn more about the conditions and forces at play in space, furthering our understanding of the universe and its incredible complexity. Thus, while cosmic rays may seem like distant phenomena, their impact is deeply woven into the fabric of life on Earth. From influencing the genetic diversity of life to reshaping the chemistry of space itself, these enigmatic particles reveal a universe that is far more interconnected and dynamic than we can even imagine. Cosmic rays, those high-energy particles traveling through the vast expanse of space, have a profound impact on the interstellar medium, ISM, the tenuous matter that exists between stars in our galaxy. These energetic particles don't just pass through unnoticed, they contribute to heating the ISM, especially in regions where the gas is of low density. The energy deposited by these cosmic rays can alter the temperature and pressure of the interstellar clouds, influencing the conditions necessary for star formation. This interaction between cosmic rays and the ISM is a perfect example of the dynamic and interconnected nature of our galaxy, where high-energy particles from distant sources continuously shape and are shaped by the sprawling web of interstellar matter. To understand the cosmic ray spectrum, it's essential to look at certain features, specifically the terms knee and ankle. These points refer to dramatic changes in the flux of cosmic rays as plotted against their energy. The knee occurs around an energy of about 1 quadrillion electron volts. It's a critical feature, providing a clue as to the limits of cosmic ray acceleration within our galaxy. One leading hypothesis suggests that the knee marks the point beyond which supernova remnants, long thought to be the primary accelerators of cosmic rays, can no longer accelerate particles effectively. As cosmic rays reach higher energies, they face increasing difficulty being confined by the magnetic fields within the remnants, causing a steep drop in their abundance beyond this point. At the knee's higher energies, particles begin to escape the galaxy's magnetic field more easily, diminishing their chances of detection here on Earth. The next significant feature, known as the ankle, appears at even higher energies, around 10 quintillion electron volts. This feature presents a different challenge, offering insights into the origins of cosmic rays. The ankle is thought to mark the transition from cosmic rays originating within our galaxy to those coming from more distant extragalactic sources. Above this energy, cosmic rays are believed to come from powerful extragalactic phenomena such as active galactic nuclei and gamma ray bursts. These ultra-high energy particles travel immense intergalactic distances, and their observed flux is less affected by the galaxy's magnetic fields and more influenced by the large-scale structure of the universe. The appearance of the ankle signals a shift in the nature of cosmic ray sources. While the knee represents a limitation of galactic acceleration mechanisms, the ankle bridges our understanding of both galactic and extragalactic cosmic phenomena, opening up a window into the complex interplay between different regions of space. Now, when it comes to categorizing the origins of cosmic rays, two broad groups emerge: solar cosmic rays and galactic cosmic rays. Though both are high-energy particles, they come from entirely different sources and possess unique characteristics. Solar cosmic rays, also known as solar energetic particles, SEPs, are primarily generated during solar flares and coronal mass ejections, CMEs. These events release enormous amounts of energy, propelling charged particles, mainly protons and helium nuclei, into the solar system. These solar cosmic rays generally have lower energies compared to their galactic counterparts, typically in the range of tens to hundreds of millions of electron volts. The intensity of solar cosmic rays is strongly influenced by the solar cycle, peaking during periods of heightened solar activity, which occur roughly every 11 years. In contrast, galactic cosmic rays, GCRs, originate from deep within our galaxy, likely from supernova remnants, pulsars, and other high-energy astrophysical sources scattered across the Milky Way. These cosmic rays travel vast distances through the interstellar medium before reaching Earth. GCRs are composed of a much broader spectrum of elements, ranging from hydrogen to heavier elements like iron, and they carry incredibly high energies, often reaching billions and even trillions of electron volts. When these galactic cosmic rays interact with the Earth's atmosphere and magnetic field, they significantly contribute to the background radiation that is experienced at ground level as well as at high altitudes. Their presence is an ever-present reminder of the dynamic, energetic universe that lies just beyond our planet. These cosmic particles not only provide valuable information about the origins and behavior of high-energy astrophysical phenomena, but they also play a crucial role in shaping the environment we live in. In essence, the study of cosmic rays reveals much about the nature of the universe. The knee and ankle in the cosmic ray spectrum, as well as the contrast between solar and galactic cosmic rays, offer invaluable insights into the mechanisms driving these particles, helping scientists unravel the mysteries of space and the forces that govern it. Because of their differing origins, solar and galactic cosmic rays interact with the heliosphere, the bubble-like region of space dominated by the solar wind, in fascinating and unique ways. The solar wind modulates the flux of galactic cosmic rays, GCRs, with solar activity directly influencing how many of these particles can penetrate deep into the inner solar system. During periods of high solar activity, the solar wind and magnetic field are enhanced, providing a greater shielding effect and reducing the intensity of GCRs that reach Earth. Conversely, during low solar activity, the GCR flux increases as the shielding effect weakens. Understanding these variations is crucial for many aspects of space exploration, where both solar and galactic cosmic rays pose significant radiation hazards to astronauts and spacecraft. The interaction between solar and galactic cosmic rays not only impacts the radiation environment in space, but also influences the broader dynamics of space weather, which can affect technological systems on Earth. This makes it vital to understand how these cosmic rays behave as they travel through the vast reaches of space. One of the most critical sources of galactic cosmic rays is the remnants of supernovae. Supernova remnants, SNRs, are some of the most powerful natural particle accelerators in the galaxy, and they play a pivotal role in accelerating cosmic rays. When a massive star reaches the end of its life, it undergoes a catastrophic explosion known as a supernova. This explosion releases enormous amounts of energy and stellar material into space, creating shock waves that travel through the surrounding interstellar medium. These shock waves are the key to accelerating particles to the high energies characteristic of cosmic rays. Within the shock front of a supernova remnant, a process called diffusive shock acceleration occurs. As particles, primarily protons and atomic nuclei, encounter the shock wave, they experience significant increases in energy through repeated interactions with turbulent magnetic fields. With each crossing of the shock front, particles gain velocity, transforming the shock into a powerful particle accelerator. This process continues until particles reach relativistic speeds, approaching the speed of light. Eventually, these accelerated particles escape the magnetic confinement and propagate across the galaxy as cosmic rays. Observations of supernova remnants, such as the ones in the Cygnus region and the TV gamma ray sources, provide compelling evidence supporting this acceleration mechanism. High-energy gamma rays detected from these remnants are believed to result from the interactions of accelerated particles with surrounding matter and magnetic fields. These gamma rays act as indirect evidence of the high-energy cosmic rays that are produced during these explosive events. Therefore, supernova remnants contribute significantly to the galactic cosmic ray population, but they also deepen our understanding of the processes that govern high-energy astrophysics and the life cycle of stars. Cosmic rays, high-energy particles originating from sources such as the Sun, supernova remnants, and distant galaxies, have a profound impact on space weather. Space weather refers to the collection of conditions and phenomena in space that can affect both Earth and its technological systems. Galactic cosmic rays interact with the space environment around Earth, influencing the dynamics of the heliosphere, magnetosphere, and ionosphere. In the heliosphere, the bubble-like region of space affected by the solar wind, cosmic rays are modulated by the solar activity cycle. During periods of high solar activity, the solar wind and stronger magnetic fields act as a shield, reducing the influx of galactic cosmic rays. During solar minimums, when solar activity is lower, this shielding effect weakens, and the flux of cosmic rays reaching Earth increases. These variations in cosmic ray intensity significantly affect the radiation environment in space, which is of particular concern for spacecraft electronics and the health of astronauts. Cosmic rays also contribute to the generation of space weather disturbances by interacting with Earth's magnetosphere and ionosphere. When high-energy cosmic rays enter Earth's atmosphere, they produce secondary particles such as neutrons and muons, which can penetrate deep into the atmosphere and even reach the surface. These secondary particles can induce transient ionization bursts in the ionosphere, disrupting radio signal propagation and GPS accuracy. The intricate relationship between solar and galactic cosmic rays, the heliosphere, and Earth's atmospheric systems underscores the complexity of space weather. Understanding these interactions is crucial for the development of mitigation strategies to protect space missions and technological systems on Earth. The role of supernova remnants in the acceleration of cosmic rays further adds a layer of intrigue to this already complex picture, highlighting the interconnectedness of cosmic events and their influence on the environments we rely on. Cosmic rays, those high-energy particles that bombard our planet from the far reaches of space, play a significant yet often underappreciated role in influencing Earth's environment. Their impact stretches far beyond just cosmic exploration, influencing everything from weather patterns to climate and even the technology we depend on in space. Yet, there's much more to these particles than meets the eye. When cosmic rays enter Earth's atmosphere, they interact with the planet's magnetic field, shaping their paths and altering the dynamics of their journey. These particles, protons, electrons, and atomic nuclei, travel through space carrying with them signatures of the environments they originated from. As they approach Earth, they don't arrive as simple, inert particles. They are messengers, transmitting information about the cosmic regions they have traveled through. These high-energy particles come from some of the most extreme and far-off places in the universe: supernova remnants, active galactic nuclei, and stellar nurseries. By studying cosmic rays, scientists can peer into the very heart of distant galaxies and stars, locations otherwise unreachable by traditional telescopes. Once these cosmic rays make contact with Earth, their composition reveals critical details about the origins of the elements they carry. Heavy elements like carbon, oxygen, and silicon found in cosmic rays indicate processes like stellar nuclear synthesis and supernova explosions, events that generate the building blocks for new stars, planets, and ultimately life itself. These particles allow us to study the chemical evolution of galaxies, from their star formation rates to the types of stars populating them. It's a cosmic map of evolution, a roadmap to understanding the formation of galaxies, stars, and even the planet we call home. However, the information cosmic rays provide doesn't stop at their composition. Their energy spectra and isotopic compositions hold even deeper layers of insight. The way these particles accelerate as they journey through space, affected by massive cosmic explosions, can be detected by variations in their energy levels and isotopic ratios. Understanding these variations informs us about the acceleration mechanisms at play, like those in supernova remnants or the powerful cores of active galaxies. Furthermore, as these particles travel through space, they leave unique imprints on the cosmic landscape, with spallation reactions occurring when they collide with interstellar atoms, breaking them down into lighter elements and isotopes detectable when the cosmic rays finally reach Earth. Cosmic rays also interact with Earth's geomagnetic field in fascinating ways, influencing both space weather and atmospheric conditions. The Earth's magnetic field, generated by the movement of molten iron in the planet's core, acts as a protective shield against these energetic particles. When cosmic rays encounter this field, the Lorentz force causes them to spiral along the magnetic lines, deflecting them away from the Earth's surface. The strength of this shielding, however, isn't the same everywhere on Earth. Near the equator, where the magnetic field is horizontal and strongest, cosmic rays are largely deflected, while at the poles, where the magnetic lines converge and are more vertical, cosmic rays can penetrate the atmosphere more easily. This difference explains why the highest concentrations of cosmic rays are observed at higher latitudes and altitudes, an effect that contributes to phenomena like auroras and influences ionization levels in the polar atmosphere. The impact of cosmic rays on weather and climate although less directly observed, is profound. Over long periods, the constant bombardment of these particles could have subtle effects on the formation and dynamics of clouds, potentially altering weather patterns, and even contributing to shifts in climate. These influences underscore the need for advanced space weather forecasting and mitigation strategies, especially as we continue to depend more heavily on space-based technology and infrastructure. In conclusion, cosmic rays are much more than just high-energy particles that stream through space. They are cosmic messengers, revealing secrets about the distant universe, the processes that drive star and galaxy formation, and even the underlying dynamics that could affect life on Earth. Understanding these particles isn't just a scientific curiosity, it's a crucial step toward better protecting our technological infrastructure and our planet's future. As we continue to advance our understanding of these particles, we gain not just insights into the cosmos, but also the tools necessary to navigate the challenges they present. In the vast expanse of space, there exists a question that has baffled scientists for centuries. What triggered the beginning of our universe? It's a question that echoes through the corridors of both physics and cosmology, one that touches on the very essence of existence. Imagine, if you will, a time before the universe as we know it, before stars, galaxies, and even space itself. The moment of creation, the Big Bang, remains one of the most enigmatic phenomena in modern science. Yet, even as we delve into its depths, the story doesn't end there. The intriguing question of what caused the initial conditions of the Big Bang is one that continues to challenge our understanding of the cosmos. Aviation and space missions have illuminated the critical role that Earth's magnetic shield plays in protecting our planet, yet the universe itself is governed by forces much more mysterious and complex. The traditional Big Bang theory paints the birth of the universe as a singularity, a point of infinite density and temperature where the laws of classical physics no longer hold. But what set this singularity in motion? This question remains an open frontier in scientific research, one that blends the unimaginable vastness of space with the mind-bending concepts of quantum mechanics. One prominent hypothesis proposes that quantum fluctuations within a pre-existing quantum vacuum could have set the universe into motion. According to the principles of quantum mechanics, even in what we perceive as empty space, tiny fluctuations occur, governed by the uncertainty principle. These fluctuations, however imperceptible they may seem, might have been the spark that ignited the Big Bang. If such a fluctuation occurred, it could have triggered a rapid expansion in a process known as cosmic inflation. This inflationary period would not only explain the universe's large-scale homogeneity and isotropy, but also give rise to the density fluctuations that eventually led to the formation of galaxies and other cosmic structures. But this theory is just one piece of the puzzle. Another captivating theory takes us even further, into the realm of the multiverse. Here, our universe is just one bubble in an infinite sea of universes, each with its own set of physical laws and initial conditions. This concept, known as eternal inflation, suggests that different regions of space-time can inflate at different rates, leading to the creation of multiple universes, each born from its own Big Bang-like event. The conditions we observe in our universe, then, could be the result of random variations across this vast multiversal expanse. Though both the quantum fluctuation theory and the multiverse hypothesis offer intriguing possibilities, they remain speculative, subjects of ongoing research and debate. These theories attempt to bridge the gap between quantum mechanics and general relativity, two of the most successful but seemingly incompatible pillars of modern physics. Yet, in doing so, they also highlight the vastness of what we still do not understand, realms beyond our current observational capabilities, where the true origin of our universe may lie. As we strive to uncover the mysteries of the Big Bang, we must also address the formation of the very first stars and galaxies. This epoch, often referred to as the Cosmic Dawn, marks a transformative moment in the history of the universe. To understand this, we must first look at the aftermath of the Big Bang. The universe, a seething cauldron of elementary particles and radiation, began to cool and expand over the course of the next few 100,000 years. During this period, particles combined to form neutral hydrogen and helium atoms, a process known as recombination. This led to the decoupling of matter and radiation, allowing the universe to become transparent and setting the stage for the formation of the cosmic microwave background, CMB, the faint afterglow of the Big Bang that we can observe today. The next phase, the Dark Ages, saw the universe bathed in a diffuse gas of neutral hydrogen and helium, devoid of visible light, as no stars or galaxies had yet formed. Yet, it was during this time that tiny density fluctuations, remnants of the Big Bang, began to grow under the influence of gravity. These fluctuations, captured in the CMB, set the stage for the formation of the first structures in the universe. Gravity continued to pull gas into increasingly dense regions, and eventually these regions collapsed, giving birth to the first stars, known as population 3 stars. These early stars were unlike those we see today. They were massive, formed from nearly pure hydrogen and helium, and lacked the heavier elements that populate stars today. The extreme pressure and temperatures in these stars ignited nuclear fusion, leading to the emission of light and ionizing radiation. This radiation began to ionize the surrounding hydrogen gas, marking the end of the Dark Ages and the beginning of the epoch of reionization. As the first stars ignited, they grouped together to form proto-galaxies, the seeds of the universe's vast interconnected structure. What we now know as the universe, the galaxies, stars, and cosmic structures, is the result of this incredible journey. From quantum fluctuations to the first stars, each step along the way has shaped the universe into the magnificent, awe-inspiring cosmos we see today. And yet, as we peer into the farthest reaches of space, we realize that our understanding is still in its infancy, and the greatest mysteries lie just beyond the horizon, waiting to be uncovered. As these stars lived and died, they left behind an indelible mark on the universe. Through the explosive fury of supernova, they enriched the interstellar medium with heavier elements, breathing life into the very building blocks of future stars. This chemical enrichment sparked the birth of new generations of stars, each with a wider range of masses and properties. As these stellar giants ignited, they contributed to the formation of galaxies, shaping the cosmic landscape. Over time, these proto-galaxies began to merge and interact, undergoing a grand cosmic choreography. Gravity, the invisible force that binds everything, guided these stellar dances, and through it, galaxies grew more complex and larger. What began as a nearly featureless universe transformed, driven by particles, radiation, and the unstoppable force of gravity, into a richly structured cosmos teeming with stars and galaxies. The epoch of reionization marks one of the most transformative periods in the universe's evolution. It began roughly 400 million years after the Big Bang, lasting until about 1 billion years later, marking a period in which the first stars and galaxies reshaped the intergalactic medium. Prior to this, the universe was shrouded in darkness, an era known as the Dark Ages. During this time, hydrogen and helium atoms had cooled sufficiently to form neutral particles, which dominated the universe's structure. This neutral state created a largely opaque cosmos, with electromagnetic radiation unable to pass freely due to the absorption of high-energy photons by the hydrogen atoms. However, everything changed with the birth of the first generation of stars, known as population 3 stars. These massive and short-lived stars emerged from nearly pristine hydrogen and helium gas, emitting vast amounts of ultraviolet light. Their intense radiation ionized surrounding hydrogen atoms, stripping electrons from protons and transforming them into plasma. The process was chaotic, patchy, and gradual. Initially, ionized regions formed around individual stars and galaxies. But as more stars emerged, their combined radiation gradually expanded these bubbles of ionized gas. Eventually, these bubbles merged and the universe began to transition from a neutral state into a largely ionized one. The reionization process was not uniform. It was a complex patchwork that unfolded over millions of years. The energy from early black holes and quasars, highly luminous centers of young galaxies, also contributed to the reionization, emitting vast amounts of energetic radiation. As the universe became more ionized, photons were able to travel more freely through space, transforming the universe into a transparent state. This transparency opened the door for the more efficient formation of galaxies and laid the foundation for the intricate cosmic web of structures that we observe today. Understanding the epoch of reionization is crucial for deciphering the origins of the first galaxies and the large-scale structure of the universe. With advanced telescopes like the James Webb Space Telescope, we are now able to peer back in time to this enigmatic period, gaining insights into the processes that ended the cosmic dark ages. Equally perplexing is the mystery of the asymmetry between matter and antimatter, a fundamental puzzle in modern physics. According to the Big Bang theory, the universe began with equal amounts of matter and antimatter. However, our universe is overwhelmingly made of matter, with very little antimatter remaining. This discrepancy, known as the baryon asymmetry problem, remains one of the most intriguing unresolved issues in cosmology. Several theories attempt to explain this imbalance, one of which is known as baryogenesis. This hypothesis proposes that specific conditions in the early universe allowed for the creation of more matter than antimatter. For this process to have occurred, three critical criteria, known as Sakharov conditions, must have been met. These include baryon number violation, C and CP violation, and a departure from thermal equilibrium. Under normal circumstances, the number of baryons, such as protons and neutrons, remains constant. However, for matter to dominate over antimatter, certain interactions must have violated baryon number conservation. Some grand unified theories, GUTS, predict that processes at high energy scales could have led to the transformation of baryons into other particles, violating this conservation. The second condition, C and CP violation, involves the idea that particles and their corresponding antiparticles were not treated symmetrically. This violation has been observed in particle physics experiments, notably involving K and B mesons, where small but significant preferences for matter over antimatter were found. The third condition, a departure from thermal equilibrium, is equally essential. In the early universe, as it cooled, various phase transitions caused deviations from equilibrium conditions, creating a dynamic environment in which matter could asymmetrically outnumber antimatter. If equilibrium had been maintained, any imbalance would have been immediately annihilated. But thanks to the unique conditions of the early universe, this imbalance persisted, allowing for the matter-dominated universe we observe today. Despite these fascinating hypotheses, the true mechanism behind the baryon asymmetry remains a captivating mystery, one that continues to fuel research and speculation in cosmology and particle physics. The exact nature of baryogenesis remains a subject of intense speculation, and to this day, direct experimental evidence is still lacking. Physicists continue to explore various models, such as leptogenesis, which suggests that an initial imbalance in leptons eventually led to the dominance of baryons through processes that are indirectly related. Among the most promising areas of research are high-energy particle experiments, including those conducted at the Large Hadron Collider, LHC, and studies of neutrino properties. These could hold vital clues to understanding the mechanisms behind CP violation and other critical factors. Solving the mystery of why there is more matter than antimatter could unlock new realms of physics beyond the standard model, offering profound insights into the fundamental workings of our universe and its origins. Imagine the universe just after the Big Bang, during a time so hot and energetic that traditional physics struggles to fully describe it. This early phase, known as cosmic inflation, occurred roughly 10 to the power of negative 33 seconds after the birth of the universe, and lasted until about 10 to the power of negative 32 seconds. In this incredibly brief moment, the universe expanded at an extraordinary rate, growing by at least a factor of 10 to the power of 26. This rapid expansion, faster than the speed of light, left behind a cosmos that was eerily homogeneous and isotropic, despite its origin from quantum fluctuations in an unimaginably small volume. Scientific consensus suggests that this inflationary period was driven by a mysterious field known as the inflaton. A concept rooted in quantum field theory, the inflaton field is believed to have had an energy density that remained nearly constant over time, causing space to stretch at an accelerating rate. As the inflaton field decayed, it released an immense amount of energy, effectively reheating the universe and setting the stage for the formation of particles and complex structures. This period of rapid expansion resolves many of the paradoxes that plagued early universe models, such as the horizon and flatness problems. It leads us to marvel at how beautifully orchestrated the cosmos is, even during its most chaotic moments. Understanding these early stages of cosmic inflation helps us appreciate the intricate balance that governs the universe. It shows us just how finely tuned the universe is, even in the face of such tremendous turbulence. Now, the ultimate fate of the universe remains one of the most tantalizing questions in cosmology, with multiple theories vying for prominence. The Big Freeze, the Big Rip, and the Big Crunch each offer a distinct vision of a final cosmic chapter. The Big Freeze suggests that the universe's relentless expansion, driven by dark energy, will continue indefinitely. Over billions of years, galaxies will drift so far apart that light from one will no longer reach another. Stars will exhaust their nuclear fuel, eventually turning into white dwarfs, neutron stars, or black holes. These remnants, too, will either evaporate or fall silent, leaving a cold, dark void where temperatures approach absolute zero and no thermodynamic work can occur. It's a bleak yet gradual fading away of all cosmic activity. In contrast, the Big Rip theory proposes a far more catastrophic end. If dark energy continues to grow stronger, it could tear the very fabric of space-time apart. Galaxies, stars, planetary systems, and even atomic particles would be ripped from one another and hurled into infinite distances. This rupture could occur relatively quickly, overpowering all other forces in the universe, dismantling gravitationally bound systems, ripping apart atoms, and dissolving the known universe into a chaotic, featureless void. Alternatively, there is the Big Crunch, where gravity ultimately prevails in this cosmic tug-of-war. If the density of the universe is high enough to halt its expansion, gravitational forces would reverse the process, pulling galaxies back together in a colossal collapse. This contraction could cause temperatures to soar and densities to rise, possibly leading to conditions reminiscent of the Big Bang. Some cosmologists speculate that this could trigger a cyclic model of eternal oscillation, with the universe being reborn from its own ashes. Determining which of these scenarios will prevail hinges on precise measurements of cosmic parameters, including the exact properties of dark energy, the universe's density, and its overall shape. As our observational tools continue to improve, we are edging ever closer to understanding how this grand cosmic narrative will ultimately unfold. Now, picture the universe as a stunningly intricate tapestry, woven from the threads of dark matter and punctuated by clusters of luminous galaxies. This vast, large-scale structure of the universe, comprising a mind-boggling web of filaments and voids, spans billions of light years. Tracing its origins back to the smallest quantum fluctuations moments after the Big Bang during the epoch of cosmic inflation, we begin to see how these tiny variations in density were exponentially magnified. These fluctuations seeded the formation of the vast cosmic structures we observe today, giving us a glimpse into the extraordinary story of our universe's beginnings. As the universe expanded and cooled, initial fluctuations in density began to shape the cosmos in profound ways. These fluctuations caused matter to gather and form clumps under the relentless pull of gravity. This process became the foundation of the cosmic web, a vast, interconnected network of galaxies, clusters, and superclusters, all separated by immense cosmic voids. At the heart of this grand design lies dark matter, an enigmatic substance that accounts for around 85% of the universe's mass. Though invisible and detectable only through its gravitational effects, dark matter played a critical role in shaping the universe. It provided the gravitational scaffolding on which ordinary matter could coalesce, eventually forming stars and galaxies. Without dark matter's influence, the universe's visible structures would have likely never taken shape in the orderly, complex patterns we observe today. As galaxies evolved, they continued to interact and merge, further molding the large-scale structure of the universe. By studying the distribution and movement of galaxies, cosmologists can trace the cosmic web's evolution all the way back to its primordial roots. This process opens a window into an unfolding narrative that began at the dawn of time and is still evolving, drawing us deeper into the vast mysteries of the universe. One of the most fascinating aspects of this unfolding narrative is the presence of primordial gravitational waves. These waves, conceived during the universe's earliest moments, can be imagined as ripples in space-time, much like the waves that form when a stone is dropped into still water, generated during the inflationary epoch. These ancient waves hold the potential to offer undeniable evidence supporting the theory of cosmic inflation. The inflationary period, which began roughly 10 to the power of 33 seconds after the Big Bang and lasted until about 10 to the power of negative 32 seconds, saw the universe expand at speeds faster than light itself. This extraordinary growth not only stretched space but amplified the quantum fluctuations present at the time. These fluctuations, frozen in place by the rapid inflation, evolved into primordial gravitational waves. Unlike electromagnetic waves, which travel through space, gravitational waves are oscillations of space itself. They are incredibly elusive, but offer profound insight into the earliest moments of the universe. Detecting these primordial gravitational waves would be a monumental breakthrough. It would not only confirm that inflation occurred, but also provide essential information about the energy scale of inflation and the fundamental physics that governed the early universe. Integral to the search for these waves is the study of polarization patterns found in the cosmic microwave background, CMB, a relic of radiation that fills the universe and originates from about 380,000 years after the Big Bang. Scientists scrutinize the B-mode polarization patterns within the CMB, searching for swirling signatures that primordial gravitational waves might imprint. These patterns would be the telltale signs of spacetime being stretched and compressed during inflation's rapid expansion, as predicted by inflationary models. The detection of primordial gravitational waves would represent a profound leap forward in our understanding of the cosmos. It would provide crucial insights not only into the nature of inflation, but also into the very fabric of the early universe, bridging the gap between the macroscopic structures of the cosmos and the minute quantum fluctuations that seeded them. As technology and observational techniques continue to advance, the search for these primordial waves remains one of the most exciting frontiers in modern cosmology. But the mysteries of the universe don't end there. The Hubble tension, a perplexing discrepancy between different measurements of the universe's current rate of expansion, introduces another layer of complexity. The Hubble constant, which quantifies the rate of expansion, is typically measured in two ways: through direct measurements of the local universe using standard candles like Cepheid variables and Type 1a supernovae, and through indirect measurements derived from the cosmic microwave background, CMB, using the standard model of cosmology and data from the early universe. Yet, these methods yield different results. Local measurements suggest a faster expansion rate, around 73 kilometers per megaparsec, while the CMB-derived measurements suggest a slower rate, closer to 67 kilometers per megaparsec. Resolving this tension is no small task and requires a deep dive into both observational data and theoretical models. One possibility is that there may be new physics beyond the current standard model of cosmology, such as another form of dark energy or a modification of general relativity. These ideas could potentially explain the differing measurements and offer a more complete understanding of the universe's expansion. In the grand scheme of things, each of these discoveries, whether it's the role of dark matter, the detection of primordial gravitational waves, or resolving the Hubble tension, brings us closer to unlocking the mysteries of our universe. Every step forward in cosmology reveals a universe far more intricate and fascinating than we ever imagined. And as technology advances, we inch closer to unraveling the secrets of space-time itself. In the vast expanse of our universe, a question lingers, a cosmic conundrum that challenges our understanding of the very fabric of existence. A prominent hypothesis proposes that the elusive forces of dark matter and dark energy might be interacting in ways that remain beyond our comprehension, influencing the rate of cosmic expansion in ways we cannot yet predict. However, an alternative explanation suggests the root cause of the discrepancy could lie in errors within the measurement techniques themselves, whether in the local observations or the cosmic background radiation measurements. Perhaps unseen variables, such as cosmic dust, galactic foreground objects, or issues with calibration, are skewing the data, leading us down a path of confusion. This introduces a pivotal area for future research, urging us to reevaluate the assumptions made about the early universe's condition and its complex composition. As we strive to resolve the so-called Hubble tension, scientists are refining their approaches to measurements, seeking new ways to unlock the universe's secrets. One intriguing avenue is the exploration of intermediate distance indicators, such as gravitational waves from neutron star mergers, which could offer new insights into the dynamics of cosmic expansion. Simultaneously, advanced simulations are being developed to account for variables that influence both local and remote measurements, providing a more holistic view of the forces at play. The resolution of this cosmic riddle, no matter which path it takes, promises to open the doors to a deeper understanding of the fundamental forces that govern the universe. It could offer the key to bridging the vast scales of cosmology with the quantum framework that once governed the early universe, unlocking new realms of physics and reshaping our understanding of reality itself. At the heart of modern physics lies an even more profound challenge: reconciling the enigmatic world of quantum mechanics with the expansive universe described by general relativity. These two cornerstones of scientific theory explain the universe on vastly different scales. Quantum mechanics provides a precise framework for understanding the behavior of subatomic particles, where phenomena can defy intuition and observation. On the other hand, general relativity describes the behavior of massive objects like galaxies and stars, as well as the very fabric of space-time itself. Yet these two theories remain disconnected. How do we reconcile the very small with the very large? How do we unify the fundamental forces of nature? This is where theories like string theory come into play. String theory posits that the fundamental building blocks of the universe are not point-like particles, as traditionally imagined, but tiny vibrating strings of energy. Each particle is simply a different vibrational mode of these strings, each with distinct properties. To make sense of this, string theory introduces the concept of additional spatial dimensions beyond the familiar three, suggesting that the universe might be 10-dimensional. While this theory remains purely hypothetical, it holds the promise of unifying quantum mechanics and general relativity into a single coherent framework, offering a more complete description of the cosmos. Another competing theory, known as loop quantum gravity, LQG, proposes an equally compelling vision. LQG seeks to quantize space-time itself, imagining it as composed of discrete loops woven into a network, known as spin foam. This theory suggests that space and time are not continuous, but are instead composed of finite, indivisible units. At the Planck scale, an incredibly tiny level of measurement, this quantization could potentially resolve some of the infinities that plague the current understanding of general relativity. By introducing quantized units of space and time, LQG aims to provide a theory of gravity that is compatible with the principles of quantum mechanics. However, both string theory and loop quantum gravity face the daunting task of making testable predictions that distinguish them from other theories. Only time and advancements in technology and observation will tell whether these bold theories can be empirically validated. As we continue to probe deeper into the mysteries of the universe, the study of black holes presents one of the most tantalizing puzzles. These cosmic giants possess a paradox, where quantum information seems to vanish behind event horizons, defying the basic principles of quantum theory. This information paradox hints at profound connections between gravity and quantum mechanics, challenging our very understanding of the universe's fundamental nature. As scientific instruments such as gravitational wave detectors and particle accelerators grow more sophisticated, we edge closer to a potential breakthrough, one that might unify quantum mechanics and general relativity into a single theory of quantum gravity. If we succeed, it could revolutionize our understanding of the universe, providing a unified description of all the forces and particles that make up the grand tapestry of existence. Turning our gaze beyond the stars, we focus on Mars, our red, rust-colored neighbor. With its thin, uninviting atmosphere, the planet has fascinated scientists and laypeople alike for centuries. One of the most captivating mysteries surrounding Mars is the detection of methane in its atmosphere. On Earth, methane is often a byproduct of biological activity, though it can also be produced through geological processes. The discovery of methane emissions on Mars raises exciting possibilities. Could Mars, perhaps, harbor microbial life? Or at the very least, Could the planet support conditions conducive to life? Over the past 2 decades, both Earth-based telescopes and Mars-bound spacecraft, like the European Space Agency's Mars Express and NASA's Curiosity rover, have confirmed the presence of intermittent methane plumes. These emissions fluctuate with the seasons, disappearing quickly, suggesting that an active yet unidentified process is responsible for their release. There are 2 prevailing hypotheses to explain these methane emissions: biological activity and geological processes. Could microbes be producing methane beneath the Martian surface, or is the gas a byproduct of volcanic activity or some other geological mechanism? While we don't yet have definitive answers, the ongoing study of Mars continues to yield new data that could one day shed light on these questions. Whatever the case may be, the discovery of methane on Mars is a tantalizing clue in our search for life beyond Earth, one that promises to keep scientists and space enthusiasts alike on the edge of their seats as we await further exploration and analysis. The biological hypothesis surrounding the origin of methane on Mars suggests that the gas could be produced by microorganisms thriving beneath the planet's surface, much like methanogens on Earth. These microorganisms are known to flourish in extreme environments such as hydrothermal vents or deep underground habitats. On Mars, these microbes could inhabit subsurface aquifers, shielded from the harsh conditions above by layers of rock and soil. While no direct evidence of life has been found on Mars, the theory remains compelling. It draws from Earth's own history with extremophiles, organisms that can live in conditions once thought to be uninhabitable, providing a tantalizing possibility that life may exist, or may have once existed, on the Red Planet. Geological processes could also explain the methane emissions on Mars. One such process is serpentinization, a chemical reaction between water and certain types of rock, like olivine and pyroxene, which are abundant on the Martian surface. This reaction not only generates methane, but also produces hydrogen, another potential energy source that could support life. In addition, methane could be trapped in clathrate hydrates beneath the surface. These compounds, which form under high pressure and low temperature, could release methane periodically, triggered by temperature fluctuations or seismic activity. Given the potential significance of Martian methane, understanding its origin has become a top priority for current and upcoming missions to Mars. One such mission is the upcoming ExoMars rover, a joint venture between the European Space Agency, ESA, and Roscosmos. This rover is set to drill up to 2 meters below the Martian surface, searching for signs of past or present life, while also gaining a deeper understanding of the planet's geochemical processes. Each new discovery about the origins of methane on Mars brings scientists closer to unraveling the mystery behind its emissions, offering valuable insights into the planet's potential for supporting life and the dynamic processes that shape its environment. In the distant reaches of our solar system, Ceres, the largest object in the asteroid belt between Mars and Jupiter, continues to captivate astronomers with its enigmatic brightness variations. These fluctuations in brightness are most prominently associated with bright spots, which have puzzled scientists since the dwarf planet was first observed in detail by NASA's Dawn spacecraft in 2015. The most striking of these bright features lies in the Achater crater, where reflective materials create a dazzling contrast against the planet's darker surface. The unusual brightness on Ceres is primarily due to deposits of sodium carbonate, a type of salt alongside other evaporite minerals like ammonium chloride and sodium bicarbonate. These bright spots are believed to be the result of cryovolcanic activity, in which briny water from Ceres' interior reaches the surface through fissures. Upon contact with the vacuum of space, the water rapidly sublimates, leaving behind reflective salt deposits. This process of sublimation and deposition contributes to the stark brightness variations that can be observed from orbit. But the question remains, why does this activity occur? The presence of these salts strongly suggests that Ceres may still harbor a subsurface ocean, or at the very least, pockets of briny liquid water. This water is likely kept from freezing solid by a combination of radioactive decay and residual heat from the dwarf planet's formation. When pressurized brine finds a path to the surface, it erupts, creating bright deposits and contributing to the observed brightness variations. Changes in brightness over time may also be influenced by diurnal cycles, temperature fluctuations that subtly alter the surface composition. Additionally, transient atmospheres of water vapor, which may form during these cycles, could further impact the brightness. Another factor contributing to the brightness variations on Ceres could be impact events. Collisions with smaller asteroids could excavate these bright, salty materials from beneath the surface, sending them into sunlight where they temporarily shine brighter. As these exposed materials interact with space weathering processes, their albedo, reflectivity, can change over time, adding to the dynamic and shifting appearance of Ceres. Understanding the cause of these brightness variations provides invaluable insights into the geological history and internal structure of Ceres. These findings challenge traditional notions about the capabilities and limitations of small planetary bodies, offering compelling evidence that even objects as small as Ceres can exhibit complex active geology. Such discoveries expand our understanding of the potential for geological activity on smaller bodies throughout the solar system and may even change the way we think about the possibility of life existing on similarly small and distant worlds. Moreover, the very presence of liquid water, despite being in the form of salty brine, opens up a whole new realm of possibilities regarding the potential for life, either past or present, in our solar system. This discovery makes Enceladus, Saturn's enigmatic moon, an even more compelling object of study for scientists and space enthusiasts alike. Enceladus is a celestial body of immense intrigue, particularly due to its surface, which is adorned with striking features known as the tiger stripes. These 4 parallel tectonic fractures located near the south pole of the moon were first discovered by the Cassini spacecraft. Since their discovery, they have captivated the imaginations of scientists around the world, offering critical clues about the moon's dynamic nature. The tiger stripes are not just cracks in Enceladus's icy surface. They are vast, deep fissures, stretching hundreds of kilometers in length and reaching widths of approximately 1 to 2 kilometers. What truly sets them apart, however, is their extraordinary thermal activity. These cracks are more than just geological features. They act as conduits for massive geysers that erupt from beneath the moon's icy shell. These plumes, which spew water vapor, icy particles, and organic compounds into space, have become key to understanding the moon's internal processes. In fact, the geysers are so significant that they contribute to the formation of Saturn's E-ring, providing further evidence of the moon's active and ever-changing nature. What's even more fascinating is that these plumes are not just the result of surface processes. They hint at the existence of a hidden subsurface ocean beneath Enceladus's icy crust. The creation of these tiger stripes is thought to be largely driven by tidal forces exerted by Saturn's powerful gravity. Enceladus follows an elliptical orbit around its parent planet, and as it moves through its orbit, it experiences varying gravitational pulls. These fluctuations cause the moon to flex and strain its interior, generating frictional heat. This constant tidal stress is crucial in keeping parts of the subsurface ocean in a liquid state, while simultaneously creating the conditions necessary for the ice shell to crack open. As the moon's icy crust responds to the gravitational forces, the tiger stripes act as fault lines where the stress from the tidal forces is released. The heat generated by this friction ensures that these fault lines remain relatively warm and active, preventing them from refreezing completely. This continuous warming not only keeps the fractures open, but it also allows water from the subsurface ocean to rise through the cracks and erupt as geysers when it reaches the vacuum of space. These eruptions are a visual reminder of the geothermal energy at play beneath Enceladus's surface. Interestingly, the repeated cycles of tidal flexing and geyser activity serve to rejuvenate and reshape the tiger stripes over time. This ongoing process could explain why the tiger stripes appear relatively young, with a fresh appearance in stark contrast to the older, heavily cratered surface of Enceladus. These groundbreaking findings, gleaned from Cassini's close flybys and its suite of scientific instruments, suggest that Enceladus is not only an active moon, but one that possesses a geothermal energy source capable of sustaining liquid water beneath its icy shell. What adds to the allure of Enceladus is the presence of organic compounds within the geysers, further hinting at the moon's potential to support life. This has placed Enceladus firmly at the forefront of the search for extraterrestrial life within our solar system. Far from just being a striking geological curiosity, the tiger stripes offer a rare and exciting window into a hidden, dynamic world beneath the ice, one that might hold the secrets to the origins of life beyond Earth. On the other hand, there's another captivating object in our solar system that piques the curiosity of scientists: Bennu, an ancient carbon-rich asteroid that seems almost otherworldly in its appearance. With its top-like, diamond-shaped form, Bennu stands out from many other celestial bodies. At roughly 500 meters in diameter, it boasts a distinctive bulging equatorial ridge, setting it apart from the typical asteroid shape we might expect. But understanding how Bennu acquired this peculiar shape requires a deeper exploration of its formative processes and its long journey through the cosmos. One leading hypothesis for Bennu's unique shape is the Yarkovsky-O'Keefe-Radzievsky-Paddock YORP effect. This fascinating phenomenon influences the spin rates of small bodies in the solar system, including asteroids. The YRP effect occurs when sunlight heats the surface of an asteroid. This heat is then re-radiated as infrared radiation, which creates a small but continuous torque on the asteroid. Over millions of years, this slow accumulation of torque can significantly alter the asteroid's rotation rate. For Bennu, this effect may have increased its spin rate to such an extent that centrifugal forces began reshaping its structure. This alteration in rotation led to the migration of material toward the equator, forming the asteroid's distinctive ridge. The YORP effect, therefore, provides a potential explanation for how Bennu's unusual features came to be, offering a glimpse into the forces that shape not only this asteroid but others like it across the cosmos. Through these remarkable processes, both Enceladus and Bennu stand as testaments to the dynamic forces at play in our solar system. Enceladus, with its active geysers and the possibility of a hidden ocean, provides a tantalizing glimpse into the potential for life beyond Earth, while Bennu, with its mysterious shape and history, serves as a window into the long-term evolution of celestial bodies. These objects remind us that our solar system is far from static. It is a place of constant change, mystery, and discovery. Bennu, like many asteroids, has a fascinating and unique shape. Unlike monolithic asteroids, Bennu's form is heavily influenced by its rubble pile nature. A rubble pile asteroid isn't a single solid mass, but a conglomeration of rocks, boulders, and dust, all held together by mutual gravity. This structure gives Bennu a much more malleable quality compared to solid bodies. As Bennu rotates, centrifugal forces push the loosely bound regolith outward, allowing it to settle around the equator. This process accentuates the asteroid's distinct ridge-like appearance, creating a visual effect that is striking and unlike anything we see on other celestial bodies. Furthermore, the shape of Bennu has been influenced by impact events and seismic shaking. Collisions with other space debris are common in the asteroid belt, and they generate vibrations that can redistribute surface materials. Over time, this redistribution has played a crucial role in shaping the surface of Bennu. The constant bombardment in the asteroid belt, with impacts happening regularly, helps these small bodies like Bennu evolve and change. But Bennu's story doesn't end there. It's also a fragment of a much larger parent body, which likely had a far more complex and varied geological history. When this parent body broke apart, it could have imparted some initial angular momentum to Bennu. This momentum laid the foundation for its subsequent evolution, influenced by the Yarkovsky-O'Keefe-Radzievsky-Paddock effect, a phenomenon that causes small asteroids to change their rotation over time due to the way they absorb and radiate heat. NASA's OSIRIS-REx mission has revolutionized our understanding of Bennu. The spacecraft's detailed surface mapping and composition analysis have provided an unprecedented look into the asteroid's structure and the forces that shape it. From the data collected, scientists now have a coherent explanation for Bennu's unusual top-like shape. Its rapid rotation, rubble pile structure, and the YORP effect all contribute to its current form. As more data is analyzed, we'll gain a clearer understanding not only of Bennu, but also of similar bodies throughout the solar system. This knowledge can provide insights into the dynamic and fascinating nature of these ancient relics from the early solar system. Meanwhile, Earth's magnetic poles are constantly shifting. Unlike the relatively stable geographic poles, the magnetic poles are in a constant state of motion, driven by complex processes deep within the Earth. The key to this phenomenon lies in the outer core, where molten iron and nickel flow in dynamic, turbulent patterns. This movement generates electric currents, which produce magnetic fields, a process known as the geodynamo. The geodynamo theory explains how the rotation of Earth and convective heat flow from the inner core give rise to the Earth's magnetic field. But this magnetic field is not static. It's constantly changing as the molten iron and nickel in the outer core flow in response to thermal convection and the Coriolis effect caused by Earth's rotation. These fluid motions result in the shifting of Earth's magnetic poles. The North Magnetic Pole, for instance, is currently moving from the Canadian Arctic towards Siberia at a rate of approximately 50 to 60 kilometers per year. This movement is part of a larger phenomenon known as geomagnetic secular variation, the slow, gradual changes in Earth's magnetic field that occur over decades or even centuries. Sometimes these shifts can be more dramatic, leading to geomagnetic reversals. During a geomagnetic reversal, the magnetic north and south poles switch places. This has occurred irregularly throughout Earth's history, with reversals taking place roughly every few 100,000 years. These transitions can weaken the magnetic field temporarily and even cause it to exhibit a more complex multipolar structure before the new polarity is fully established. The monitoring of the Earth's magnetic field is essential for understanding these shifts. Instruments like magnetometers on the ground and satellites in orbit provide valuable data on the strength and direction of the magnetic field. This information not only helps scientists model the geodynamo processes, but also informs practical applications, such as navigation. The Earth's magnetic field plays a crucial role in protecting life on Earth by deflecting harmful solar radiation. As we continue to study the causes of pole shifts, we gain important insights into both the planet's internal dynamics and the technology that relies on the stability of Earth's magnetic field. In 2017, the scientific world was captivated by the arrival of Oumuamua, the first known interstellar object to pass through our solar system. This bizarre and elongated visitor immediately piqued the curiosity of astronomers due to its unusual characteristics, particularly its unexpected acceleration. This acceleration, a deviation from the expected gravitational path, challenged conventional understanding of celestial bodies. For centuries, comets and asteroids have followed predictable orbits influenced by the sun's gravity, but Oumuamua was different. Typically, the acceleration of such objects is explained by outgassing, a phenomenon where volatile substances like water and carbon dioxide vaporize as the object approaches the sun. This process creates jets that push the object forward. However, Oumuamua didn't seem to fit this mold. The object showed no visible signs of outgassing, suggesting that something else might be at play. Another hypothesis emerged, pointing to solar radiation pressure as a possible cause. In this theory, the sun's photons exert pressure on the object, causing it to accelerate. For solar radiation to be a significant factor, Oumuamua would need to have an incredibly low mass-to-area ratio, much like a light sail. This idea gained traction given the object's slender, elongated shape, which could have made it particularly susceptible to this kind of pressure. The implications of this theory are staggering. If Oumuamua is indeed a giant space sail, it would suggest that the object is much less dense than typical comets or asteroids. Some even speculated that it might be a fragment of a much larger, less dense structure, perhaps a piece of interstellar debris from an unknown origin. Yet, despite these intriguing theories, there remains a great deal of uncertainty. The short period of time during which Oumuamua was visible, combined with its high velocity, meant that scientists had a limited window to study it in detail. The object passed through our solar system so quickly that the opportunity to fully understand its behavior was fleeting. This mysterious acceleration of Oumuamua remains a subject of deep fascination for both astronomers and physicists. Its behavior continues to highlight the complex nature of objects from beyond our solar system. As we prepare for future interstellar visitors, scientists are developing more advanced observational tools and missions to identify and study these enigmatic travelers. The insights we gain from studying such objects could unlock fundamental knowledge about the forces and dynamics that govern the universe beyond our own solar system. Shifting from interstellar phenomena to the wonders of our own solar system, we find the enigmatic spokes of Saturn's rings, ghostly, radial features that have intrigued scientists for decades. Discovered by the Voyager spacecraft in the early 1980s and later studied in depth by the Cassini mission, these strange formations appear as faint striations that move in sync with Saturn's rings, briefly disturbing their otherwise smooth appearance. While their presence initially baffled researchers, it is now understood that the spokes are likely the result of an electrostatic interaction between the tiny particles in the rings and Saturn's powerful magnetic field. These particles, which are predominantly dust-sized grains, can become electrically charged through interactions with solar ultraviolet radiation or energetic particles trapped in Saturn's magnetosphere. When charged, these particles can be influenced by the planet's magnetic field, causing them to lift slightly above the ring plane. This creates the visible spokes, which appear as lighter or darker bands depending on the angle of the sunlight and the particle's electric charge. The spokes' intensity and visibility vary with Saturn's seasons, and they are most prominent during equinoxes, when the planet's rings align edge-on to the sun. This alignment allows for optimal ultraviolet radiation to charge the ring particles, leading to the creation of the spokes. What makes the spokes even more fascinating is their dynamic nature. They can form and dissipate over just a few hours or days, moving across Saturn's rings in synchrony with the planet's rotation. This rapid and temporary behavior suggests a delicate balance between electromagnetic forces and the physical properties of the ring particles. The study of these spokes not only enriches our understanding of Saturn's unique ring system, but also provides valuable insights into the behavior of dust in other astrophysical environments. The interaction between solid particles and plasma is a key phenomenon that shapes celestial bodies, and the spokes of Saturn's rings offer a tangible example of this interaction in action. Lastly, we turn our attention to Pluto, a world at the farthest reaches of our solar system, where one of its most iconic features, Tombaugh Regio, captures the imagination of all who study it. Tombaugh Regio, named after Clyde Tombaugh, the astronomer who discovered Pluto in 1930, is a vast, heart-shaped region on Pluto's surface. It is made up of two distinct lobes. The left lobe, Sputnik Planitia, is a massive basin filled with nitrogen, methane, and carbon monoxide ices, while the right lobe is marked by rugged mountainous terrain. The formation of Sputnik Planitia, a significant part of Tombaugh Regio, is thought to be the result of both internal and external forces acting on Pluto. One prevailing theory suggests that Sputnik Planitia was created by a massive impact event billions of years ago, possibly caused by an asteroid or comet. The impact would have formed a large basin that over time became a cold trap for volatile ices. These icy deposits, due to Pluto's unique climate and low elevation, were able to accumulate and contribute to the current shape of the region. As the ices built up, the crust of Pluto underwent a process known as isostatic adjustment, where the surface slowly rebounded and the basin filled in with the smooth, icy plains we see today. However, Sputnik Planitia is not just a passive region filled with ice. The area exhibits fascinating geological activity, particularly in the form of polygonal cells that have likely been caused by convection within the nitrogen ice. These convection patterns suggest that the ice is not static, but is instead being slowly renewed through the movement of material driven by the heat from Pluto's interior. This process, though incredibly slow, indicates that Pluto is still geologically active, a finding that adds yet another layer of intrigue to this distant dwarf planet, making it one of the most intriguing objects in our solar system. In summary, the study of both interstellar objects like Oumuamua and the features of our own solar system, such as Saturn's spokes and Pluto's Tombaugh Regio, continue to push the boundaries of our understanding of the cosmos. These phenomena highlight the complexity and mystery of the universe. offering new challenges and insights into the forces that shape not only our solar system, but also distant regions of space. As we continue to explore and uncover the secrets of these cosmic travelers and distant worlds, one thing is clear: the universe is full of surprises waiting to be discovered. In this fascinating exploration of our solar system, a curious discovery unfolds regarding the thermal dynamics of Pluto, a world long considered distant and frozen. Far from being a simple icy body, Pluto reveals itself to be a complex planet with a surprisingly high level of thermal activity, even at such great distances from the Sun. Tombaugh Regio, the right lobe of this dwarf planet, stands out with its rugged topography, a dynamic mix of nitrogen ice and water ice mountains. While the exact mechanisms behind the formation of this terrain remain shrouded in mystery, scientists suspect tectonic processes, sublimation, and a delicate interplay between different types of ice may be at work. What makes this region even more intriguing is its geological diversity, which holds critical clues to understanding how both internal and external forces shape Pluto's surface. The prominent positioning of Tombaugh Regio near Pluto's equator suggests that it plays a crucial role in the planet's climate. For example, the bright, reflective ices of Sputnik Planitia help control the temperature and pressure of Pluto's thin atmosphere by reflecting sunlight. This reflective surface is far more than just visually striking. It has a profound effect on the sublimation and condensation cycles of nitrogen and other volatiles. These cycles, in turn, influence atmospheric dynamics and contribute to seasonal changes on Pluto, adding layers of complexity to this distant world. The high-resolution images and data provided by NASA's New Horizons spacecraft, which flew by Pluto in 2015, have been instrumental in unraveling the complexities of Tombaugh Regio. These observations have unveiled unexpected geological activity and diverse surface compositions that challenge previous notions of what distant, small dwarf planets could be like. As scientists continue to analyze the data from New Horizons, they are developing new models that will deepen our understanding of how such features form. This ongoing research not only promises to offer fresh insights into planetary processes, but could also extend our knowledge about the formation and evolution of planets far beyond our solar system. Shifting our gaze further into space, another enigma presents itself on Venus, where radar reflections from its high lens have puzzled scientists since their discovery by the Magellan spacecraft in the early 1990s. These highlands, particularly regions like Maxwell Montes, exhibit bright radar signatures far more intense than the surrounding lowlands, sparking interest in their mysterious reflective properties. What causes these unusual radar reflections is a subject of ongoing investigation, and one leading hypothesis points to a fascinating interplay of Venusian geology and its harsh atmospheric chemistry. Venus's surface temperature is a staggering 465 degrees Celsius, about 870 degrees Fahrenheit, and its dense atmosphere is thick with sulfuric acid and carbon dioxide, creating an extreme environment for chemical reactions to occur. The reflective properties of the highland surfaces suggest that metallic or semi-metallic compounds may be the key to this mystery. In such conditions, minerals can react with atmospheric gases, leading to the precipitation of substances on the cooler surfaces of the highlands. Materials like pyrite, also known as fool's gold or bismuth compounds, may be responsible for the bright reflections seen in radar images. One plausible explanation is that these substances form through volcanic outgassing, where elements released by Venus's volcanic activity later condense and settle on the highlands. Sulfides such as pyrite could result from sulfur gases emitted during volcanic eruptions, combining with metallic elements present in the Venusian atmosphere. Another contributing factor could be the cooler temperatures at higher elevations, which, although still extreme by Earth standards, could allow certain minerals or metallic compounds to solidify into a form similar to frost. This solidified layer would enhance the radar reflectivity, making the highlands appear much brighter than the surrounding terrain. Together, these mysteries, Pluto's rugged ice mountains and Venus's reflective highlands, illustrate the incredible diversity of planetary processes occurring throughout our solar system. The more we learn about these distant worlds, the clearer it becomes that the universe is far more dynamic and intricate than we ever imagined. As technology advances, our ability to observe and understand these celestial bodies will only deepen, unlocking more secrets that could reshape our understanding of the cosmos. The surface roughness of celestial bodies, particularly on Venus, may play a crucial role in their radar reflectivity. Venus's highlands, for example, might exhibit a rougher surface texture at smaller scales, enabling them to scatter radar waves more efficiently. This enhanced scattering could be the result of a combination of geological processes, such as tectonic activity and erosion patterns, which are unique to the high-temperature, high-pressure environment of Venus. The data gathered from Mellon's radar mapping, complemented by observations from missions like the Arbo Observatory and Japan's Akatsuki probe, have been pivotal in refining our understanding of Venusian surface properties. As our technological capabilities advance, future missions such as NASA's Veritas and ESA's Envision aim to provide more in-depth radar and spectroscopic studies. These missions will likely shed light on the exact compositions responsible for Venus's high radar reflectivity, offering more profound insights into the geological and chemical processes that continue to shape the planet's enigmatic highlands. Miranda, one of the most intriguing moons of Uranus, presents a geological mystery like no other in the solar system. With a diameter of just 480 kilometers, about 300 miles, this small moon features a bewildering array of geological features that include colossal canyons, terraced layers, and vast racetrack-shaped bands known as coronae. These features point to a history of intense geological activity and highlight Miranda's complex and violent formation process. Leading theories suggest that the moon's patchwork-like surface could have emerged from multiple episodes of tectonic activity and cryovolcanism. Tidal forces exerted by Miranda's interactions with Uranus, along with gravitational influences from other moons, likely generated significant internal friction and heat within the moon, a phenomenon known as tidal heating. This heating may have led to partial melting of the interior, triggering convective motion and surface deformation. One of Miranda's most distinctive features, the coronae, could have been formed by warm ice diapers, blobs of molten ice that rose through the moon's cold, rigid outer shell. As these diapers pushed against the surface, they caused the terrain to stretch and crack, resulting in the characteristic ridges and troughs seen today. Miranda's expansive canyons, some reaching depths of up to 20 kilometers, may have formed through extensional tectonics, where internal forces caused the crust to stretch and fracture. Cryovolcanic activity involving the eruption of volatile substances like water, ammonia, or methane could have further reshaped the moon's surface, deepening the canyons and altering the landscape dramatically. Another theory proposes that Miranda may have undergone catastrophic disruption and reaccretion. This hypothesis suggests that a massive impact could have shattered the moon, causing it to break apart and later reassemble due to gravitational forces. This process would have resulted in the highly varied and heterogeneous surface that we observe today. Miranda's surface defies traditional geological expectations, showing clear evidence of resurfacing events across different epochs. Each geological unit on the moon's surface seems to tell the story of a distinct era, marked by tectonic and cryovolcanic activity. This makes Miranda a particularly fascinating subject for ongoing scientific study. While much of the data we currently have on the moon comes from Voyager 2's flyby in 1986, future missions to the Uranian system may offer deeper insights into Miranda's geological history, further elucidating the processes that have shaped this captivating moon. The origin of life on Earth remains one of science's most profound and puzzling questions, sparking a wealth of theories and research. Although definitive answers are still elusive, several leading hypotheses offer compelling possibilities for how life might have emerged from non-living chemical processes. One of the most widely discussed theories is the primordial soup hypothesis, which suggests that life began in a warm primordial ocean or pond, where simple organic molecules were exposed to energy sources like ultraviolet light, lightning, or volcanic activity. This environment, rich in reactive chemicals, could have provided the ideal conditions for the formation of more complex molecules, ultimately leading to the emergence of self-replicating molecules such as RNA. Experiments by Stanley Miller and Harold Urey in the 1950s helped support this theory. They demonstrated that when a mixture of water, methane, ammonia, and hydrogen was exposed to electrical sparks, simulating lightning, amino acids, the building blocks of proteins, could be synthesized. These findings provided vital insight into how life's molecular foundations could have arisen from simple compounds, offering a plausible explanation for one of the greatest mysteries of science. The origin of life remains one of the greatest mysteries of science, with multiple theories attempting to explain how simple molecules transitioned into the complex living organisms we know today. One of the most influential hypotheses is the hydrothermal vent theory, which suggests that life may have begun near the deep-sea hydrothermal vents on the ocean floor. These vents spew mineral-rich water, heated by the Earth's geothermal processes, into the cold depths of the ocean. This combination of extreme heat and abundant chemicals creates an environment rich in energy, potentially fostering the chemical reactions that led to the formation of life. Modern hydrothermal vents are home to diverse ecosystems that thrive in the absence of sunlight, relying entirely on chemosynthesis to fuel life. In such an environment, simple organic compounds could have interacted and assembled into more complex molecules, eventually forming the first living cells. Another compelling theory, known as the RNA world hypothesis, offers a slightly different view. It proposes that life began with RNA molecules, a unique type of molecule capable of both storing genetic information and catalyzing chemical reactions. RNA, unlike DNA, has the ability to replicate itself, and this self-replicating nature could have been the catalyst for the development of early life forms. According to this hypothesis, RNA molecules might have formed spontaneously from simpler precursors. Due to their catalytic properties, these molecules could have triggered the formation of additional RNA molecules, creating a primitive system of replication. This process might have set the stage for natural selection, favoring more efficient RNA replicators, eventually leading to the complex forms of life we recognize today. There is also the panspermia hypothesis, which takes a more cosmic approach. This theory suggests that life, or at least the building blocks of life, could have originated elsewhere in the universe and been transported to Earth on comets, asteroids, or meteoroids. While it doesn't explain how life first began, it shifts the origin of life beyond Earth to other celestial bodies. Though this theory remains controversial, it raises interesting questions about the potential for life beyond our planet, especially given the vast number of exoplanets that might harbor similar conditions to those on early Earth. Recent advancements in synthetic biology and prebiotic chemistry have provided some fascinating insights into how life could have arisen from non-living matter. Laboratory experiments have demonstrated that under the right conditions, lipid molecules can spontaneously form vesicles that resemble cell membranes. Additionally, amino acids and nucleotides, essential building blocks of life, can form peptide bonds and nucleic acids, respectively. These findings suggest that simple protocells, structures that mimic living cells but lack true replication and metabolism, could have emerged from natural processes on early Earth. While each of these theories presents its own challenges, they all contribute to a deeper understanding of life's potential origins. As research progresses, scientists may find ways to combine elements of these theories to develop a more comprehensive picture of the chemical processes that led to the emergence of life on our planet. But the implications of these discoveries extend far beyond Earth. One of the most exciting pursuits in modern science is the search for alien life, and identifying biosignatures, indicators of past or present life, will be key to this quest. Biosignatures are measurable characteristics, molecules, or phenomena that could indicate the presence of life elsewhere in the universe. Among the most promising biosignatures is the detection of oxygen and ozone in a planet's atmosphere. On Earth, oxygen is primarily produced by photosynthetic organisms. If oxygen or ozone were detected in an exoplanet's atmosphere, especially in conjunction with other gases, it could hint at biological processes similar to those on Earth. However, it's important to note that non-biological processes could also produce oxygen, so this biosignature must be considered alongside other potential indicators. Another key biosignature is methane. On Earth, methane is primarily produced by biological processes, such as microbial digestion. However, it can also be produced through geological processes. If methane and oxygen were detected together in an exoplanet's atmosphere, it would be particularly intriguing, as these gases would typically react with each other and neutralize one another. The presence of both gases suggests a continuous source, potentially linked to biological activity. Complex organic molecules such as amino acids and lipids also serve as potential biosignatures. These molecules form the building blocks of life, and their presence on another world could indicate the existence of life, or at least its precursor compounds. Scientists could search for these molecules either by directly analyzing samples from other planets or by using spectroscopic techniques to identify the specific wavelengths of light absorbed or emitted by these molecules. Finally, water vapor is another crucial element to consider. While water vapor alone is not a definitive biosignature, its presence on another planet is essential because all known forms of life require liquid water to survive. Thus, finding water vapor in the atmosphere of an exoplanet could significantly increase the chances of discovering life. These biosignatures, together with future technological advancements, could pave the way for the discovery of life beyond Earth, opening a new chapter in our understanding of the universe and our place within it. Exploring the possibility of life beyond Earth is one of humanity's most exciting and profound scientific endeavors. The detection of water vapor, along with other potential biosignatures, significantly increases the likelihood of identifying environments where life could thrive. But how do scientists narrow down the vastness of space to find signs of life? One key method involves the analysis of a phenomenon known as the red edge. This refers to a specific spike in the reflection of light in the near-infrared spectrum, a telltale sign of vegetation on Earth. If telescopes detect a similar spectral signature on an exoplanet, it could suggest the presence of photosynthetic organisms, a critical sign of biological activity. Another promising angle for detecting life is by examining isotopic ratios. Biological processes on Earth show a clear preference for lighter isotopes, elements with fewer neutrons. For example, Earth's life forms produce a significant surplus of the light isotopes of carbon, nitrogen, and sulfur. The detection of unusual isotopic ratios in the atmosphere of an exoplanet could therefore indicate biological processes, since these patterns are unlikely to occur naturally without the influence of life. A third important biosignature involves atmospheric disequilibria, which refers to the unnatural presence of certain gases that wouldn't normally coexist in an atmosphere without biological intervention. A combination of gases like methane and oxygen, or hydrogen and oxygen, would signal active biological processes. This is because such gases would react with each other in an atmosphere without life to maintain the delicate balance. Detecting such disequilibria could be one of the most compelling signs of ongoing biological activity on distant worlds. Advanced telescopes and space missions are getting better at detecting these biosignatures. Instruments like the James Webb Space Telescope, JWST, are capable of observing the atmospheres of distant exoplanets, identifying potential signs of life. Upcoming missions, like the European Space Agency's Ariel mission, aim to further hone in on these elusive biosignatures. In addition to studying distant exoplanets, missions targeting the icy moons of our solar system, such as NASA's Europa Clipper and ESA's JUICE mission to Jupiter's moon Ganymede, are looking for signs of life beneath the frozen surfaces of these worlds. Each potential biosignature, when considered alone, is fascinating. However, the most convincing evidence of extraterrestrial life will likely come from a combination of these indicators. When multiple biosignatures reinforce each other within the context of a planetary environment, they could paint a compelling picture of biological processes. The ultimate goal is to create a comprehensive profile of an exoplanet that strongly suggests it is harboring life. This approach would not only enhance our understanding of life beyond Earth, but could revolutionize the way we think about habitability in the universe. One of the key factors in the search for life is identifying Earth-like planets located within the habitable zone of their stars, the region where conditions may be just right for liquid water to exist on a planet's surface. Liquid water is a fundamental requirement for life as we know it, making the habitable zone a critical area of focus for astronomers. The ability to detect planets within this zone has improved dramatically with advances in space telescopes and observational methods, bringing us closer to answering the profound question of whether we are alone in the universe. NASA's Kepler Space Telescope, which operated from 2009 to 2018, made significant strides in this search. By monitoring the brightness of over 150,000 stars, Kepler was able to detect periodic dimming caused by exoplanets transiting in front of their host stars. Through these observations, Kepler discovered thousands of exoplanets, many of which are small and rocky, similar to Earth. Based on Kepler's data, current estimates suggest that about 20 to 25% of Sun-like stars may host at least one potentially habitable Earth-sized planet in their habitable zone. Further advancements in exoplanet exploration came with the launch of the Transiting Exoplanet Survey Satellite, TESS, in 2018. TESS continues Kepler's mission, focusing on nearby stars to identify Earth-like planets in the habitable zone. Ground-based observatories and the radial velocity method of detecting exoplanets add another layer of confirmation, refining our understanding of how common these potentially habitable planets might be. Yet, despite these incredible discoveries, not all planets found in the habitable zone are necessarily Earth-like. While size and location are important, other factors must also be considered to determine a planet's habitability. The composition of a planet's atmosphere, the presence of a protective magnetic field, geological activity, and, of course, the availability of liquid water all play crucial roles in sustaining life. As our technology advances and our knowledge deepens, the search for exoplanets that meet these criteria becomes ever more promising. In the quest for alien life, it's not just about finding the right location in space. It's about finding the right conditions, whether it's detecting the unique light signatures of photosynthetic life, analyzing atmospheric gases that indicate biological activity, or identifying planets with the perfect balance of size, location, and resources. Each discovery brings us one step closer to answering one of humanity's greatest questions. Is there life beyond Earth? In the vast expanse of the Milky Way, the quest to uncover planets that could support life continues to evolve with incredible discoveries and technological advancements. The range of a star's habitable zone, the region where liquid water could potentially exist on a planet, can vary dramatically depending on the star's size, type, and activity. Red dwarfs, the most abundant type of star in our galaxy, possess smaller and narrower habitable zones compared to stars like our Sun. While these stars are more common, they are also prone to intense stellar flares that can strip away a planet's atmosphere, presenting a significant challenge for the possibility of life. Considering that the Milky Way is home to an estimated 100 to 400 billion stars, scientists estimate that the fraction of these stars that host potentially habitable planets could mean there are billions of Earth-like worlds scattered throughout our galaxy. This number is not merely speculative. It continues to be refined as more exoplanets are discovered and studied in greater detail. With each new breakthrough, astronomers are able to improve their understanding of what makes a planet truly habitable. Much of the focus of these investigations is on nearby stars, such as the Proxima Centauri system, to gauge how common Earth-like planets might be. Proxima Centauri b, a planet orbiting within the habitable zone of the closest star to our Sun, has captured the attention of scientists worldwide. Although its exact conditions are still under intense study, its discovery offers hope that Earth-like planets might not be as rare as once believed. Upcoming missions, such as those involving the James Webb Space Telescope, the European Space Agency's Plato mission, and ground-based giants like the Extremely Large Telescope and the giant Magellan Telescope, are poised to offer detailed observations. These instruments are expected to analyze the atmospheres of exoplanets to search for signs of habitability or even biosignatures, traces of life itself. While the prospect of Earth-like planets in the habitable zone is certainly promising, determining whether these planets can truly host life requires an immense amount of research and technological refinement. As our understanding and tools improve, we will come closer to answering the question that has captivated humanity for centuries. Are we alone in the universe? Shifting our focus closer to home, the idea of life existing in the clouds of Venus has become an intriguing topic for scientists. Despite Venus's extreme surface conditions, temperatures reaching up to 465 degrees, 869 degrees Fahrenheit, and atmospheric pressure 90 times that of Earth's, some believe life could exist in the planet's upper cloud layers, which offer far milder conditions. At altitudes ranging from 30 to 70 degrees Celsius, 86 to 158 degrees Fahrenheit, and pressures similar to those on Earth's surface, these clouds present a potential habitat for life, though drastically different from what we know on Earth. Interest in Venus as a potential home for life surged in 2020 with the detection of phosphine, a molecule typically associated with anaerobic organisms, microbes that live in oxygen-poor environments like swamps or animal intestines. Phosphine on Earth is produced either industrially or by these types of organisms, leading some to speculate that similar life forms could exist in Venus's clouds. However, this discovery has not been without controversy. Critics have raised concerns over the validity of the data and the interpretation of the spectral lines. Nevertheless, the potential presence of a biosignature gas like phosphine has reignited interest in Venus's clouds and sparked calls for further investigation. If life does exist in the acidic clouds of Venus, it would require highly specialized organisms capable of surviving the harsh environment. These hypothetical life forms could possess biochemical mechanisms that allow them to neutralize or even exploit the acidic conditions. Some might survive by using the limited water vapor and particulate matter available in Venus's clouds to fuel their metabolic processes. Future missions, such as NASA's Da Vinci Plus and the European Space Agency's Envision mission, are set to provide much-needed insight into the planet's atmosphere and surface conditions. These missions will deploy advanced instruments capable of detecting trace gases, cloud particles, and atmospheric chemistry, giving us a deeper understanding of the potential for life in Venus's clouds. As we push the boundaries of what we consider possible for habitability, Venus is just one of many fascinating frontiers in the search for extraterrestrial life. Other candidates in our solar system include moons with subsurface oceans, such as Europa, Enceladus, and Titan, each of which offers unique environments that could be conducive to life. Europa, one of Jupiter's largest moons, that is particularly intriguing. Beneath its icy surface lies a global ocean of liquid water, twice the volume of Earth's oceans. Observations from the Galileo spacecraft and the Hubble Space Telescope have confirmed the presence of water vapor plumes erupting from cracks in Europa's icy shell, suggesting that its ocean could be in contact with a rocky seafloor, where hydrothermal vents may provide the necessary heat and nutrients to support life. Hydrothermal vents on Earth are teeming with life, and if similar conditions exist on Europa, it could be a potential hotspot for microbial or even more complex life forms. Enceladus, another moon of Saturn, has also shown promising signs. The Cassini spacecraft found evidence of water ice plumes erupting from Enceladus's south polar region, indicating the presence of liquid water beneath the surface. These plumes contain organic molecules, salty water, and even silica grains, all of which suggest hydrothermal activity on the ocean floor. The combination of liquid water, organic molecules, and energy sources makes Enceladus one of the most promising places to search for extraterrestrial life. Titan, Saturn's largest moon, offers an entirely different environment with surface lakes and seas made of liquid methane and ethane. In addition, Titan is thought to harbor a subsurface ocean of water beneath its thick, icy crust. The presence of both liquid methane and water raises the possibility that Titan could host life forms unlike anything we've seen on Earth. As we continue to explore these mysterious moons and planets, the potential for discovering extraterrestrial life becomes more real and more exciting. With each new mission, each new discovery, we edge closer to understanding whether we are alone in the universe or whether life exists in places beyond our imagination. On the surface of distant moons, hydrocarbons present a fascinating alternative to water-based chemistry, potentially enabling life forms that rely on methane solvents rather than water. However, beneath the thick, icy shells of moons like Europa and Enceladus lies subsurface oceans, more similar to Earth's own oceans than previously thought. these hidden oceans are becoming increasingly intriguing targets for future exploration, like offering the possibility of life in environments vastly different from our own. For life to thrive in these mysterious seas, several key conditions must be met. A stable environment with liquid water is essential, along with the presence of vital chemical compounds like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. In the absence of sunlight, life would depend on chemical energy derived from hydrothermal vents or reactions involving icy materials, offering a potential lifeline to sustain biological processes. The discovery of organic molecules and possible energy sources in the plumes of Enceladus and the surface of Europa strengthens the argument that these moons might harbor life beneath their icy exteriors. The excitement is mounting as future missions aim to explore these moons in unprecedented detail. NASA's Europa Clipper, scheduled to launch in the 2020s, will embark on a mission to perform detailed reconnaissance of Europa's ice shell and subsurface ocean. Its primary goal will be to assess the moon's habitability by studying the thickness of the ice, the composition of the ocean, and the potential for hydrothermal activity beneath the frozen surface. Meanwhile, the proposed Enceladus Lifefinder mission aims to capture and analyze samples from the moon's plumes, seeking signs of life that could reside in its watery depths. Titan, the enigmatic moon of Saturn, will be the focus of NASA's Dragonfly mission, which will send a rotorcraft to explore its diverse surface and atmospheric chemistry. While it won't directly probe the subsurface ocean, it will investigate prebiotic chemistry and explore methane-based life hypotheses. As we turn our gaze toward these icy worlds, we are not only searching for life, but also expanding our understanding of how life might adapt to survive in extreme environments far beyond Earth. The study of extremophiles, organisms that thrive in environments once thought to be inhospitable, has dramatically broadened the scope of where life might exist in the universe. These remarkable organisms not only challenge our definition of habitable environments on Earth, but also provide critical insights into survival strategies that could be applicable elsewhere in the cosmos. One key lesson from extremophiles is the extraordinary adaptability of life. These organisms can endure a vast array of environmental conditions, some of which are strikingly similar to those found on other planetary bodies. For example, thermophiles and hyperthermophiles, which flourish in the extreme heat of deep-sea hydrothermal vents, provide evidence that similar habitats could exist on moons like Europa and Enceladus, where hydrothermal activity could support microbial life beneath the icy crusts. The potential for water-rock interactions in these subsurface oceans could create niches where life might thrive, akin to the deep-sea extremophiles on Earth. Acidophiles and alkaliphiles, which survive in environments with highly acidic or alkaline conditions, demonstrate that extreme pH levels do not necessarily preclude the existence of life. This discovery is particularly relevant for missions to Venus, where the acidic clouds might harbor life forms capable of withstanding such harsh conditions. Similarly, evidence from Mars, such as ancient lake beds that suggest past acidic conditions, hints that microbial life could have flourished during wetter periods in the planet's history. On icy worlds, cryophiles, organisms that thrive in sub-zero temperatures, offer crucial insights into how life could survive in places like Europa and Enceladus, where frozen surfaces dominate. Antarctic lakes, where psychrophiles exist, serve as terrestrial analogs for these distant moons, helping scientists understand how life might endure in perpetual ice. In these conditions, life would rely not on sunlight, but on chemical reactions for energy, just as extremophiles on Earth do in places devoid of light. Xerophiles, organisms that endure extreme desiccation, provide valuable models for understanding potential life on Mars, where the surface is dry and arid. On Mars, features like recurring slope lineae and evidence of brines suggest that temporary wet conditions might provide windows of opportunity for life to emerge from dormancy. The resilience of life extends beyond temperature and chemical tolerance. It also encompasses radiation. Organisms like Deinococcus radiodurans, known for withstanding high levels of radiation, shed light on the potential for life to endure extreme radiation on planets like Mars or moons like Europa. On Mars, the thin atmosphere offers little protection from cosmic and ultraviolet radiation, making the survival strategies of radiation-resistant extremophiles particularly pertinent. Likewise, beneath Europa's ice shell, life could be shielded from radiation, suggesting that a habitable environment may exist despite the radiation-rich surface conditions. Extremophiles not only push the boundaries of our understanding of life's limits, but also illuminate possible metabolic pathways that life might use. For instance, chemoautotrophs, organisms that derive energy from inorganic compounds, suggest that extraterrestrial life could rely on chemical energy rather than sunlight, utilizing processes like methanogenesis or sulfur reduction. These metabolic pathways could be critical for sustaining life in the dark, cold, and high-pressure environments beneath the icy shells of moons like Europa and Enceladus. Hydrothermal vents or water rock reactions in these subsurface oceans could serve as vital sources of energy for microbial life, underscoring the potential habitability of these alien worlds. The ongoing study of extremophiles continues to shape the design of future missions aimed at detecting life in extreme environments. As technology evolves and our understanding of life's resilience grows, the search for extraterrestrial life becomes more hopeful and exciting, promising to answer one of humanity's greatest questions: are we truly alone in the universe? For instance, the upcoming Europa Clipper and Mars 2020 missions are armed with advanced analytical tools, specifically designed with insights from extremophiles in mind. These tools aim to detect biosignatures, like specific molecules, isotopic ratios, or certain minerals that are often linked with life. Extremophiles, these extraordinary organisms that thrive in extreme environments on Earth, have radically transformed our understanding of life's resilience and adaptability. They provide invaluable models, guiding the search for life in the universe. These models help shape mission designs as well as experiments aimed at uncovering the possibility of life across the solar system and beyond. The possibility of silicon-based life is an especially fascinating topic, one that challenges the very foundations of biology and chemistry. While carbon is considered the cornerstone of life on Earth due to its versatility and ability to form stable, complex molecules, silicon is an intriguing alternative. Positioned just below carbon on the periodic table, silicon shares several chemical similarities with its neighbor. In theory, silicon could form 4 covalent bonds, just as carbon does, enabling the construction of complex molecules potentially capable of sustaining biological structures. Moreover, silicon can bond with oxygen, nitrogen, and hydrogen, all elements essential for life as we know it. However, despite its potential, silicon-based life faces numerous challenges. The first obstacle lies in the strength and stability of silicon-silicon bonds, which are weaker than the carbon-carbon bonds that form the backbone of organic life. This makes it difficult to create large, stable macromolecules, essential for life's complexity. Additionally, silicon tends to form strong bonds with oxygen, leading to the creation of solid silicates like quartz, rather than the flexible, dynamic molecules that support life's intricate biochemistry. Whereas carbon-based molecules such as proteins and nucleic acids can easily rearrange and interact dynamically, silicon-based molecules might lack this flexibility. Furthermore, when carbon oxidizes, it forms carbon dioxide, a gas that organisms can exhale with ease. In contrast, oxidized silicon forms silicon dioxide, or silica, which is solid at Earth-like temperatures and would be difficult for a living organism to expel or manage. This presents a serious hurdle, as the solid form of silica could impede the biochemical cycles required for life. Another limitation lies in silicon's inability to match carbon's versatility. While carbon forms a wide variety of compounds, essential for life's biochemical processes, silicon, despite its ability to form diverse compounds, cannot compete with carbon's vast array of complex molecules necessary for sustaining life. Additionally, the environmental constraints on potential silicon-based life are profound. It is speculated that such life forms might require environments vastly different from those we are familiar with. For example, conditions with higher temperatures and lower humidity might be more suitable for the stability of silicon compounds. Alternatively, silicon-based biochemistry could thrive in environments with solvents such as ammonia or methane, as we see on Titan, Saturn's largest moon. However, despite these theoretical possibilities, no silicon-based life has ever been observed. Yet, This idea is not entirely dismissed. In fact, it encourages scientists to maintain an open mind, remaining open to the diverse forms life might take, especially in extreme environments. Science fiction has long explored the concept of silicon-based life, imagining everything from crystal-like organisms to biochemistries in extreme planetary conditions. Such speculation emphasizes the adaptability and resilience of life, potentially even beyond the familiar carbon-based frameworks. Ongoing research in astrobiology and exoplanet studies is crucial to this understanding, expanding the potential for finding life beyond Earth. Missions like the James Webb Space Telescope aim to analyze the atmospheres of exoplanets, seeking chemical signatures that could point to life forms that are entirely different from what we know. While carbon remains the most likely foundation for life as we understand it, the investigation into silicon-based life broadens the scope of our search for extraterrestrial life. It compels us to look beyond Earth-centric biases and consider the possibility that life may take forms we cannot yet fathom. This expanded search for life and the recognition that life could thrive in many different environments is crucial to our understanding of life in the universe. Moreover, another crucial element in the search for extraterrestrial life lies in the detection of technosignatures, evidence of advanced civilizations beyond Earth. These technosignatures encompass a wide array of potential indicators, each requiring sophisticated methods and instruments for detection. Among the most promising of these are radio signals. Radio waves can travel vast distances across space with minimal interference, making them an ideal candidate for communication. Radio telescopes, such as the Allen Telescope Array and the Green Bank Telescope, continuously scan the cosmos for patterns that may signify intelligent origins. Another method of detecting technosignatures involves looking for powerful optical signals. These could take the form of laser pulses, used either for communication or as beacons. Lasers emit highly coherent light, standing out against the background starlight. Instruments like the Laser SETI project are specifically designed to detect such signals by scanning large sections of the sky for bright flashes of light at distinct wavelengths, which could indicate laser activity from extraterrestrial sources. Perhaps one of the most intriguing possibilities for identifying extraterrestrial civilizations is the detection of Dyson spheres, enormous structures that advanced civilizations might construct to harness the energy of their stars. These megastructures, which could partially or completely encircle a star, would generate unique infrared signatures. A star surrounded by a Dyson swarm, for example, would emit less visible light but more infrared radiation, as the starlight would be absorbed and re-emitted as heat. Surveys conducted by spacecraft like the Wide Field Infrared Survey Explorer WISE could potentially reveal such anomalies, providing a breakthrough in our search for alien civilizations. By exploring these methods and refining our technologies, we edge closer to answering the ultimate question: are we truly alone in the universe? Or is there a thriving cosmos of life waiting to be discovered? In the vast expanse of space, there are multiple ways in which we might uncover evidence of advanced civilizations beyond Earth. One intriguing approach is the observation of artificial satellites and space debris. By using high-resolution imaging and spectroscopy, we could detect unusual objects or reflections moving in non-natural orbits, potentially signaling the presence of an advanced civilization. These technological signatures, such as concentrated satellites or even entire space habitats, could offer critical clues to civilizations that have reached an industrial or technological threshold. Such investigations could be key to understanding how other star systems are developing, or even whether they have already mastered space travel. Along with the tracking of artificial objects, industrial pollutants could also reveal the presence of advanced civilizations. Certain chemicals, like chlorofluorocarbons, CFCs, are industrial pollutants that are not naturally abundant in the cosmos. Detecting such compounds in the atmospheres of exoplanets through spectroscopic analysis could offer evidence of industrial activity. The upcoming James Webb Space Telescope and future instruments are designed to delve into these atmospheric signatures, opening a window to possible civilizations that may be altering their environment in ways we can detect. These pollutants might serve as the fingerprints of a civilization's technological advancement, offering an unprecedented opportunity for discovery. Another potential marker of a technologically advanced society is city lights. Planets with significant technological development may emit a faint but detectable glow from artificial illumination during their nighttime hours. This non-natural, non-periodic light variation could be spotted through sensitive instruments capable of distinguishing the faint glow from the planet's natural light. Projects such as the Extremely Large Telescope, ELT, or similar high-resolution instruments could identify these anomalies, giving us a closer look at planetary development beyond Earth. The ability to discern artificial city lights could transform our understanding of how far technological societies might have evolved. Mega engineering projects could also leave behind traces that reveal the activity of an advanced civilization. Consider large-scale undertakings like altering the light curve of a star. Methods such as star shading or stellar lifting could manipulate the light emitted by a star in detectable ways. These alterations could be observed as unusual or repetitive dimming and brightening patterns, which would suggest the presence of vast structures or activities altering the star's brightness. Long-term monitoring of star systems by missions like TESS, Transiting Exoplanet Survey Satellite, and other future space observatories may help detect these engineering feats, allowing us to identify the incredible capabilities of civilizations that have far surpassed our own. Interstellar probes, often called Bracewell probes, could also be key indicators of intelligent life. These autonomous spacecraft are designed to seek out and communicate with other civilizations across the cosmos. Detecting such probes might involve identifying their propulsion methods or the signals they emit. Although no direct evidence has been found yet, objects like Oumuamua, which pass through our solar system, serve as intriguing clues. While no technosignatures were found in that instance, the search for such probes is inherently multidisciplinary. This requires advances in astronomy, physics, engineering, and data analysis, as well as international collaboration. Future space missions may eventually detect these probes, offering humanity one of its most profound discoveries: proof of extraterrestrial intelligence. The study of technosignatures represents a rapidly evolving field, with exciting prospects ahead. With the development of new technologies and computational techniques like machine learning and artificial intelligence, we are now better equipped to analyze the vast amounts of data gathered in these searches. These tools enhance our ability to detect faint, distant signals that might otherwise be overlooked, bringing us closer to uncovering the truth of whether we are alone in the universe. But what if life itself is not exclusive to Earth? Panspermia is an intriguing hypothesis that suggests life, or its precursors, could travel across the universe, potentially from one planet to another. This concept challenges the traditional belief that life must originate independently on each world it inhabits. Instead, panspermia proposes that life might spread through the cosmos via natural mechanisms, such as radiation pressure or cosmic events. Several variations of this hypothesis offer different possibilities for how life could be distributed. Lithopanspermia, for instance, suggests that microorganisms could hitch a ride on space rocks like asteroids and comets. A major impact on a planet such as Mars could eject rocks containing microbial life into space. These rocks might then travel through the vacuum of space, eventually landing on another planet like Earth and potentially seeding it with life. The discovery of Martian meteorites on Earth provides some support for this idea, suggesting that material exchange between planets is indeed possible. Ballistic panspermia takes a similar approach, but focuses on the transfer of life within a single stellar system. It emphasizes how impacts on moons or planets could eject microorganisms to other planets or moons in the same system. For instance, meteorite impacts on a moon of Jupiter could send life to another of Jupiter's moons, fostering the exchange of life between distant worlds in the same planetary system. Radiopanspermia proposes that radiation from stars could push microscopic particles or spores through the vast expanse of space. While the vast distances make this form of panspermia less likely than lithopanspermia, it remains a possibility. The force exerted by starlight could, in theory, carry tiny life forms across interstellar distances, although this would take much longer and be more difficult to detect. Finally, directed panspermia suggests that intelligent extraterrestrial civilizations might deliberately seed life on suitable planets. This speculative variation proposes that advanced beings could transport microbial life to planets capable of sustaining it, spreading life intentionally across the universe. Each of these theories offers a fascinating view into the potential paths that life might take across the cosmos. As we continue to refine our techniques for detecting technosignatures, we are also expanding our understanding of how life itself could travel through the stars. With the right tools and collaboration, the search for life beyond Earth and the discovery of intelligent civilizations remains one of humanity's most exciting quests. Panspermia, an intriguing hypothesis in astrobiology, posits that life may spread throughout the cosmos, either as a result of intentional exploration or as a natural means of survival. This theory has profound implications for how we understand the distribution and origins of life. If life on Earth began elsewhere in the universe, it would suggest that the biochemical traits fundamental to life are not as unique as previously thought. In fact, this could mean that life is far more widespread in the cosmos than we currently imagine, potentially appearing anywhere conditions are conducive to its survival. The concept of interconnected biospheres further amplifies this idea, proposing that the ecosystems of different planets could be linked in a way we've yet to fully understand. Imagine discovering life with a similar biochemical makeup on distant planets. It would provide compelling evidence that microbial life could endure the harsh conditions of space travel, defying the boundaries we once thought confined it to Earth. This interconnectedness could mean that life spread across the universe isn't just possible, it's a probable reality. Astrobiological missions currently underway or planned, such as those exploring Mars, Europa, and Enceladus, are not solely focused on finding indigenous life forms. They also aim to detect signs of life that may have traveled across space, transported by the forces of panspermia. If these missions were to uncover microbes genetically similar to Earth's life, it would be a breakthrough discovery supporting the theory of panspermia. Research into extremophiles, organisms that thrive in extreme conditions, has already provided some insight into this possibility. Experiments have demonstrated that certain extremophiles can survive the vacuum of space, withstanding high radiation levels, intense temperatures, and the challenges of space travel itself. While the concept of panspermia is both compelling and scientifically supported by the resilience of extremophiles, direct evidence remains elusive. However, future missions to Mars, like NASA's Perseverance rover and ESA's ExoMars mission, as well as exploration of the icy moons of the outer solar system, may hold the key to answering this question. If organic compounds or life forms with origins outside our planet are discovered, it would dramatically shift our understanding of the distribution of life, its resilience, and the potential for interconnected biospheres throughout the universe. Planetary habitability is a complex and dynamic process that evolves over geological timescales, influenced by numerous factors. Understanding these factors is essential for guiding our search for extraterrestrial life and evaluating the conditions necessary to sustain life. One of the most significant of these factors is stellar evolution. As stars age, they undergo profound changes in luminosity, radiation output, and spectral type. Our own sun, for example, is gradually increasing in brightness. In its early years, when it was dimmer, the habitable zone, the area around a star where liquid water could exist, was much closer to the sun. As the sun brightens over time, this habitable zone shifts outward. Eventually, this increase in solar flux will trigger a runaway greenhouse effect on Earth, rendering the planet uninhabitable. Similarly, the evolution of other stars can either enhance or diminish the habitability of surrounding planets. Another key factor influencing planetary habitability is volcanism and geothermal activity. Volcanic processes play a critical role in cycling essential elements and maintaining a planet's atmosphere. Volcanic outgassing, for example, replenishes greenhouse gases like carbon dioxide, which are vital for sustaining a stable surface temperature. However, excessive volcanic activity can lead to dramatic climate shifts, such as global cooling during a volcanic winter or warming from an intensified greenhouse effect. The balance of volcanic processes and their duration is critical in maintaining the conditions necessary for life. Finally, plate tectonics is essential in regulating a planet's climate and supporting life. The movement of lithospheric plates facilitates geological processes that help maintain the planet's climate over long periods. One of the most important contributions of plate tectonics is its role in the carbon-silicate cycle, which acts as a thermostat for the planet, regulating the levels of carbon dioxide and, in turn, stabilizing the planet's temperature. The ongoing dynamic interactions between these geological processes are essential for the long-term habitability of a planet. In conclusion, while the concept of panspermia is a fascinating and compelling hypothesis, much more research is needed to uncover definitive proof. Whether through astrobiological missions or further study of extreme life forms on Earth, the search for extraterrestrial life will continue to expand our understanding of life's distribution, its resilience, and the interconnectedness of biospheres across the universe. Understanding planetary habitability in the context of stellar evolution, volcanism, and plate tectonics will provide us with the insights necessary to explore new worlds, and perhaps new forms of life. This process begins with the weathering of silicate rocks, where minerals break down over time, releasing carbon into the atmosphere. It's followed by the subduction of carbonates into the mantle, where they can be recycled back to the surface through volcanic activity. Volcanic outgassing, in turn, releases gases that help regulate a planet's climate. A tectonically active planet can stabilize its climate over long geological periods, which increases its ability to support life. This is why Earth, with its active plate tectonics, remains relatively stable and hospitable compared to other celestial bodies. A planet's magnetic field plays a pivotal role in shielding its atmosphere from harmful solar and cosmic radiation. This magnetic barrier prevents the stripping away of atmospheric gases by the solar wind, which could otherwise erode the planet's atmosphere over time. The strength and configuration of this magnetic field can change as a planet evolves, and any loss or weakening of the field can have dire consequences for habitability. Mars, for example, experienced a weakening of its magnetic field, leading to significant atmospheric loss and eventually a decline in its ability to support life. In contrast, a robust magnetic field helps retain a planet's atmosphere, ensuring the protection of surface life from dangerous radiation. The presence of this field is essential for maintaining the conditions necessary for habitability. Large asteroid or comet impacts are another crucial factor in determining a planet's habitability. These cosmic events can lead to environmental catastrophes that result in mass extinctions, climate shifts, and even volcanic eruptions. However, impacts can also bring essential building blocks for life: water, organic molecules, and other materials crucial for sustaining life. In the early history of planets like Earth, such impacts may have been integral to the development of life, delivering the necessary elements to kickstart biological processes. Over geological timescales, a planet's climate can undergo dramatic changes. These changes are driven by a variety of factors, including orbital variations, Milankovitch cycles, which refer to periodic changes in Earth's orbit, axial tilt, planetary rotation, and interactions with other celestial bodies. These factors influence the distribution of sunlight, shifting climate patterns across regions and altering the conditions for life. Earth's history provides vivid examples of these dynamic processes, including several periods of rapid climate shifts, such as ice ages, warm periods, and mass extinctions. For instance, the Paleocene-Eocene thermal maximum, which occurred around 56 million years ago, was a period of rapid global warming, likely triggered by volcanic activity and the release of methane from frozen clathrates. During ice ages, vast ice sheets expanded, cooling the planet and altering habitats significantly. Mars and Venus offer important insights into how a planet's habitability can change over time. Mars, once a potentially habitable world with liquid water and a thicker atmosphere, lost much of its atmosphere and water due to several factors, including its weak magnetic field. Venus, on the other hand, likely experienced a runaway greenhouse effect, causing it to become the scorching, inhospitable world we observe today. Understanding the ways in which a planet's climate can evolve, whether through natural catastrophes or slow environmental shifts, offers invaluable insights into the factors that influence habitability. This understanding of planetary habitability is essential not only for assessing the potential for life on other worlds, but also for understanding the long-term future of Earth. By examining these processes, we can better identify which planets in our galaxy might be capable of supporting life and what might threaten their ability to do so over vast time periods. As we look to the stars in search of extraterrestrial life, the lessons learned from Earth's dynamic past guide us, helping to shape our exploration and our understanding of what it truly takes for a planet to remain habitable over millions or even billions of years.